Space has long captivated human imagination, yet beyond the familiar stars and planets lies a realm full of astonishing and mind-bending phenomena that challenge everything we think we know about the universe. Tonight, we embark on an awe-inspiring journey through the cutting-edge discoveries and theories that are reshaping modern astronomy. From planets pushed to their limits to the largest cosmic structures, we'll delve into the extraordinary evidence driving some of the most compelling space science questions of our time. Join us as we venture beyond the boundaries of conventional understanding in search of the universe's most spectacular mysteries. One such mystery is WASP-12b, a planet so extreme it's earned the chilling moniker, the Planet of Death. Orbiting its parent star at a perilously close distance, this exoplanet completes a full orbit in just over 25 hours, barely enough time for its surface to cool before it's bathed in the scorching heat once more. The proximity to its star subjects WASP-12b to immense gravitational forces and temperatures exceeding 2,000 degrees Celsius. These brutal conditions have led to a cosmic tug-of-war between the planet and its star, pulling at its atmosphere with such intensity that it begins to peel away layer by layer. Over time, this gravitational stripping results in the planet losing material at an astonishing rate, consuming itself piece by piece. This destruction is accelerated by the intense heat, which further expands the atmosphere, making it even more vulnerable to being stripped away. If this relentless process continues, WASP-12b may be completely consumed in tens of millions of years, a rapid timeline in cosmic terms, though seemingly vast by human standards. This harsh fate provides invaluable insight into the life cycles of stars and the perilous orbits of exoplanets caught in their gravitational grip. It serves as a reminder of the universe's immense power, where even the most distant worlds can meet a tragic end. But the extremes don't stop there. On planets like Neptune and Uranus, something truly bizarre is happening beneath the icy clouds. Researchers have discovered that within the atmospheres of these frozen gas giants, diamonds are literally raining down. The conditions on these planets, extreme temperatures and pressures, are unlike anything we experience here on Earth. Deep within their atmospheres, methane molecules break down under crushing pressure, releasing carbon atoms, which then crystallize into diamonds. These diamonds grow over time, falling towards the planet's cores like raindrops. As they plunge deeper into the planet's interior, these sparkling gems are crushed even further, potentially forming enormous chunks of diamond. This stunning phenomenon reshapes our understanding of planetary interiors, offering a scientific explanation for unusual atmospheric conditions and the internal dynamics of gas giants. While the diamonds may never reach the surface, their transformation under extreme pressures reveals the breathtaking hidden complexities of distant worlds. On exoplanet HD 199773b, an entirely different kind of atmospheric phenomenon is occurring: glass rain. Located around 63 light-years from Earth, this gas giant experiences temperatures upwards of 1,800 degrees Celsius and winds that reach speeds exceeding 2 kilometers per second. These extreme conditions cause silicate molecules in the atmosphere to vaporize, then cool and condense, falling back to the surface as razor-sharp shards of glass. The fierce winds on this planet cause the glass to fall sideways, creating a terrifying and surreal weather pattern. This constant cycle of vaporization and condensation raises fundamental questions about the diversity of weather systems beyond Earth. The existence of glass rain emphasizes the vast array of atmospheric conditions that exoplanets can exhibit, offering astronomers crucial insights into the complexities of distant atmospheres. It's a vivid reminder that in space, the unimaginable is possible. But perhaps no planet embodies the extremes of the cosmos better than Kelt 9b, the hottest exoplanet ever discovered. With surface temperatures exceeding 3,000 degrees Celsius, this world is hotter than some stars. Orbiting its parent star, Kelt 9, an ultra-hot A-type star nearly 2.5 times more massive than our Sun, Kelt 9b experiences an unimaginable amount of heat and radiation. The star's scorching surface temperature of around 30,000 degrees Celsius is more than 5 times hotter than our own Sun, making this exoplanet's environment almost incomprehensible. This planet orbits in just under 1.5 days, causing it to constantly be exposed to intense radiation that strips away its atmosphere. At such high temperatures, the gases in its atmosphere, such as iron, become so hot they exist in a gaseous state. In the face of this extreme radiation, Kelt 9b challenges our existing ideas about planetary atmospheres, revealing just how different conditions can be on worlds orbiting stars much hotter and more massive than our Sun. Korot 7b is another extreme world, earning the nickname Lava Planet due to its blistering surface temperatures of around 1,000 degrees Celsius. This exoplanet orbits its host star so closely that it completes an entire orbit in only 20 hours, exposing it to relentless radiation. The intense heat causes parts of the planet's surface to melt, forming lakes of lava that dominate vast stretches of terrain. Unlike Earth, where plate tectonics and a stable atmosphere create diverse landscapes, Korot 7b is a barren, molten world with an atmosphere that likely fails to form at all due to the extreme heat. This molten surface and the absence of weather systems make Korot 7b an inhospitable place for life, but a fascinating study in planetary evolution. It serves as a stark reminder that in the universe there are worlds where geological activity is defined not by the familiar forces of plate tectonics, but by extreme heat and volcanic chaos. Finally, there are the rogue planets, those wanderers of the cosmos that drift aimlessly through the galaxy, untethered to any star. These mysterious worlds may have formed in the same way as regular planets, but for one reason or another they were ejected from their solar systems, cast into the cold darkness of space. Despite the absence of a sun, rogue planets have shown that they possess a remarkable ability to survive. Their atmospheres, warmed by internal heat rather than stellar radiation, allow them to retain a strange and unpredictable existence. These rogue worlds, though adrift and isolated, challenge the traditional definition of a planet. They exist in the most remote regions of space, far beyond the comforting glow of any star. Their survival, despite the harshness of their environments, raises important questions about how planets form, evolve, and persist in the universe, even when their parent stars are no longer there to provide warmth and light. In these extreme and varied worlds, we glimpse the incredible diversity of environments that exist beyond our solar system. From diamond rain to molten landscapes and rogue wanderers, the cosmos continues to surprise us with its boundless creativity and complexity. As our understanding of space deepens, so too does our appreciation for the astonishing variety of planets, stars, and phenomena that shape the universe. However, violent gravitational interactions, particularly those that occur during close encounters with other celestial bodies, have the power to eject planets from their home systems, casting them into the vast empty stretches of interstellar space. These rogue planets, as they are called, become wanderers in the universe, drifting without the gravitational anchor of a star. Yet, one of the key factors that may determine the survival of these lost worlds lies within their own internal heat. Many rogue planets manage to retain the warmth they generated during their formation, coupled with the heat produced by the radioactive decay of elements deep within their cores. This residual heat is crucial. It sustains the planet's internal activity for much longer than might be expected. The warmth allows these planets to maintain geological activity, potentially supporting some form of atmosphere, even if that atmosphere is thin and fragile. Without the energy of a nearby star, rogue planets inevitably face a gradual cooling over time. But the heat from their early days can keep their interiors active for long, extended periods. This dynamic could allow them to maintain unique characteristics that defy the conventional model of planetary life. Some scientists believe that rogue planets could harbor unusual forms of atmospheric chemistry. It's been proposed that they might even possess thick atmospheres, composed of gases like hydrogen or ammonia. These atmospheres could trap heat, creating temporary habitable-like environments. On these worlds, the right conditions could even allow liquid water to exist. If the planet is large enough to retain its atmosphere against the vacuum of space, this could lead to fleeting yet fascinating habitable conditions in the planet's twilight zone. Though rogue planets face significant challenges when it comes to maintaining stable, habitable conditions, their very existence provides a fascinating lens through which scientists can study planetary formation and survival in the harshest of conditions. These wandering worlds challenge our preconceived notions of what is necessary for life and force us to rethink what makes a planet capable of sustaining life. Their unique properties make rogue planets some of the most intriguing subjects for scientific exploration. They hold the potential to broaden the very definition of habitable environments in the universe, igniting curiosity and pushing the boundaries of what we thought possible. Understanding the mysteries of these wandering planets may hold the key to uncovering new, surprising insights about the cosmos. One of the most remarkable exoplanets discovered to date is June 347b, often called Super Saturn, due to its dazzling and elaborate ring system. Discovered in 2012, June 347b is located around 400 light-years from Earth in the Centaurus constellation. This planet boasts features that not only rival those of Saturn, but in many respects exceed them. The most striking feature of June 347b is the sheer scale of its rings. The rings are believed to span over 100 times the radius of the planet itself. They are vast and staggeringly massive, hinting at a complex structure that likely varies in density and composition. The ring system of June 347b is made up of multiple bands of icy and rocky particles, not unlike the famous rings of Saturn. However, what sets this exoplanet apart is the possibility that these rings are not simply a collection of debris, but might also be accompanied by orbiting moons or moonlets. These smaller bodies could play a significant role in shaping the intricate dynamics of the ring system. Recent observations suggest that the rings are composed of various materials, possibly interspersed with gaps and waves, features that could be caused by the gravitational influence of the moons. Another fascinating aspect of June 347b is its enormous size. This planet is thought to be about 20 times the mass of Jupiter, making it significantly more massive than Saturn. The planet's immense mass could be one of the factors contributing to the complexity of its rings. The stronger gravitational forces exerted by a planet of such mass might foster more intricate interactions between the planet's moons, its rings, and the surrounding environment. These interactions could play a pivotal role in the formation and ongoing evolution of its ring system. In many ways, June 347b serves as a key subject for planetary scientists, offering a rich source of data about the diversity of planetary systems beyond our solar system. This exoplanet's massive size and remarkable ring system provide a glimpse into the dynamic processes that govern planetary formation and the evolution of rings around giant planets. Studying June 347b allows scientists to unravel new details about how such complex features arise, providing us with a deeper understanding of the universe's intricate cosmic tapestry. Another mysterious and captivating world is Gliese 436b, a planet that has earned the nickname Icefire Planet due to its extreme and paradoxical environmental conditions. Orbiting its host star at an extraordinarily close distance, Gliese 436b experiences temperatures that soar beyond 800 degrees Celsius on its surface, scorching the planet in intense heat. However, its name comes not just from its scorching surface temperatures, but from its highly unusual atmospheric composition. Despite its intense heat, this exoplanet is believed to harbor a unique blend of cold and hot regions, resulting in a dramatic juxtaposition of fiery heat and icy conditions. It's a world where extremes collide, creating an environment that is both fascinating and confounding to astronomers and researchers. The nature of Gliese 436b invites deeper questions about the forces at play in such environments. How do planets that exist in such extreme conditions maintain stability, and what could these hostile worlds teach us about the nature of planetary atmospheres and their ability to sustain any form of life, however unlikely it may seem? However, despite the scorching heat that defines its environment, a significant portion of the planet Gliese 436b is believed to be composed of water, yet in its solid form. This creates a fascinating juxtaposition of ice and fire, a dynamic that challenges our understanding of how extreme temperatures and pressures can coexist on the same world. The physical structure of Gliese 436b is a testament to the planet's ability to maintain stability in the face of these extreme conditions. The planet's intense gravitational field subjects its surface to immense pressures, which play a crucial role in shaping its unique characteristics. Water, under such extreme pressure, undergoes remarkable transformations, allowing it to remain solid even at temperatures that would otherwise turn it into gas on Earth. This phenomenon results in an unusual form of ice, capable of enduring temperatures that would incinerate typical ice forms elsewhere in the cosmos. As a result, the surface of Gliese 436b could potentially feature vast ice formations, or even oceans, all while the surrounding atmosphere remains hostile, thick with gas and blisteringly hot. Beneath this dense gaseous layer, an unexpected coexistence of solid ice and fiery heat unfolds, demonstrating a remarkable balance of extremes. The planet's atmospheric composition adds further complexity to this scene. Primarily made up of hydrogen and helium, the atmosphere plays a vital role in trapping heat, maintaining conditions where water can exist in such a solid state, while the external environment remains fiery and relentless. The interplay of temperature and pressure results in a planetary ecosystem where ice and fire are not opposites, but complementary forces that shape the world in extraordinary ways. This delicate balance between pressure, temperature, and the state of matter reveals how divergent planetary environments can intersect, redefining our understanding of ice and fire. Gliese 436b serves as an extraordinary example of how planetary conditions can lead to the development of unique and unexpected states of matter. Its characteristics not only challenge our ideas about planetary formation, but also highlight the breathtaking diversity of exoplanets scattered across the universe. Exploring the mechanisms that make this ice-fire world possible broadens our understanding of the extreme conditions that exist on planets beyond our solar system. By delving into the dynamics at play on Gliese 436b, scientists can gain deeper insights into the atmospheric processes and planetary characteristics that shape other worlds in distant star systems. This knowledge enriches our scientific discourse and offers captivating glimpses into the forces that govern the universe. In contrast, the exoplanet TRES-2b presents another extraordinary mystery. Often described as the darkest known exoplanet, it absorbs nearly all the light that strikes its surface, reflecting less than 1% of the incoming radiation. Located approximately 300 light-years from Earth, this gas giant orbits perilously close to its host star, exposing it to searing temperatures that can exceed 1,000 degrees Celsius. The combination of proximity to its star and the unique properties of its atmosphere contribute to its nearly impenetrable darkness. TRES-2b's atmosphere is believed to be composed of compounds like sodium and potassium, which help form a dense haze that contributes to its shadowy appearance. These elements, working together with other compounds, likely create clouds that not only absorb visible light, but also block much of the light that might otherwise reflect off the planet's surface. As a result, TRES-2b's surface appears closer to the blackness of charcoal than the reflective gas giants we are familiar with in our solar system. The extraordinary darkness of TRES-2b offers a natural laboratory for scientists studying the interaction of light with various materials under extreme conditions. By studying how light behaves in such an opaque atmosphere, researchers can enhance their understanding of exoplanetary atmospheres, particularly those with similar compositions and temperatures. TRES-2b's unique characteristics challenge conventional assumptions about how planetary bodies are classified based on their light absorption and reflection. The discovery of TRES-2b's extreme darkness forces scientists to rethink how they identify and categorize exoplanets. This, in turn, opens up new avenues for understanding how the physical properties of distant worlds can diverge from our expectations. By studying planets like TRES-2b, scientists not only expand their understanding of atmospheric chemistry, but also deepen their knowledge of the conditions that exist in the farthest reaches of the universe. Both Gliese 436b and TRES-2b exemplify the vast and varied nature of exoplanets, pushing the boundaries of our understanding and prompting us to reimagine the possibilities of planetary environments. These extraordinary worlds offer a glimpse into the incredible diversity of conditions that can arise far beyond the familiar landscapes of our own solar system. Through continued study, we inch ever closer to comprehending the full extent of the universe's hidden wonders. The atmosphere of HD 2009458b, commonly known as Osiris, is a captivating subject of study, especially when considering the dynamic and dramatic process of its atmospheric evaporation. Positioned close to its host star, Osiris completes an orbit in less than 4 Earth days. This extraordinary proximity subjects the planet to extreme temperatures, often soaring above 1,000 degrees Celsius. The intense heat wreaks havoc on its atmosphere, causing it to lose significant quantities of gas to the vast emptiness of space. A key factor driving this evaporation is the high-energy radiation emitted by the host star. As the radiation bathes Osiris, it bombards the planet's atmosphere with an intense flow of energy, enough to break apart particles in the upper layers. This phenomenon, known as thermal evaporation, is the result of the kinetic energy of atmospheric particles increasing to such a degree that they can no longer be held by the planet's gravitational pull. As a result, lighter elements like hydrogen and helium are more prone to escaping into space, forming a striking tail-like structure that stretches outward. Recent observational studies reveal just how dramatic this process is. Osiris is losing an estimated thousands of tons of atmospheric mass every second. However, this loss is far from constant. The rate and extent of evaporation fluctuate depending on the intensity of stellar radiation and the unique composition of the planet's atmosphere. Heavier molecules, such as water vapor and carbon monoxide, also play a role, though they evaporate at a slower rate. These complex dynamics contribute to the ever-changing nature of the planet's atmospheric behavior. The evaporation of Osiris's atmosphere offers invaluable insights into the atmospheric processes affecting exoplanets, especially those located in close proximity to their stars. By studying this process, scientists are gaining a deeper understanding of how planetary atmospheres evolve and how factors like stellar radiation influence the habitability of worlds under such extreme conditions. The dynamic processes observed on Osiris serve as a powerful reminder of the diverse and unpredictable nature of exoplanets in the cosmos, each contributing a unique chapter to the ongoing story of our universe. Beyond individual exoplanets, the cosmos itself is an intricate web of interconnected structures. Galactic filaments, immense thread-like structures that stretch across the universe, form a crucial part of this larger cosmic tapestry. These filaments, composed of galaxies, dark matter, and gas, are the fundamental building blocks of the universe's large-scale structure, often referred to as the cosmic web. The cosmic web is a vast, interconnected network of galactic filaments with galaxies strung along their lengths, separated by vast voids. These filaments were formed over billions of years through the gravitational clumping of matter. As the universe expanded from the Big Bang, minute fluctuations in density allowed gravity to pull dark matter and gas together, forming the long, thin structures we observe today. Galaxies and clusters of galaxies aligned along these filaments serve as cosmic highways, guiding the flow of matter and energy across the universe while shaping its large-scale architecture. Galactic filaments do more than connect galaxy clusters. They are also pivotal sites for star formation. In the dense regions of these filaments, gas can cool and condense, triggering the birth of new stars. This ongoing process of star formation within the filaments highlights their importance in the life cycle of galaxies and the larger evolution of cosmic structures. The study of galactic filaments offers astronomers a deeper understanding of the universe's formation, helping to unlock the mysteries of galaxy development and the larger forces that shape the cosmos. Integral to this grand cosmic evolution are supermassive black holes. These behemoths, typically located at the centers of large galaxies, play a decisive role in the development and behavior of galaxies. With masses millions, even billions, of times that of our Sun, these black holes exert an overwhelming gravitational pull on their surroundings. This influence dramatically alters the dynamics of the galaxy, shaping the movement of stars and gas while impacting the galaxy's overall evolution over vast cosmic timescales. Supermassive black holes are not merely passive objects at the heart of galaxies. Their growth and behavior have profound implications for the formation of stars, the distribution of matter, and even the overall structure of galaxies. By studying these cosmic giants, astronomers continue to peel back the layers of galaxy formation, revealing the deep connections between gravity, matter, and time in the universe's most distant reaches. Through this ongoing exploration, we inch ever closer to understanding the intricate workings of the cosmos itself, from the smallest exoplanets to the largest galactic structures. Supermassive black holes, those mysterious giants at the hearts of galaxies, play a profound and multifaceted role in shaping the evolution of the cosmos. Their influence extends far beyond their gravitational pull, acting as cosmic engines that regulate the very birth and death of stars within their host galaxies. As matter spirals toward these colossal black holes, it forms a dense, spinning disk of material known as an accretion disk. This disk, heated to unimaginably high temperatures, emits vast amounts of energy, particularly in the form of X-rays and powerful jets of high-energy particles. This energetic outburst, known as active galactic nucleus (AGN) activity, doesn't just light up the galaxy, it has the power to influence the very processes that govern star formation. The energy released by these black holes can either inhibit or accelerate star birth, depending on the circumstances. The tremendous energy emitted by these black holes can heat up or even expel surrounding gas, preventing it from collapsing and forming new stars. In some cases, this feedback mechanism suppresses star formation, creating a stark contrast to the usual patterns of galactic evolution. In other instances, however, the intense energy may trigger bursts of star formation, feeding the galaxy's growth in an entirely different way. Therefore, supermassive black holes don't just coexist with their host galaxies. They help determine whether the galaxy flourishes with new stars or stagnates in an energy-fueled cosmic equilibrium. But their influence doesn't stop there. Supermassive black holes also shape the very structure of galaxies themselves. The immense gravitational forces they exert are essential in maintaining the overall balance of a galaxy's shape, particularly in spiral galaxies. The black hole's gravity can help stabilize the spiral arms of the galaxy, ensuring that the familiar, graceful curves we associate with these galaxies persist over time. As the black hole grows in mass, often through the consumption of surrounding stars and gas, its grip on the galaxy tightens, influencing the distribution and motion of stars across the galactic plane. The story of these black holes doesn't just end with their interaction with the galaxy's existing structure. As galaxies evolve and merge, so too do the black holes that lie at their centers. When galaxies collide, often triggered by their mutual gravitational attraction, they bring their supermassive black holes together in a dramatic cosmic dance. This process, unfolding over billions of years, can lead to an immense release of energy, transforming the newly merged galaxy. The resulting active galactic nucleus activity can intensify, creating a more chaotic and energetic environment that impacts the galaxy's growth and structure. Such mergers, though violent, play a crucial role in shaping the final form of galaxies. When the nuclei of two merging galaxies combine, they often create a single, more massive, supermassive black hole. This new central black hole becomes the focal point for the merged galaxy, which may now take on a new shape, often transitioning from a spiral form to an elliptical one. These galactic mergers don't just reshape individual galaxies, they have far-reaching consequences for their surroundings, affecting the gravitational dynamics of nearby galaxies and clusters. Moreover, these galactic collisions stir the cosmic pot, setting off starbursts, intense periods of accelerated star formation. As gas clouds are compressed during the merger, new stars are born at a frantic pace, filling the galaxy with a youthful, vibrant glow. Yet, this rapid star formation is but one aspect of the merger process. Over time, the galaxies settle into a new equilibrium with their new supermassive black holes at the heart of a changed and evolving galactic system. In the broader context of cosmic evolution, these galactic mergers and the forces at play within them are critical to understanding the grand narrative of the universe. They are the engines of galactic growth, the crucibles where new stars, black holes, and cosmic structures are born. The study of these events gives astronomers invaluable insight into the complex processes of galaxy formation, star birth, and the intricate relationships between gravity, dark matter, and the evolution of the cosmos. Indeed, as galaxies collide and merge, they do more than just reshape the stars within them. They challenge our very understanding of the universe itself, offering a glimpse into the forces that drive cosmic change and the vast interconnected web of galaxies that make up the universe. The formation of stars and the evolution of supermassive black holes are key processes that significantly enrich our understanding of the universe's structure and history. One of the most fascinating phenomena in this realm is the formation of galactic bars in spiral galaxies, a topic that has intrigued astrophysicists for years. Over time, various theories have emerged, each seeking to explain the genesis of this striking structural feature that appears as a prominent elongated bar stretching across the heart of many spiral galaxies. At the heart of one prominent theory lies the idea of gravitational instabilities within the galactic disk. In most spiral galaxies, the distribution of stars, gas, and dark matter is far from uniform. Instead, these components create regions of varying density. When the density in a particular region reaches a critical threshold, gravitational instabilities can arise. These disturbances cause the formation of a bar-like structure that cuts through the center of the galaxy, reshaping the dynamics of the system. This elongated feature facilitates a redistribution of matter, allowing gas to funnel towards the galaxy's nucleus and affecting the overall flow of energy and material within the galactic system. Another crucial factor in the formation of galactic bars involves the gravitational interaction between various components of the galaxy, particularly the stars in the disk and the supermassive black hole at the center. As stars orbit the galactic core, their motions are not entirely random. Over time, the gravitational influence of the supermassive black hole and the gravitational interactions between stars in the disk can align these stellar orbits, creating a coherent bar-like structure. These interactions, occurring over millions or even billions of years, allow the bar to become more stable, with its shape becoming more pronounced as time progresses. This stability, in turn, affects the dynamics of other stars in the galaxy, further contributing to the overall evolution of the system. Interestingly, bars can also form as a result of external influences. Galaxies are rarely isolated in the vastness of space. Instead, they often interact or merge with other galaxies. When these interactions occur, the gravitational forces exerted by nearby galaxies can induce the formation of a bar structure in the disk of a spiral galaxy. These external forces can cause gas and stars to become more ordered, effectively triggering the onset of bar formation. These kinds of interactions underscore the dynamic nature of galaxies and emphasize how environmental factors, such as the gravitational pull from nearby systems, can shape the very structure of a galaxy. The theories surrounding the formation and persistence of galactic bars are far from settled. They remain an active area of research, with ongoing studies utilizing computer simulations and observational data to build a more comprehensive understanding of these complex structures. Bars are more than just curious cosmic features. They play a pivotal role in regulating several key galactic processes. For example, galactic bars are known to influence star formation within galaxies by controlling the flow of gas, which in turn can affect the rate and pattern of star birth. Additionally, the presence of a bar can significantly alter the dynamics of the galaxy's evolution, possibly even contributing to the eventual fate of the galaxy itself. The study of galactic bars also intersects with another crucial area of astrophysical research, the role of galactic magnetic fields. These invisible fields, though often overlooked, are fundamental in shaping both the formation of stars and the architecture of galaxies. Magnetic fields exert pressure on the charged particles within the interstellar medium, a vast, largely unexplored region filled with gas and dust. This pressure can have a profound impact on the formation of new stars. As stars form from collapsing clouds of gas, magnetic fields can either facilitate or hinder this process. When a massive cloud begins to collapse under its own gravity, the magnetic field lines surrounding it can provide additional pressure that counters the gravitational pull, helping to stabilize the cloud. This can lead to a more organized, gradual formation of stars, where dense clusters are created in a structured manner. However, if the magnetic field is weak or poorly oriented, it may not offer enough support, leading to a more chaotic collapse and a less efficient star formation process. Thus, the strength and orientation of magnetic fields within a galaxy can have profound effects on the rate of star formation and the overall evolution of the galaxy. Together, the interplay between gravitational forces, magnetic fields, and galactic interactions helps to shape the architecture and evolution of galaxies, ultimately enriching our understanding of the universe's grand design. The continuing research into these complex processes will no doubt reveal even more about the intricate dynamics of the cosmos and the forces that govern its evolution. Magnetic fields, though often invisible to the naked eye, play a fundamental role in shaping the dynamics of galaxies. These fields are not merely passive structures but active guides, steering the flow of ionized gases within a galaxy. By acting as invisible forces, magnetic fields shape the very spirals that define many galaxies, channeling the movement of gas and creating intricate patterns that affect the growth and evolution of galaxies. It's within these flows of gas that new stars and planets are born. The interaction between gas dynamics and magnetic fields isn't just a minor detail, it's the very engine of star formation. Magnetic fields help organize and direct the motion of gas, leading to the creation of stellar nurseries, the birthplaces of new stars. Recent discoveries have illuminated the profound influence of these magnetic fields. They extend far beyond simply guiding gas. They play a key role in the behavior of cosmic rays, a form of high-energy radiation that permeates the universe, and in heating the gas within galaxies. This connection between magnetic fields and cosmic processes suggests that these fields do more than influence current star formation. They could also shape the long-term evolution of galaxies and even affect the distribution of stellar populations across the universe. Understanding how these magnetic forces function is critical if we are to decode the intricate tapestry of cosmic evolution. But magnetic fields are just one part of the galactic story. Galactic winds, powerful outflows of gas driven by the intense energetic processes occurring within a galaxy, are another. These winds are not random events. They are the result of phenomena like supernovae, active star formation, and the ferocious activity of supermassive black holes at the hearts of galaxies. As massive stars exhaust their fuel and reach the end of their life cycles, they explode in violent supernova, releasing vast amounts of energy. This energy can blow surrounding gas out of the galaxy, propelling it into space at high velocities. These winds, escaping the gravitational grip of the galaxy, have far-reaching consequences. One of the most profound impacts of galactic winds is their ability to enrich the intergalactic medium, the vast expanse of space between galaxies, with elements forged in the hearts of stars. As gas is expelled from a galaxy, it carries with it a mix of primordial elements, hydrogen and helium, along with heavier elements such as carbon, oxygen, and iron, produced through the process of nuclear fusion. This not only alters the chemistry of the intergalactic medium, but also influences the birth of future stars and galaxies. Galactic winds, in essence, act as a form of cosmic recycling, returning material into the larger universe, shaping the formation and structure of galaxies for eons to come. But the story doesn't end there. Galactic winds have another key role. They regulate the rate of star formation within galaxies. If these winds are powerful enough, they can blow away the gas required for new star formation, effectively halting it. In other cases, the shock waves generated by these winds compress nearby gas clouds, triggering the formation of new stars. Thus, these winds act as both destroyers and creators, depending on the conditions at hand. This delicate balance between gas expulsion and compression plays a significant role in the evolution of galaxies over time. Moreover, galactic winds don't exist in isolation. They are part of the greater cosmic web, a vast network of interconnected galaxies and dark matter. As winds travel through the intergalactic medium, they don't just affect their local environments, they compress and heat the surrounding gas, contributing to the thermal and magnetic structure of the universe. This interconnectivity between galaxies, their winds, and the broader cosmos highlights their vital role in the overarching narrative of cosmic evolution. Galaxies are not isolated systems. They are part of a much larger, interconnected cosmic ecosystem. On an even grander scale, galaxy clusters, some of the largest gravitationally bound structures in the universe, form over billions of years through a process of gravitational attraction. In the early universe, small density fluctuations provided the seeds for this cosmic growth. These fluctuations allowed matter to accumulate, eventually forming protoclusters, dense regions of gas and dark matter where galaxies begin to merge and form. As gravity pulls more and more matter into these protoclusters, they evolve, growing in mass and complexity. Galaxies within these clusters interact and merge, creating new stellar populations and increasing the overall mass of the cluster. The process of hierarchical clustering drives the evolution of these clusters. Smaller clusters and groups of galaxies collide and merge, forming larger and more massive structures. As galaxies interact, they may experience significant cooling of the gas between them, leading to the emission of X-rays, signaling the presence of extremely hot gas. These X-rays are more than just a light show. They provide essential information about the properties and mass of the cluster. Over cosmic time, galaxy clusters can also affect their environments in profound ways. Their immense gravitational fields can trap hot gas, preventing it from escaping, and thereby contribute to further galaxy formation, creating a cycle of cosmic growth. In summary, from magnetic fields to galactic winds to the formation of galaxy clusters, the forces at play in our universe are interconnected in a dance of creation and destruction. These processes shape not only the galaxies we observe, but also the very fabric of the cosmos itself. By understanding these dynamic systems, we can better appreciate the vast and ever-evolving story of the universe, a story that spans billions of years and continues to unfold before our eyes. The presence of a galaxy cluster can significantly influence the motion and distribution of dark matter in its surroundings. Understanding how these clusters form and evolve allows astronomers to piece together the intricate history of the universe, offering invaluable insights into the interactions between dark matter, normal matter, and cosmic expansion. Dark matter, while invisible, plays a crucial role in shaping the structures of both galaxies and the universe as a whole. Although dark matter cannot be directly observed, its existence is inferred from its gravitational effects on visible matter, such as stars and gas. First theorized in the early 20th century due to discrepancies in galaxy rotation speeds, dark matter has since become a cornerstone of our understanding of cosmic structure. The gravitational influence of dark matter stretches far beyond the visible components of galaxies, forming a vast, unseen halo around them. This halo provides the necessary gravitational pull to keep together the stars and gas that make up a galaxy's visible structure. This dark matter halo not only explains the unusually high rotation speeds of galaxies, but also plays a critical role in the formation and evolution of galaxies themselves. As gas within galaxies cools and collapses under gravity to form stars, dark matter halos create gravitational wells that attract this material, guiding it into denser clumps. The distribution of dark matter within a galaxy significantly influences its overall shape and behavior. For example, in spiral galaxies, dark matter is distributed in a roughly spherical halo that extends far beyond the visible boundaries of the galaxy. This distribution directly impacts the galaxy's angular momentum and stability, which in turn affects the formation of spiral arms and the dynamic interactions among its various components. In contrast, elliptical galaxies exhibit a more homogeneous and smooth structure, largely due to the unique role dark matter plays in their formation. But the influence of dark matter extends far beyond individual galaxies. On a larger scale, dark matter plays a pivotal role in the clustering of galaxies. It is instrumental in the formation of galaxy groups and clusters through gravitational interactions, ultimately giving rise to the vast, web-like structure of the universe known as the cosmic web. This web is a direct consequence of dark matter's gravitational influence, which binds galaxies together and drives their development over billions of years. Quasars, short for quasi-stellar objects, are extraordinarily bright and energetic phenomena found at the centers of some galaxies. These objects are powered by supermassive black holes that have accreted vast amounts of gas and dust. The formation of a quasar typically begins with the collapse of material into a supermassive black hole at the heart of a galaxy. As matter spirals inward, it forms an accretion disk, heating up to extreme temperatures due to friction and intense gravitational forces. This heat causes the disk to emit immense amounts of energy, radiating across the electromagnetic spectrum. The relationship between quasars and galactic evolution is profound. Quasars often mark an active phase in the life of a galaxy, particularly during periods of significant growth and transformation. In the early universe, many galaxies underwent intense bursts of star formation and activity. During these periods, the feeding of the supermassive black hole can result in the quasar shining brighter than all the stars in its host galaxy combined. This intense luminosity allows quasars to be visible from vast distances, offering astronomers a unique opportunity to study the properties of distant galaxies and the conditions that prevailed in the early universe. In essence, the study of dark matter and quasars provides a critical lens through which we can observe the universe's most fundamental processes. These phenomena offer clues not only about the nature of the cosmos today, but also about the forces and events that shaped it over the vast span of cosmic time. Quasars, some of the most energetic and distant objects in the universe, are not only fascinating for their extreme brightness, but also for the profound role they play in shaping the galaxies that host them. When we delve into the dynamics of quasars, we uncover a fascinating mechanism of cosmic feedback. The energy released by these enormous black holes can dramatically influence the evolution of their host galaxies. Powerful jets of material, shot out from the black hole at near light speed, interact with the surrounding gas. This high-energy interaction heats the gas, preventing it from cooling and condensing into new stars. This feedback process acts as a cosmic regulator, controlling the rate of star formation within the galaxy. It can even determine the future development of the entire galaxy. As the quasar eventually exhausts its fuel, the black hole shifts into a quieter phase, and the galaxy transitions into a more stable state. Observations suggest that many of the massive galaxies we observe today likely experienced an active quasar phase during their past. This implies that by studying quasars, we gain not only valuable insights into the nature of black holes, but also the processes that drive galaxy formation and evolution in the broader cosmos. Quasars thus serve as a vital window into understanding the interplay between these colossal black holes and the galaxies they reside in, revealing a crucial chapter in the ongoing story of the universe. Another captivating aspect of galactic evolution lies in the formation of elliptical galaxies. These galaxies, with their smooth spherical shapes, have long been a subject of interest within astronomical research. Several theories attempt to explain how they come into being, but one of the most prominent ideas is that elliptical galaxies form primarily through the merging of smaller galaxies. When two or more spiral or dwarf galaxies collide and merge, their gravitational interactions lead to the redistribution of stars and gas. This process often results in a more rounded, spheroidal structure that defines elliptical galaxies. Such mergers are more likely to occur in dense environments like galaxy clusters, where encounters between galaxies are frequent. An essential concept in the formation of elliptical galaxies is the process of gravitational relaxation. As galaxies merge, their stars interact gravitationally, leading to a randomization of their orbits over time. This randomization smooths out the original disk-like structure of the galaxies, converting it into a more isotropic, uniform in all directions distribution of stars. In other words, the stars no longer follow a preferred direction of motion. Instead, they occupy a wide range of orbits across the entire galaxy. This relaxation process helps produce the elliptical shape as it erases the ordered structure of the galaxy's earlier stages. Additionally, the monolithic collapse model offers another explanation for the formation of elliptical galaxies. According to this theory, a large cloud of gas and dust collapses under its own gravity, forming a massive protostar. As the core collapses, stars form rapidly in a burst of activity. This results in a compact system with little to no new star formation after the initial burst. The rapid star formation during this process often produces older, red stars, which lend early elliptical galaxies their characteristic color. In this model, the exhaustion of available gas during the intense star formation phase leaves the galaxy with minimal or no further star formation, giving rise to a more stable, mature structure. These theories, whether through galaxy mergers, gravitational relaxation, or rapid stellar formation, highlight the complexity of elliptical galaxy formation. They offer crucial insights into how galaxies evolve over cosmic timescales, helping us understand the intricate processes that have shaped the universe as we see it today. Studies have increasingly highlighted the crucial role that the current environment of elliptical galaxies plays in their ongoing evolution. These galaxies are not passive entities, they are active, constantly evolving by accumulating gas from their surroundings or merging with smaller galaxies. This continual growth profoundly influences their brightness, size, and stellar populations, adding layers of complexity to our understanding of their development. These theories provide a framework to grasp the intricate processes behind elliptical galaxy formation. Yet the dynamic interplay of interactions, gas dynamics, and gravitational influences remains an area of active exploration. The complexities of these factors continue to challenge astronomers and physicists alike as they unravel the mysteries of galaxy formation. One of the most captivating phenomena in the cosmos is the gravitational anomaly known as the Great Attractor. Situated within the vicinity of the Virgo cluster, this massive concentration of mass is pulling galaxies, including our own Milky Way, toward it at astonishing speeds. For many years, the exact nature of the Great Attractor was shrouded in mystery, partly because its location is obscured by the dense gas and dust of the Milky Way's plane. This obstruction made it difficult for astronomers to observe it directly. The Great Attractor is thought to be tied to the Laniakea supercluster, a massive galactic structure that encompasses the Perseus-Pisces supercluster and other significant galactic systems. At its core, this region harbors an immense invisible mass, much of which is believed to be dark matter. Dark matter, interacting gravitationally with visible matter, generates a force that affects the motion of galaxies over vast distances. Estimates suggest that the Great Attractor's mass could be equivalent to millions of times the mass of our Sun, explaining its immense gravitational influence. Our own local group, which includes the Milky Way and the Andromeda Galaxy, is currently moving toward the Great Attractor at nearly 700 kilometers per second. This motion is part of a larger cosmic flow, suggesting that regions like the Great Attractor have played a pivotal role in shaping the distribution and formation of galaxies across the universe. Understanding this enigmatic region is key to deciphering the large-scale structure of the cosmos. It offers valuable insights into the dynamics of galaxy motion and interaction within the vast cosmic web. As astronomers continue to investigate this mysterious area, they seek to piece together the interconnected forces that have shaped the universe and its myriad galaxies. The existence of supermassive black holes in the early universe has opened new avenues of inquiry about their formation and evolution. Observations have shown that these colossal black holes were already in place just a few 100 million years after the Big Bang, raising intriguing questions about how they could have emerged so rapidly. One prominent hypothesis involves the direct collapse of massive clouds of gas and dark matter in the early universe. Unlike the typical process in which stellar black holes form from the collapse of individual massive stars, these direct collapse black holes could have formed seeds of thousands of solar masses. These massive seeds would have had the potential to grow quickly through accretion and mergers with other black holes. Alternatively, supermassive black holes could have emerged from the population of smaller black holes formed in the early stages of star formation. These stars were likely more massive than those that form today and exploded as supernovae, leaving behind black holes. Over time, these smaller black holes could have merged, accumulating mass and eventually growing into supermassive black holes. Their growth would have been particularly accelerated in dense environments, such as the centers of early galaxies, where gas was abundant. The environment in which these early black holes formed played a crucial role. Gas, left over from the Big Bang, filled these dense regions, offering an ideal fuel source for rapid accretion. The interaction between dark matter and regular matter in these regions also contributed to the gravitational clumping necessary for the birth of these giant entities. Today, the detection of supermassive black holes in the early universe is a rapidly expanding field of study, offering new insights into galaxy formation and evolution. Understanding the origins of these black holes can shed light on the intricate relationship between galaxies and their central supermassive black holes, which ultimately influences the broader narrative of cosmic evolution. As we investigate the origins of the universe, the role of dark energy becomes an unavoidable topic. This mysterious force makes up roughly 70% of the total energy density of the cosmos, yet its nature remains one of the most profound enigmas in modern astrophysics. Its discovery has transformed our understanding of the universe, yet its true nature continues to elude even the most advanced theories. How this dark energy fits into the grand structure of the universe and how it influences cosmic evolution is a question that challenges the brightest minds in science today. In examining these cosmic forces, from elliptical galaxies to the Great Attractor, from supermassive black holes to the elusive dark energy, we are peeling back the layers of the universe's vast history. These phenomena are interconnected in ways that we are only beginning to understand, and each discovery brings us closer to answering the questions that have fascinated humanity for millennia. The universe is far from static. It is in constant motion, evolving in ways we are still uncovering, one revelation at a time. Dark energy is thought to be responsible for the observed accelerated expansion of the universe, a phenomenon that first caught the attention of astronomers in the late 1990s. It all began when scientists noticed something puzzling. Distant supernovae appeared fainter than expected. This observation suggested that these stars were much farther away than previously believed, leading to the startling realization that the universe was expanding at an accelerating rate. The leading explanation for this mysterious force is based on the concept of the cosmological constant, a term introduced by Albert Einstein in his equations of general relativity. In this framework, dark energy is considered a repulsive force, counteracting the attractive pull of gravity. This repulsion results in a consistent energy density that fills space uniformly. The negative pressure exerted by dark energy pushes galaxies further apart over vast cosmic distances, driving the expansion of the universe at an increasingly rapid pace. As the universe expands, dark energy becomes more dominant in influencing its evolution, outpacing the gravitational attraction of matter. However, an alternative hypothesis suggests that dark energy might not be a constant force after all. Known as quintessence, this idea posits that dark energy could vary over both time and space. Unlike the cosmological constant, which maintains a fixed energy density, quintessence involves a scalar field that evolves over time. This evolution could have profound effects on cosmic expansion, potentially altering the rate at which the universe is expanding. Current observational data offers strong evidence supporting the presence of dark energy. The accelerating expansion of the universe is seen in a variety of ways, from the cosmic microwave background radiation to the formation of large-scale structures and the behavior of distant supernovae. Understanding dark energy is crucial, as it is a dominant force shaping the ultimate fate of the cosmos. As research into dark energy continues, astrophysicists are working diligently to unravel its complexities and gain a clearer understanding of how this enigmatic force impacts the evolution of the universe. Fast radio bursts, or FRBs, are another cosmic mystery that has captured the attention of astronomers. These are intense bursts of radio waves that last only a few milliseconds, but release an astonishing amount of energy, often comparable to the total energy emitted by the sun over an entire day. Despite their brevity, FRBs present a unique opportunity to probe the farthest reaches of the universe. The exact origin of these bursts remains largely unknown, though several hypotheses have been proposed. One leading theory suggests that FRBs may be linked to neutron stars, particularly a type known as magnetars, which possess exceptionally strong magnetic fields. When these stars undergo violent events such as starquakes or magnetic reconnection, they may emit powerful bursts of energy that manifest as radio waves. Another possibility is that FRBs could be generated by the collapse of massive stars into black holes, or even by interactions in binary star systems or stellar collisions. What makes FRBs especially valuable to scientists is their ability to provide insights into the structure of the universe. As these bursts travel across vast distances, they pass through the intergalactic medium, a region of space filled with low-density gas and free electrons. By studying the dispersion measure of an FRB, essentially the number of free electrons along the path of the signal, astronomers can learn about the density of matter in the universe and the distribution of matter in the intergalactic medium. This information is crucial for advancing our understanding of cosmic evolution. Further intrigue arises from the repeated detection of certain FRBs, such as the famous FRB 121102. The ability to observe these bursts multiple times from the same source offers an unprecedented opportunity to study the environment around the burst and the conditions under which it was generated. As astronomers continue their quest to uncover the origins of these mysterious bursts, they hope not only to answer fundamental questions about their formation, but also to use them as tools for investigating the larger structure and dynamics of the universe. Finally, the observed flatness of the universe presents yet another profound mystery. On large scales, the universe appears to have a flat Euclidean geometry, meaning that the familiar rules of geometry, such as the sum of angles in a triangle equaling 180 degrees, hold true across vast distances. This flatness has significant implications for cosmology and our understanding of the universe's fate. It suggests that the total energy density of the universe is very close to a critical value, where the universe neither collapses upon itself nor expands infinitely. This realization has prompted further investigation into the ultimate trajectory of the universe, raising questions about the possible future of cosmic expansion, the nature of dark energy, and the eventual fate of all that exists. As these cosmic puzzles continue to unfold, researchers strive to better understand the forces that shape the universe. With each new discovery, we come closer to unraveling the mysteries of dark energy, fast radio bursts, and the flatness of the universe, bringing us one step closer to comprehending the grand design of the cosmos itself. One of the central ideas explaining the universe's flatness is the inflationary model, a theory that proposes the universe underwent an extraordinary expansion in its earliest moments. Just after the Big Bang, during a brief but intense period known as cosmic inflation, the universe expanded at an exponential rate. This rapid expansion smoothed out any initial irregularities and fluctuations, stretching space to such an extent that any curvature of the universe was effectively flattened. The result? A geometry that on large scales appears almost perfectly flat. Another crucial factor in understanding the flatness of the universe is the overall energy density, which comes from different components: matter, radiation, and dark energy. Observations suggest that the universe's total energy density is remarkably close to the critical density, the exact threshold where the universe would be geometrically flat. If the universe's density were higher than this critical value, it would be closed, curving inward like a sphere. On the other hand, if the density were lower, it would be open with a hyperbolic geometry. Current measurements of the cosmic microwave background radiation and the large-scale structure of the universe show that its density is balanced very close to this critical value, reinforcing the idea that the universe is indeed flat. Furthermore, the role of dark energy, which currently dominates the universe's energy budget, cannot be overlooked. As the universe expands, dark energy accelerates this expansion, influencing the long-term geometry of space itself. This interaction between matter, dark energy, and cosmic structure shapes the universe's evolution. Understanding this delicate balance of forces is key not only to explaining the universe's current flatness, but also to predicting its future trajectory. As we dive deeper into the universe's structure, we encounter the concept of cosmic voids, vast, largely empty regions of space that contain far fewer galaxies and much less matter than the average cosmic density. These voids can stretch tens of millions to more than 100 million light-years across and are among the most fascinating features of the universe's large-scale architecture. They are nestled between denser regions filled with galaxies, known as galaxy clusters and superclusters, creating a web-like pattern referred to as the cosmic web. The formation of these voids can be traced back to the early universe. Small fluctuations in the density of matter during the universe's infancy led to areas where matter began to clump together, eventually forming clusters of galaxies and gas. Gravity then drew matter into these denser regions while leaving gaps of empty space between them, allowing the voids to take shape. Over time, as the universe continued to evolve, these voids grew larger and more defined, giving us the cosmic structure we observe today. Cosmic voids are not just large, empty spaces. They play an important role in the evolution of galaxies and large-scale cosmic dynamics. Their low density alters gravitational interactions, affecting how galaxies form, behave, and evolve. Voids influence the movement of galaxies within denser regions, potentially impacting the distribution of galaxies and the growth of large-scale structures over time. Together, these insights into the flatness of the universe and the formation of cosmic voids provide us with a deeper understanding of the forces shaping the cosmos. From the rapid expansion of space during inflation to the delicate balance of matter and dark energy, each piece of the puzzle helps illuminate the complex evolution of the universe. Understanding these factors isn't just key to cosmology, it's crucial for making predictions about the universe's fate and how it will continue to evolve in the distant future. Moreover, studying cosmic voids offers invaluable insights into some of the most elusive phenomena in the universe, namely dark matter and dark energy. As researchers analyze the distribution, size, and characteristics of these massive empty regions, they can infer the subtle gravitational effects of dark matter that shape the entire cosmic web. By examining these voids, scientists can also uncover clues about the properties of dark energy, a mysterious force responsible for accelerating the expansion of the universe. The way cosmic voids grow and evolve, influenced by the expansion of the universe, reveals much about the underlying forces that drive both the emptiness of voids and the dense clumps of matter that form galaxies and clusters. This makes cosmic voids an incredibly fascinating and significant area of research in cosmology, as they offer a deeper understanding of the universe's large-scale structure, its evolution, and the fundamental forces that govern its behavior. Equally captivating is the cosmic microwave background, CMB, the faint glow of radiation that permeates the universe, carrying with it a history of the universe's earliest moments. Referred to as the afterglow of the Big Bang, this radiation is primarily in the microwave portion of the electromagnetic spectrum and has a temperature of approximately 2.7 degrees above absolute zero. The CMB is one of the most powerful tools astronomers have for understanding the universe's infancy. It offers a snapshot of the cosmos when it was just 378,000 years old, and an incredibly young age, considering the universe itself is nearly 14 billion years old. The significance of the CMB lies in its role as a cosmic fossil, preserving information about the universe when it was cooling and evolving rapidly. As the universe expanded and cooled, protons and electrons combined to form neutral hydrogen, allowing photons to travel freely for the first time without constantly scattering. This event, known as recombination, marks the release of the CMB radiation. The light we observe today is a direct reflection of the density fluctuations of matter and energy present in the universe at that time. These fluctuations are believed to have laid the groundwork for all the structures we observe in the universe today, such as galaxies, galaxy clusters, and the vast cosmic voids themselves. Incredibly detailed measurements of the CMB, made possible by satellites like the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite, have revealed minuscule temperature variations, anisotropies, that correspond to areas of differing density. By analyzing these fluctuations, scientists can uncover critical information about the early universe, including the proportions of ordinary matter, and dark energy. These observations have strongly supported the inflationary model of the universe, which posits a rapid expansion in the very first moments after the Big Bang. The CMB not only offers a glimpse into the birth of the cosmos, but also serves as a compact record of the universe's journey from a hot, dense state to its present expansive form. Through the study of the CMB, astronomers have refined their models of cosmic evolution, gaining a more precise understanding of fundamental cosmological parameters, such as the Hubble constant, the age of the universe, and the overall geometry of space. In this way, the cosmic microwave background is a cornerstone of modern cosmology, offering essential clues about the origins, structure, and ultimate fate of the universe. In addition to the study of voids in the CMB, another enigma of the cosmos lies in the matter-antimatter asymmetry observed throughout the universe. According to the standard model of particle physics, the Big Bang should have produced equal amounts of matter and antimatter. However, the observable universe contains a striking excess of matter over antimatter, with very little antimatter detectable in the cosmos today. This discrepancy remains one of the greatest unsolved puzzles in cosmology and particle physics, fueling ongoing research into the fundamental nature of matter, the laws of physics, and the mysteries that remain hidden in the vast expanse of space. However, the universe we observe today is predominantly made up of ordinary matter, with very little antimatter in sight. This significant discrepancy has prompted deep, foundational questions regarding the laws of physics and the events that unfolded in the universe's early stages. The mystery of why we see more matter than antimatter is one of the most perplexing problems in cosmology, and various theories have been proposed to explain this asymmetry. One such theory involves a process known as baryogenesis. Baryogenesis refers to the set of processes that could have created an imbalance between baryons, particles like protons and neutrons, and their antimatter counterparts, the antibaryons. For such an imbalance to arise, certain conditions must have been met in the early universe, as outlined by the Sakharov conditions. These conditions include the violation of baryon number conservation, the violation of charge C and charge parity CP symmetry, and non-equilibrium conditions that would have favored the creation of more matter than antimatter. A well-studied candidate for baryogenesis is the electroweak phase transition, which would have occurred at extremely high temperatures shortly after the Big Bang. During this phase transition, the dynamics of particle interactions might have allowed for CP violation, providing the necessary imbalance for the production of more matter than antimatter. Other theories focus on the decay of heavy particles, such as certain supersymmetric particles, which could provide the mechanisms needed to produce an excess of baryons. Alongside these theoretical models, researchers are also investigating experimental approaches to shed light on this cosmic mystery. One area of study involves neutrinos, subatomic particles that may hold the key to discovering additional sources of CP violation. By studying neutrino interactions, scientists hope to uncover further clues that could help explain the asymmetry between matter and antimatter. Furthermore, precision measurements of particle interactions at high-energy particle accelerators are yielding critical insights into fundamental symmetries, potentially uncovering new physics beyond the standard model. Despite the many hypotheses, the matter-antimatter asymmetry remains one of the most profound puzzles in both cosmology and physics. As researchers continue to test and refine their theories, the hope is to eventually unlock this mystery, thereby enhancing our understanding of the fundamental forces and events that shaped the universe. In addition to these fundamental questions about matter and antimatter, another groundbreaking phenomenon is the study of gravitational waves, ripples in the fabric of spacetime that are produced by the acceleration of massive objects. These waves, first predicted by Albert Einstein in his general theory of relativity, travel outward from their source at the speed of light. They are generated when incredibly dense bodies, such as neutron stars or black holes, merge or collide, causing distortions in spacetime that stretch and compress distances between objects in their vicinity. The detection of gravitational waves is made possible by highly sensitive observatories like the Laser Interferometer Gravitational Wave Observatory, LIGO, and more recently, the Virgo collaboration. These instruments measure minuscule fluctuations in distance caused by the passing of gravitational waves, which are smaller than even a fraction of the diameter of a proton. The first direct detection of gravitational waves in 2015 was a monumental event that not only confirmed Einstein's century-old prediction, but also opened up an entirely new era of observational astronomy. Gravitational waves provide a unique window into the universe, offering insights into cosmic events that are otherwise invisible to traditional telescopes. For instance, they enable the study of black hole mergers and neutron star collisions, spectacular astrophysical events often hidden from electromagnetic observations. By analyzing the frequency and amplitude of these waves, scientists can extract vital information about the merging bodies, such as their masses, spins, and even their distances from Earth. This new form of cosmic observation promises to revolutionize our understanding of the universe, shedding light on the most extreme and enigmatic phenomena in space. Gravitational wave astronomy stands at the forefront of an extraordinary revolution in our understanding of the universe. With its unparalleled ability to reveal hidden dimensions of space and time, it opens new doors to phenomena that were once entirely beyond our reach. Through the detection of these ripples in space-time, we gain access to the formation and evolution of compact astrophysical objects, the enigmatic behavior of neutron stars, and the extraordinary conditions under which matter behaves under extreme forces. When combined with electromagnetic observations, such as gamma rays and X-rays emanating from the same cosmic events, gravitational waves provide a much richer, more nuanced picture of the universe's most energetic processes. This synergistic approach allows scientists to probe celestial occurrences with unprecedented depth and clarity, adding layers of insight into the dynamic forces that shape the cosmos. Indeed, gravitational waves are not just an advancement in technology. They confirm decades of theoretical predictions, while also carving a path into uncharted territories of astrophysics. The study of these waves has the potential to illuminate profound mysteries about the very fabric of the universe, offering a new lens through which we can explore cosmic phenomena. As gravitational wave astronomy continues to evolve, it promises to answer age-old questions and uncover new ones, guiding our understanding of the laws that govern everything from the smallest particles to the largest galactic structures. At the heart of our universe lies the cosmic web, a vast, intricate network that connects galaxies, clusters of galaxies, and dark matter across unimaginable distances. This cosmic structure, shaped by the gravitational pull that governs matter's behavior over billions of years, is far from a random assortment. Instead, it reflects the deep, underlying forces that emerged just after the Big Bang, where tiny density fluctuations laid the groundwork for the formation of the universe as we know it. These filaments of galaxies stretch across the cosmos like enormous strands of cosmic silk, connecting massive clusters that serve as the hubs of activity in the universe. Between these structures, vast voids, regions nearly devoid of galaxies, stretch out, making the web all the more captivating in its complexity. The arrangement of galaxies within this web offers more than just a striking visual. It provides us with clues about dark matter and dark energy, the unseen forces that make up the majority of the universe's mass and energy. The study of the cosmic web is not only about mapping the universe's structure, it's about understanding how the universe evolved. By analyzing the distribution of galaxies, astronomers are slowly piecing together the story of the cosmos, revealing how it has transformed from its chaotic origins into the vast, structured entity we observe today. The cosmic web holds the key to understanding where the universe has come from and where it might be headed in the future. In this way, it deepens our appreciation of the forces that govern every galaxy, star, and planet, offering insights into the very nature of existence itself. Within this grand cosmic tapestry, stars are the jewels that light up the night sky, but some stars exhibit characteristics that stretch the boundaries of our understanding. Magnetars, a type of neutron star, are among the most remarkable objects in the universe. These highly magnetic stars possess the strongest magnetic fields known to humankind, far beyond the reach of anything we encounter on Earth. The origin of these extreme magnetic fields lies in the violent collapse of a massive star during a supernova explosion. When a massive star runs out of nuclear fuel, it undergoes a spectacular explosion, leaving behind a dense core. This core, known as a neutron star, is so packed that protons and electrons merge to form neutrons. This collapse, governed by the laws of gravity and angular momentum, leads to a rapid rotation of the neutron star, which amplifies the magnetic field in the process. In the dense interior of a neutron star, the alignment of particles and the pressure generated by gravitational collapse contribute to the creation of magnetic fields that can reach over 1 billion Teslas, over 1,000 times stronger than the magnetic fields of ordinary neutron stars. Although the exact mechanism behind these immense fields remains an active area of research, it's believed that a dynamo effect takes place within the magnetar, where electrically conductive fluids generate powerful currents that further amplify the magnetic field. These magnetic fields are not static, they fluctuate, leading to phenomena such as starquakes, sudden, violent releases of energy as the star's crust adjusts to the intense magnetic forces. These eruptions produce gamma rays and X-rays, making magnetars some of the most energetic objects in the universe. By studying magnetars, astronomers can probe the nature of matter under extreme conditions and gain deeper insights into the fundamental laws of the universe itself. Among the stars that have captured the imagination of astronomers is Tabby's star, also known as KIC 8462852. This enigmatic star has been the subject of intense study due to its strange and periodic dimming pattern, first discovered by the Kepler Space Telescope. The star exhibits significant unexplained fluctuations in brightness, leading to a flurry of theories attempting to explain the cause of these dimming events. Initially, astronomers speculated that clouds of dust or debris might be orbiting the star, causing its light to be partially obscured as the clouds passed in front of it. Yet, the mystery of Tabby's star has only deepened, challenging our understanding of stellar phenomena and inviting further exploration. This star's behavior could potentially unlock secrets about the behavior of stars, the nature of interstellar dust, or even the possibility of alien megastructures, hypotheses that push the limits of our imagination. Regardless of the explanation, Tabby's star continues to serve as a reminder of how much we have yet to learn about the wonders of the cosmos. However, the characteristics of the dimming observed in Tabby's star didn't align perfectly with what scientists expected if dust were the sole cause. The irregular dips in brightness, fluctuating in both depth and duration, hinted at something far more intricate and elusive. One of the most captivating hypotheses suggested that an enormous structure might be orbiting the star, possibly an alien megastructure, such as a Dyson sphere designed to harness its energy. This bold and speculative idea captured the imagination of many, sparking a wave of excitement and wonder. Yet despite its allure, the theory remains highly unlikely. As time passed, subsequent observations began to favor more natural explanations. One such theory involved the presence of a swarm of comets, perhaps countless icy bodies that could cause temporary dimming effects as they clustered around the star, their dust and debris obscuring the light in dramatic bursts. When comets approach a star, they disintegrate, creating a transient shadow across the star's brightness. This swarm-like scenario, though still speculative, provided a more grounded explanation that could account for the irregular behavior. To date, no single theory has definitively unraveled the mystery of Tabby's star's periodic dimming. Ongoing studies, armed with cutting-edge observational tools, continue to track the star's unusual light curves in the hopes of uncovering deeper insights. Every new observation brings us a step closer to understanding not only the peculiar behavior of Tabby's star, but also the broader cosmic phenomena that challenge our understanding of the universe. This case is a perfect example of how the vast, mysterious cosmos can spark both scientific inquiry and our wildest imaginations. Binary star systems, which consist of two stars orbiting a shared center of mass, are among the most common and intriguing features of the universe. These systems form as a natural consequence of the life cycle of stars, particularly in stellar nurseries. When a molecular cloud collapses under its own gravity, it can fragment into multiple clumps of gas, each of which eventually condenses into a protostar. If two protostars form close enough together, their mutual gravitational pull may cause them to become bound in a binary system, where they will continue to orbit one another as they evolve. As these stars grow and mature, they may interact in ways that deeply influence their development. For example, if one star becomes more massive than the other, it may rapidly progress through its evolutionary phases, leaving its companion star behind in its wake. In some cases, if the stars are close enough to one another, they may exchange mass through a phenomenon known as Roche-Lobe overflow, where the outer layers of one star extend beyond its own gravitational reach, spilling material onto its companion. The evolutionary paths of binary stars can vary significantly depending on their masses and separation. For instance, if one of the stars becomes a red giant, it may transfer mass to its companion, which can lead to dramatic outcomes. In some binary systems, this exchange of material results in what's known as a Type 1a supernova, where a white dwarf accumulates enough mass from its companion to trigger a cataclysmic explosion. Alternatively, these interactions can lead to phenomena like X-ray binaries, where material from the companion star spirals into the denser star, emitting intense X-ray radiation in the process. The fate of a binary system largely depends on the initial separation of the stars. Wide binaries, where the stars are separated by vast distances, tend to evolve independently. However, closer binaries are more likely to engage in intricate interactions, with their stars impacting one another's evolution in unpredictable ways. Over time, these systems may result in one star becoming a white dwarf while the other continues to evolve along a different path. The development of binary stars provides essential insights into stellar evolution. Their complex and interconnected fates offer us a window into the diverse outcomes that can unfold in the universe. From supernovae to white dwarfs, binary star systems help illuminate the intricate relationships that govern the behavior of stars and their role in shaping the cosmos. A star's life cycle is an awe-inspiring journey that spans millions to billions of years, depending on its mass. The process begins in a stellar nursery where immense clouds of gas and dust collapse under their own gravity. As the material condenses, it forms a protostar, which begins to heat up due to the gravitational energy being converted into thermal energy. This phase marks the beginning of the star's existence, with mass continuing to accumulate until the core reaches a high enough temperature and pressure for nuclear fusion to ignite, signaling its transition to the main sequence phase. During the main sequence, which constitutes the bulk of a star's life, hydrogen nuclei fuse into helium, releasing energy in the process. The duration of this phase varies dramatically depending on the star's mass. More massive stars may only spend a few million years in this stage, while smaller stars like our Sun can remain in this phase for roughly 10 billion years. As a star exhausts its hydrogen fuel, its core begins to contract under the pressure of gravity, while its outer layers expand. This transformation marks the star's entry into the red giant phase. During this stage, the core's temperature rises high enough to initiate the fusion of helium into heavier elements, such as carbon and oxygen. This process sets the stage for the star's eventual fate, which may include shedding its outer layers or exploding in a supernova, depending on its mass. Each of these phases, birth, evolution, and death, tells a story of cosmic balance, of forces far beyond our daily experience, yet intimately tied to the future of the universe itself. However, not all stars follow the same path. The future pathways diverge dramatically based on their initial masses. For stars with low to medium mass, like our Sun, the fate is both beautiful and peaceful. As these stars near the end of their life, they shed their outer layers, forming a breathtaking planetary nebula. What remains of the star is a dense core, a white dwarf, fading and cooling over the course of billions of years, ultimately becoming a faint relic of its former self. But for high-mass stars, the story takes a much more dramatic turn. Upon exhausting their nuclear fuel, they undergo a complex series of fusion processes that create progressively heavier elements, building up a core rich in iron. When the core becomes so massive that it can no longer support itself under the force of gravity, the stage is set for a cataclysmic event. The star's core collapses, and the result is a supernova explosion. This spectacular detonation scatters the star's material into space, enriching the interstellar medium with new elements that will go on to form new stars, planets, and perhaps even life itself. In the aftermath, the core may be compressed into a neutron star, an incredibly dense object where the forces of gravity have collapsed atoms into a tightly packed state. In some cases, however, the collapse continues until the object becomes a black hole, an enigmatic and invisible remnant of a once vibrant star. This marks the end of that star's life cycle, but also contributes to the ongoing narrative of cosmic creation and destruction, of beginnings and endings. Supernovae are among the most spectacular events in the universe, representing the explosive death of stars and leaving behind a cosmic legacy. There are two main types of supernova, each resulting from different mechanisms. Type 1 supernovae occur in binary star systems, where a white dwarf accumulates material from its companion star. When the white dwarf's mass reaches a critical threshold, known as the Chandrasekhar limit, the pressure and temperature at its core become sufficient to ignite carbon fusion. This triggers a rapid, runaway nuclear reaction, causing the white dwarf to explode in a cataclysmic burst of energy, leaving behind no remnant. On the other hand, Type 2 supernovae are the dramatic end-of-life events for massive stars. When these stars exhaust their nuclear fuel, the fusion processes that have been balancing gravitational collapse cease. The star's core contracts under immense pressure, eventually forming a dense iron core. When the mass of this core exceeds its capacity to resist gravity, it collapses, triggering an explosive rebound effect. The outer layers of the star are hurled into space in an explosive shockwave. This burst of energy can briefly outshine entire galaxies, a vivid display of the immense power unleashed in the final moments of a star's existence. Supernovae play an essential role in the evolution of the universe, particularly in the chemical enrichment of the cosmos. The elements that form in the hearts of stars, along with those created in the supernova explosion itself, are scattered throughout the interstellar medium. This material becomes the building blocks for new stars, planets, and even life. Supernovae synthesize and scatter heavy elements like iron, nickel, and lead, elements that are crucial to the formation of planets and the existence of life as we know it. Without these explosive events, the universe would lack the complexity and diversity of elements we rely on for life. But the impact of supernovae doesn't end with their destruction. The remnants of these explosions, often in the form of neutron stars or pulsars, offer profound insights into the nature of matter and the laws of physics. These dense objects become natural laboratories for astrophysics, providing clues about the behavior of matter under extreme conditions. Furthermore, the energetic bursts associated with supernovae can trigger the formation of new stars in nearby clouds of gas, influencing the structure and evolution of entire galaxies. In this sense, supernovae are not merely the violent ends of stars, they are also the beginnings of new cosmic structures. Supernovae, then, are not only dramatic and awe-inspiring, they are pivotal events in the ongoing process of cosmic evolution. Through their explosive power, they contribute to the dynamic, ever-changing tapestry of the universe, reminding us of the interconnectedness of stellar life cycles and the continual unfolding of creation and destruction on a grand scale. The universe is constantly being shaped and reshaped by these incredible forces, marking both the ends of stars and the births of new worlds and galaxies. Neutron stars are some of the most fascinating and dense objects in the universe, remnants left behind after the explosive deaths of massive stars. Their formation occurs during supernova events, when the core of a star collapses under its own immense gravity. This collapse compresses protons and electrons so tightly that they combine to form neutrons, resulting in a star that is primarily composed of these subatomic particles. Despite having a mass greater than the Sun, this remnant is compressed into a sphere only a few kilometers across, making neutron stars incredibly dense and compact. Within the realm of neutron stars, there are several distinct types, each with its own unique characteristics and formation processes. One of the most well-known types is the pulsar, a rotating neutron star that emits powerful beams of electromagnetic radiation from its magnetic poles. As the pulsar spins, these beams sweep across space, and if their trajectory aligns with Earth, we detect them as regular, rhythmic pulses. These pulses are much like a cosmic lighthouse, offering a glimpse into the extreme conditions present in the star. Pulsars are born when the progenitor star's core collapses, conserving angular momentum and causing the neutron star to spin at incredibly high speeds. This rapid rotation generates powerful magnetic fields that produce the electromagnetic beams we observe. Another striking type of neutron star is the magnetar, which is defined by its extraordinarily powerful magnetic fields that can be more than 1 billion times stronger than those of typical neutron stars. Magnetars are formed in a similar manner to pulsars, but their magnetic fields are far more intense, resulting from unique conditions in their formation. During the collapse of the star's core, these intense magnetic fields can trigger dramatic phenomena such as starquakes and explosive bursts of X-rays and gamma rays. These energetic outbursts give magnetars a reputation for being some of the most extreme and unpredictable objects in the universe. There are also binary neutron stars, which are systems in which two neutron stars orbit each other. These systems can form in two ways, either through the simultaneous evolution of two stars within a binary system, or as a result of interactions that cause two neutron stars to merge. When these stellar remnants collide, the event is nothing short of spectacular. The merger of neutron stars can create heavy elements such as gold and platinum through a process known as kilonova. These mergers play a crucial role in enriching the universe with the materials necessary for planet formation and, ultimately, life itself. The diversity among neutron stars underscores the complex and varied outcomes of stellar evolution. Each type offers a glimpse into the extremes of physical conditions and the fascinating processes that govern the lives and deaths of stars. By studying neutron stars, we not only gain a deeper understanding of high-energy astrophysics, but also learn more about the cosmic forces that have shaped our galaxy over billions of years. In contrast to neutron stars, white dwarfs are the remnants of medium-sized stars, specifically those that have exhausted their nuclear fuel. The formation of a white dwarf begins when a star like our Sun evolves into a red giant after burning through its hydrogen fuel. As the core contracts, the outer layers of the star expand dramatically. When helium in the core begins to fuse into heavier elements, the star sheds its outer layers, creating a planetary nebula. What remains is the hot, dense core, which ultimately becomes a white dwarf. This core is primarily composed of carbon and oxygen, the remnants of the star's earlier fusion processes. Unlike their more massive counterparts, which explode as supernovas, white dwarfs do not experience such violent ends. Instead, they gradually cool over time, with their fate shaped by the principles of electron degeneracy pressure. This quantum mechanical effect provides the necessary support to prevent the white dwarf from collapsing under its own gravity, allowing it to exist as a stable object despite the lack of fusion in its core. However, a white dwarf's mass is limited. It cannot exceed approximately 1.4 times the mass of the Sun, a threshold known as the Chandrasekhar limit. If a white dwarf exceeds this limit, perhaps by accumulating material from a companion star, it can trigger a Type 1a supernova, a catastrophic explosion that can outshine an entire galaxy. The ultimate fate of a white dwarf is to continue cooling and fading over an unimaginably long timescale. Initially, it shines brightly due to the residual thermal energy from its past, but over billions of years, this energy dissipates. As the white dwarf cools, it becomes dimmer and eventually transforms into a cold, dark remnant, a black dwarf. This process, however, occurs on a timescale so vast that it far exceeds the current age of the universe, making black dwarfs still theoretical objects. Together, neutron stars and white dwarfs represent two different paths that stars take after exhausting their fuel. While neutron stars provide insight into the extremes of stellar collapse and the forces that govern the universe's most extreme phenomena, white dwarfs offer a glimpse into the fate of stars like our own Sun, slowly fading into cold remnants over eons. These stellar remnants, in all their complexity and diversity, continue to fascinate astronomers and deepen our understanding of the cosmos. However, this stage remains purely theoretical. The universe, at this point, is not yet old enough for any white dwarf to have cooled to the point where it could reach such a state, given that the first stars are still relatively young in cosmic terms. White dwarfs, however, play an essential role in the broader narrative of galaxy evolution and the ongoing cycle of stellar material. As they cool over time, they contribute valuable elements to the interstellar medium, ingredients crucial for the formation of new stars and planets. This process of cooling and eventual transformation of a white dwarf is a testament to the universe's continuous cycle of creation and destruction. It underscores the intricate dance of stellar life and death, revealing how even the remnants of stars, those often thought of as lifeless husks, are vital to the ongoing evolution of cosmic matter. Stellar flares, by contrast, are dramatic, explosive events that send ripples through the cosmos. These sudden bursts of energy erupt from the surfaces of stars, including our own Sun, and are the result of intricate magnetic dynamics within these celestial bodies. The underlying cause of a stellar flare is tied to the behavior of magnetic fields, which are generated by the movement of electrically charged particles in a star's atmosphere. As these magnetic field lines become twisted and tangled, particularly through the star's rotation and convection currents in its outer layers, they can snap and reconnect, releasing an immense amount of energy. This surge of energy radiates across the entire electromagnetic spectrum, from radio waves to X-rays and even gamma rays. The release of such intense heat during a flare can result in a sudden and dramatic increase in a star's brightness, often making the event detectable from vast distances. Our sun, for instance, frequently experiences solar flares of varying intensities. These flares can have far-reaching effects on the space environment, influencing the weather conditions in our solar system. The radiation and particles released during a flare can generate coronal mass ejections, massive clouds of charged particles that are expelled into space. If a particularly strong flare occurs, these particles can slam into a planet's magnetosphere, causing geomagnetic storms. On Earth, these storms can disrupt satellite communications, damage power grids, and even cause stunning auroral displays near the poles. Yet for planets that lack strong magnetic fields, like Mars, the situation is much more dire. Without a protective shield, the energetic particles from a flare can strip away a planet's atmosphere over time, potentially making it inhospitable for life. For astronomers, studying stellar flares is vital for understanding not only the magnetic behavior of stars, but also the potential impacts on the planets orbiting them. These powerful events reveal much about the dynamic and often hazardous nature of stellar environments, helping scientists learn how stars interact with their planetary systems. This knowledge has profound implications for the study of planetary atmospheres and the conditions required for life to thrive in other parts of the universe. Meanwhile, pulsars, one of the most intriguing classes of neutron stars, continue to captivate the imagination of astrophysicists. These stellar remnants are known for emitting remarkably regular and periodic pulses of radio waves. What makes pulsars so extraordinary is the mechanism behind their pulsating signal, which is directly linked to their unique physical properties. When a massive star reaches the end of its life, it may explode in a supernova, leaving behind a neutron star, a dense and rapidly rotating object. These pulsars spin at incredible speeds, and their strong magnetic fields, trillions of times stronger than Earth's, accelerate charged particles along their magnetic poles, propelling them toward the star's surface. Due to the tilted alignment of the pulsar's magnetic field relative to its rotation axis, the radiation emitted is not uniform, but concentrated in two narrow beams that sweep across space. As the pulsar spins, these beams of radiation rotate like a lighthouse beacon, sweeping in and out of our line of sight. When one of these beams aligns with Earth, we detect the pulses as radio waves, often with staggering regularity. Some pulsars emit pulses with intervals of mere milliseconds, while others have periods stretching into seconds or minutes. This remarkable stability arises because of the pulsar's well-defined rotational period, which is a direct consequence of the conservation of angular momentum. Among the various types of pulsars, millisecond pulsars stand out for their exceptionally rapid rotation rates. These pulsars spin at incredible speeds, having gained angular momentum by accreting material from a companion star in a binary system. This rapid rotation leads to an astonishing degree of precision in their pulse timings, making them incredibly valuable tools for testing fundamental theories of gravity and the behavior of matter in extreme environments. They even allow scientists to study gravitational waves, providing insights into some of the most profound phenomena in astrophysics. The study of pulsars not only deepens our understanding of neutron stars, but also raises fundamental questions about the nature of matter and the forces that govern it. Each pulse emitted by a pulsar serves as a cosmic signal, an extraordinary reminder of the intense conditions within neutron stars and the larger processes shaping the universe. Through this exploration, we continue to unlock the mysteries of these enigmatic celestial objects, and in doing so, we gain deeper insights into the fundamental workings of the cosmos. Brown dwarfs are captivating celestial bodies that occupy a fascinating space between the largest planets and the smallest stars. They form in stellar nurseries just like other astronomical objects, but they never acquire enough mass to ignite hydrogen fusion, the process that powers most stars. Typically, brown dwarfs have a mass between about 13 and 70 times the mass of Jupiter, which sets them apart from true stars and gas giant planets. Often called failed stars, brown dwarfs do not possess the necessary mass to sustain the fusion process that occurs in stars like our Sun. While stars maintain equilibrium by fusing hydrogen into helium over billions of years, brown dwarfs lack the mass and pressure needed to trigger this reaction. Instead, they may briefly fuse deuterium, a heavier isotope of hydrogen, but this process is short-lived, occurring only during the early stages of their formation. As a result, brown dwarfs remain cool and dim, emitting energy primarily in the infrared spectrum, making them incredibly difficult to detect using traditional optical telescopes. Despite their low luminosity, brown dwarfs are not without intrigue. Their atmospheres, which can include clouds of compounds like water, ammonia, and even silicates, bear a striking resemblance to the atmospheres of gas giants. These relatively low temperatures allow for complex chemical interactions, and in some cases, brown dwarfs even exhibit weather patterns and cloud formations, providing a unique glimpse into the atmospheric dynamics of objects that are neither stars nor planets. The study of brown dwarfs is crucial for several reasons. First, they bridge the gap between stars and planets, offering valuable insight into stellar formation and the processes that govern the creation of celestial bodies. Moreover, brown dwarfs contribute to our broader understanding of cosmic evolution, revealing the diversity of objects within our galaxy. As researchers continue to discover and study these fascinating objects, we gain a deeper understanding of the myriad forms matter can take in the cosmos. In a completely different part of the universe, supermassive black holes lurk at the centers of most galaxies, including our Milky Way. These monstrous entities can be millions to billions of times the mass of our Sun. The formation of supermassive black holes is a complex and still largely mysterious process, involving a number of overlapping mechanisms that researchers are working tirelessly to unravel. One widely accepted theory posits that supermassive black holes are the result of the merging and gradual growth of smaller black holes and other massive objects over cosmic time. The process begins with the formation of stellar mass black holes, which occur when massive stars collapse at the end of their lives. These black holes can grow by accreting gas and dust from their surroundings and can merge with other black holes created in star clusters or by supernova events. Over time, these once relatively small black holes can grow significantly, accumulating more mass through accretion and mergers. Another crucial factor in the formation of supermassive black holes is the behavior of matter in the early universe. Just after the Big Bang, dense pockets of gas began to collapse, forming the first stars and star clusters. Some of these primordial stars may have been extraordinarily massive, collapsing directly into black holes. In the dense environments of early galaxies, conditions were ripe for rapid growth, as gas would fall into the black hole's gravitational well, heating up and creating the perfect conditions for rapid accretion. Additionally, galaxy mergers, common events in the universe's evolution, can lead to the merging of central black holes, which ultimately results in the formation of even larger supermassive black holes. During these galactic collisions, the gravitational dynamics often funnel gas toward the center, further feeding the growing black hole. The presence of supermassive black holes at the centers of galaxies has profound implications for our understanding of astrophysics and galaxy formation. They influence the motion of stars and the patterns of star formation within galaxies. Understanding how these colossal black holes form and grow not only sheds light on the structure and evolution of galaxies, but also provides important insights into the physics of gravity and the nature of space-time itself. As astronomers continue to investigate this intriguing subject, they deepen our understanding of the dynamic processes that have shaped our universe over billions of years. At the heart of every black hole lies the event horizon, a boundary beyond which nothing can escape the black hole's intense gravitational pull, not even light. This threshold raises profound questions about the nature of space-time and the fate of objects or information that cross it. Scientifically, it is nearly impossible to understand what happens beyond the event horizon, as no information can ever return from this region to be observed or measured. Once an object crosses the event horizon, it is inexorably drawn toward the singularity, the core of the black hole, where gravity becomes infinite, and the laws of physics, as we know them, cease to apply. The singularity, a point of infinite density, remains one of the greatest mysteries in astrophysics, challenging our understanding of the fundamental nature of the universe. As matter approaches the singularity at the heart of a black hole, it is subjected to extreme tidal forces, forces so intense that they stretch and compress it in what is known as spaghettification. This effect occurs due to the immense gravitational gradient present in the vicinity of the black hole. In the framework of relativity, however, the experience of crossing the event horizon might not be as catastrophic as one might expect, at least not immediately. For an observer falling into the black hole, the passage through the event horizon could be almost imperceptible. They might not feel anything unusual as they continue toward the singularity, though their fate would already be sealed. But the perspective is starkly different for an outside observer. To them, the infalling object appears to slow down progressively, never quite crossing the event horizon. This phenomenon is a direct result of time dilation, an effect caused by the extreme warping of space-time around the black hole. As the object nears the horizon, light emitted from it gets increasingly redshifted, ultimately fading from view entirely. This scenario leads us to one of the most intriguing challenges in modern physics, the information paradox. The question arises, when an object is swallowed by a black hole, does the information it carries, its properties and the data of its physical state, simply disappear forever, or can it be recovered in some form? This dilemma goes beyond the known laws of classical physics, delving into the realm of quantum mechanics. The paradox has spurred multiple theories that attempt to reconcile the seemingly incompatible principles of general relativity, which describes black holes classically, and quantum mechanics. Some theories suggest that the information might be stored on the event horizon itself, perhaps encoded in the event horizon's quantum properties, while others propose that the information could be preserved in some unknown manner, waiting to be uncovered. Despite the complexities of this issue, ongoing research in fields such as quantum gravity and black hole thermodynamics continues to provide new insights. Every breakthrough in these areas brings us closer to understanding the extreme conditions within black holes and, more broadly, the fundamental laws governing the universe. One such groundbreaking idea is the concept of Hawking radiation, introduced by physicist Stephen Hawking. Hawking proposed that black holes are not entirely black, but instead can emit radiation due to quantum effects near the event horizon. At first glance, this idea seems paradoxical. Black holes are known for their enormous gravitational pull, one so powerful that not even light can escape once it crosses the event horizon. Yet, according to Hawking's calculations, black holes can still emit radiation, a phenomenon rooted in the quantum mechanical behavior of particles. The key to this process lies in virtual particles, pairs of particles and antiparticles that spontaneously form and annihilate in empty space due to quantum fluctuations. These pairs can form even in the vacuum surrounding a black hole. In some cases, one member of a virtual particle pair falls into the black hole while the other escapes into space. The escaping particle is then detected as radiation emanating from the black hole. For this escaping particle to be detectable as Hawking radiation, the particle that falls into the black hole effectively carries negative energy. From the perspective of an outside observer, this causes the black hole to lose energy in the form of radiation. Over time, this continuous emission of Hawking radiation could cause the black hole to lose mass and energy, potentially leading to its gradual evaporation. However, this process occurs incredibly slowly, especially for massive black holes. For large black holes, the rate of Hawking radiation emission is so low that it is nearly negligible compared to their gravitational dominance. Despite this, the concept of Hawking radiation has profound implications for theoretical discussions on the fate of black holes, particularly concerning the conservation and loss of information in the universe. This raises a further issue. If black holes eventually lose mass and evaporate, what happens to the information about the matter that fell in? The loss of this information presents a challenge to the very foundations of quantum mechanics, and it remains a highly debated area of research. While much is still unknown, Hawking radiation offers a stunning intersection of quantum mechanics and astrophysics, suggesting that black holes are not completely black after all. In 2019, a momentous achievement in astrophysics provided a direct glimpse into the nature of black holes. The Event Horizon Telescope, a global collaboration of scientists, released the first ever image of a black hole located at the center of the galaxy M87. This black hole is estimated to be 5 billion times more massive than the Sun, and is situated around 53 million light-years from Earth. The significance of this image lies not only in the confirmation of the existence of a black hole, but also in the technological and scientific teamwork that made it possible. The capture of this image marked a milestone in our understanding of these enigmatic cosmic objects, offering unprecedented insight into their structure and behavior. Each new discovery, like this image, brings us a step closer to unraveling the mysteries of black holes and, by extension, the very fabric of our universe. The Event Horizon Telescope, EHT, is a groundbreaking global collaboration, a network of radio observatories that work in tandem to create a virtual telescope as vast as the Earth itself. This ambitious initiative draws together thousands of scientists from across multiple countries, showcasing the immense power of global cooperation in advancing our understanding of the universe. The result of this effort? The first ever image of a black hole, a striking visual that shows a bright ring-like structure encircling a dark central region. This is the event horizon, the point of no return surrounding a black hole. The image, captured in the galaxy M87, provides more than just a stunning visual. It serves as powerful confirmation of Einstein's theory of general relativity. The depiction aligns remarkably well with predictions made by the theory, offering further validation of this cornerstone of modern physics. Beyond its aesthetic impact, the observation gives scientists a new window into the dynamics of matter as it spirals into the black hole, answering fundamental questions about gravity, space-time, and the behavior of black holes within their cosmic environments. The discovery also holds profound implications for our understanding of galaxy formation and evolution. Supermassive black holes, such as the one in M87, often reside at the centers of galaxies, and their growth can significantly influence the galaxy's structure and star formation processes. By examining these immense cosmic objects, astronomers gain invaluable insights into the forces that shape galaxies across the universe, from their birth to their evolution. This pioneering achievement not only marks a significant milestone in observational astrophysics, but also opens new avenues for future research. As technology improves and observational techniques advance, scientists hope to capture more detailed images of black holes, study their properties, and dive deeper into the mysteries of the universe they inhabit. The image of the black hole in M87 stands not only as a scientific triumph, but also as an inspiring reminder of the vast enigmas that still lie hidden, waiting to be uncovered in the cosmos. In the intricate dance of binary black hole systems, two black holes evolve over time, interacting through complex gravitational forces. These systems typically begin with two massive stars orbiting each other. After their life cycles end, both stars collapse, giving birth to black holes. Over time, these black holes continue to orbit each other, gradually losing energy through the emission of gravitational waves, ripples in the fabric of space-time that carry energy away from the system. As they lose energy, the black holes spiral ever closer together, accelerating in their orbital motion. Eventually, the gravitational attraction between the black holes becomes so strong that it triggers the final stages of their merger. As the black holes approach each other at increasingly high speeds, they enter a phase known as the inspiral. During this phase, intense gravitational waves are emitted, detectable by observatories like LIGO and Virgo. The merger itself is a cataclysmic event, producing a burst of energy as the event horizons of the black holes combine. The result is often a single, more massive black hole. After the merger, the newly formed black hole may oscillate briefly before settling into a stable state. The energy released during the merger is immense, and the detection of such events has opened up new opportunities in the study of black holes. It offers fresh insights into the fundamental laws of physics, including the very nature of gravity and the fabric of space-time itself. Primordial black holes, which are believed to have formed in the early universe just after the Big Bang, present another fascinating avenue of study. Unlike the more familiar black holes that form from the collapse of massive stars, primordial black holes could have originated from density fluctuations in the hot, dense matter that existed during the universe's infancy. These fluctuations could have caused regions of mass to concentrate enough for gravitational forces to trigger an instantaneous collapse into black holes. Some theories propose that these black holes might have formed during a period of incredibly high temperatures, allowing for rapid gravitational collapse under specific conditions. As the universe expanded and cooled, certain dense regions could have collapsed into black holes without the need for stars to form first. As a result, primordial black holes could range in size from minuscule objects smaller than typical asteroids to massive ones, potentially many times the mass of our Sun. Understanding primordial black holes has profound implications for cosmology and dark matter research. Some theories suggest that these black holes could make up a significant portion of the dark matter that permeates the universe. Dark matter, though it constitutes a large part of the universe's total mass, remains largely undetectable by traditional methods. Detecting primordial black holes or their effects could provide critical insights into the fundamental processes that shaped the early universe and might even help explain the nature of dark matter itself. As scientists continue to investigate this intriguing possibility, the search for primordial black holes raises essential questions about the conditions that existed at the dawn of time, offering a glimpse into how the universe has evolved into what we observe today. Intermediate mass black holes serve as an intriguing link in our quest to understand black hole evolution. They occupy a mass range between stellar black holes, which typically have masses of just a few tens of solar masses, and supermassive black holes, which can reach millions or even billions of times the mass of the Sun. These intermediate mass black holes generally range between 100 and 1,000 solar masses, and their very existence challenges long-standing theories regarding the formation of black holes. The formation of these mysterious objects remains poorly understood. One hypothesis proposes that they arise from the mergers of smaller black holes, particularly in dense stellar environments such as globular clusters. In these settings, stellar black holes collide and merge, gradually accumulating mass and potentially forming an intermediate mass black hole. Another possibility is that they might form directly from the collapse of massive stars, especially during the early stages of the universe, when conditions were more conducive to the existence of larger progenitor stars. Studying these intermediate mass black holes is crucial for understanding how supermassive black holes, which reside at the centers of galaxies, grow. It's believed that intermediate mass black holes could serve as seeds for the formation of supermassive black holes, growing through additional accretion of matter and further mergers. By investigating their properties and distribution across the universe, scientists are gradually piecing together how black holes have evolved over cosmic time. This research offers invaluable insights into the formation and evolution of galaxies, showing how these massive objects have shaped the cosmos. However, detecting intermediate mass black holes is no easy feat. Traditional observational techniques often struggle to identify them due to their elusive nature. Yet, confirming their existence could not only reshape our understanding of black hole formation, but also reveal the underlying processes that govern black hole evolution. Such discoveries would illuminate their role within the broader cosmic landscape, enhancing our knowledge of the universe's deep structure. The relationship between black holes and galaxy formation is a dynamic one, intricately tied to the evolution of the universe itself. At the heart of most galaxies lies a supermassive black hole, whose mass can range from millions to billions of times that of the Sun. These behemoth black holes exert profound influence over their surrounding environments, playing a key role in the growth and stabilization of galaxies over cosmic time. Galaxies themselves form from vast clouds of gas and dark matter, undergoing an initial gravitational collapse that triggers the creation of stars and other celestial bodies. During this process, matter can gather at the center of the emerging galaxy, leading to the formation of a massive black hole, either through the direct collapse of a gas cloud or through the merger of smaller black holes. Once formed, the supermassive black hole at the galaxy's center becomes a gravitational anchor, regulating the dynamics of the galaxy. Its immense gravitational pull influences the orbits of nearby stars and gas, shaping the galaxy's structure and guiding its evolution through the vast stretches of time. In this cosmic interplay, black holes don't just exist as passive objects, but actively contribute to the very formation and stability of galaxies, underscoring their importance in the grand narrative of the universe's evolution. Black holes, when actively accreting material, unleash enormous energy that drives powerful winds and outflows of gas. This feedback mechanism plays a crucial role in shaping star formation within the surrounding regions, influencing how galaxies evolve. Research has revealed a remarkable connection between the masses of supermassive black holes and the stars in their host galaxies. Observations suggest that more massive black holes are typically found in larger galaxies, pointing to an intricate relationship where the growth of black holes and galaxies is deeply intertwined. This dynamic interaction enhances our understanding of cosmic evolution, highlighting how black holes not only shape galaxies but also the broader structure of the universe. The impact of black holes goes beyond just galaxies. They significantly influence both time and space due to their immense gravitational pull. According to Albert Einstein's theory of general relativity, massive objects warp the fabric of space-time. Black holes, among the densest and most massive objects in the universe, generate intense gravitational fields, bending space-time in profound ways. As one approaches the event horizon, the boundary beyond which nothing can escape, a fascinating phenomenon occurs. Time appears to slow down relative to an observer far away. This effect, known as time dilation, is a direct result of the black hole's gravitational influence. For someone near the event horizon, time would pass normally from their perspective. However, if they could somehow observe a clock from the outside, they would see it ticking at an accelerated rate. This mind-bending aspect of black holes raises profound questions about the very nature of reality and challenges our perception of time. Space itself is altered by black holes as well. Their immense gravitational pull causes a significant distortion, making the paths of nearby objects curve. This leads to fascinating phenomena, such as accretion disks, where material spirals inward at incredible speeds, heating up and emitting intense radiation. This curvature of space affects the movement of stars and gas in nearby galaxies, influencing their dynamics. The closer one gets to a black hole, the more extreme these effects become. At the singularity, the point at the center of a black hole where density becomes infinite, the known laws of physics break down, and scientists are left grappling with the true nature of space, time, and gravity. Understanding how black holes manipulate time and space deepens not only our knowledge of these enigmatic objects, but also enriches our broader comprehension of the universe itself. This exploration forces us to confront the limits of our understanding and challenges our views on the very fabric of reality. When two black holes in a binary system collide, the result is a spectacular merger. As the black holes spiral toward one another, they release an immense amount of energy, primarily in the form of gravitational waves, ripples in the fabric of spacetime generated by the acceleration of massive objects. This event unfolds in a phase known as inspiral, where the two black holes orbit a common center of mass, losing energy through the emission of gravitational waves. The closer they get, the more intense these waves become, culminating in a final burst of energy just before the merger. As the black holes collide, they rapidly coalesce into a single, more massive black hole. After the merger, the newly formed black hole may oscillate briefly before stabilizing into a steady state. Detecting these colossal events is made possible by advanced observatories like LIGO and Virgo, which are equipped with highly sensitive instruments designed to measure minuscule distortions in spacetime caused by passing gravitational waves. These observatories use laser interferometry to detect changes in the length of arms, forming an L shape. When a gravitational wave passes, it stretches one arm while compressing the other, causing a detectable shift in the measurement. This technology enables scientists to observe distant black hole mergers, allowing them to study the properties of the merging black holes, such as their masses and spins. The detection of gravitational waves not only confirms the existence of black hole mergers, but also opens up new frontiers in our understanding of fundamental physics, cosmology, and the nature of the universe. Each event detected provides valuable insights into how black holes form, merge, and evolve, offering us glimpses into the early universe and the extreme nature of spacetime. This growing body of knowledge continues to transform our understanding of the cosmos and our place within it. Around the colossal cosmic structures, the formation of the first stars and galaxies after the Big Bang marks a pivotal era in the history of the universe, an era we now refer to as the cosmic dawn. In the initial moments following the Big Bang, the universe was a hot, dense soup of fundamental particles. As the universe expanded and cooled, protons, neutrons, and electrons began to form, eventually combining to create simple atomic nuclei. This period, known as recombination, allowed electrons to bond with these nuclei, forming neutral hydrogen and helium atoms. Once the universe became transparent to radiation, it entered the cosmic dark ages, a time marked by a lack of structure, where the universe was predominantly filled with hydrogen and helium gas. Over hundreds of millions of years, tiny fluctuations in density, primarily driven by quantum effects in the early universe, began to cause matter to clump together under the influence of gravity. As these regions contracted, they gathered mass, forming dense clouds of gas. Eventually, these clouds, composed mostly of hydrogen and helium, became so dense and hot that nuclear fusion ignited, giving birth to the very first stars, known as population 3 stars. These stars were likely massive, their enormous energy output leading to the formation of heavier elements through nuclear fusion within their cores. Once their fuel was exhausted, these massive stars ended their life cycles in spectacular supernova explosions, dispersing the newly formed elements into the surrounding gas. The remnants of these explosions contributed to the gravitational collapse of nearby gas clouds, fueling the formation of the first galaxies. Over time, gravity brought together stars, gas, and dark matter into larger structures, leading to the creation of more complex galaxies. This critical process set the stage for the rich tapestry of the universe that we observe today. Galaxies have evolved over billions of years through mergers, star formation, and the interplay of dark matter and cosmic expansion. Understanding this early phase of the universe enhances our knowledge of its history and the ongoing processes that continue to shape it. Dark matter plays a crucial yet enigmatic role in the formation and evolution of cosmic structures. Unlike ordinary matter, which makes up stars, planets, and living beings, dark matter does not interact with electromagnetic forces. This means it does not emit, absorb, or reflect light, making it nearly invisible to our instruments. Despite this invisibility, we can infer its presence through its gravitational effects on visible matter, radiation, and the overall structure of the universe. Less than 1 billion years after the Big Bang, the universe was filled with a uniform distribution of gas and dark matter. As gravity began pulling this matter together, dark matter acted as a scaffold, influencing the clumping of ordinary matter. The gravitational wells created by dark matter allowed gas and dust to collapse into denser regions, leading to the formation of stars and galaxies. Essentially, while ordinary matter formed the visible structures of stars and galaxies, dark matter provided the framework that guided their growth. Galaxies form in halos of dark matter, which provide the gravitational pull necessary to prevent the gas from dispersing. These dark matter halos are crucial for holding galaxies together, especially during interactions and mergers. Observations of the rotation curves of spiral galaxies show that stars at the edges of galaxies move faster than they should, assuming only visible matter were present. This disparity strongly suggests a significant amount of unseen dark matter is lurking in and around these galaxies. The influence of dark matter extends beyond individual galaxies and plays a vital role in the formation of galaxy clusters and cosmic filaments, contributing to the large-scale structure we observe today. Dark matter acts like a vast network of highways, guiding the flow of matter throughout the cosmos. As research continues to probe its properties and behavior, dark matter remains one of the most significant and mysterious components of our universe, an essential ingredient in understanding cosmic structure formation and the fundamental workings of gravitational interactions. The rate of star formation has experienced significant changes throughout cosmic history, displaying a dynamic and evolving trajectory. Initially, star formation was a slow process in the early universe. As the universe transitioned from a hot, dense state to a cooler, more structured one, the first stars took hundreds of millions of years to form. During the first few 100 million years, the universe primarily consisted of hydrogen and helium gas, with very little star formation. However, around 1 billion years after the Big Bang, conditions began to change. The formation of the first stars ignited a dramatic increase in the rate of star formation, a period often referred to as the cosmic noon. This phase, which occurred roughly between 6 to 10 billion years ago, marks the peak of star formation. During this time, galaxies were more abundant, and conditions were favorable for gas to collapse into stars, leading to the formation of massive populations of stars. This surge in star formation also coincided with the growth of massive galaxies, often triggered by intense bursts of star formation during galaxy mergers and interactions. These dynamic events fueled a period of rapid star birth, shaping the galaxies we observe today. The evolving rate of star formation tells a captivating story of the universe's dynamic nature and the interplay of gravity, dark matter, and gas over the vast expanse of cosmic history. However, as the universe expanded and evolved, a shift began to emerge in the rate of star formation. Around 5 billion years ago, this change became notably more pronounced. A variety of cosmic factors, including the increasing metal enrichment from supernova explosions and the regulation of star formation driven by energetic feedback from massive stars, contributed to this gradual decline. As galaxies aged, their gas reservoirs slowly diminished, reducing the material available for new star formation. The overall star formation rate steadily decreased, with fewer stars being born in the present-day universe. In the current era, star formation happens at a much slower pace than it did during the universe's earlier, more active stages. The available gas in galaxies has been mostly converted into stars, leaving less material to fuel further birth of stellar bodies. As a result, the universe is transitioning into a quieter phase. While some galaxies still experience bursts of star formation, the prevailing trend points to an inevitable aging process of the universe. Existing stars continue their life cycles, eventually reaching their end. This evolving landscape of star formation highlights the intricate interconnectedness of cosmic processes and the ever-changing nature of the universe over billions of years. Looking ahead, the future of the universe is shaped by key cosmological factors, including the rate of expansion, which is driven by dark energy, the distribution of matter, and the universe's geometry. One prominent theory, the lambda cold dark matter model, suggests that the universe is expanding at an accelerating rate due to dark energy. This mysterious force accounts for roughly 70% of the universe's total energy density. As this expansion continues, galaxies will drift further apart. Over millions to billions of years, many galaxies will move beyond the observable horizon, making them unreachable and invisible to us. This gradual separation will lead to a phenomenon known as cosmic isolation, where the visible universe becomes increasingly sparse, dominated by the remnants of stars and galaxies that once thrived. Over an even longer timescale, the fate of the remaining stars becomes critical. Most stars will eventually exhaust their nuclear fuel, leading to a universe populated mainly by white dwarfs, neutron stars, and black holes. The death of stars will mark the transition to a dark cosmos, where only the faintest glow of stellar remnants illuminates the void. In approximately 100 trillion years, star formation is expected to cease entirely, signaling the end of an era for active galaxies. As we look even further into the distant future, on the scale of trillions of years, theories such as the heat death of the universe predict that entropy will continue to rise, leading to a state of thermodynamic equilibrium. In this scenario, galaxies, stars, and black holes will eventually decay into low-energy particles and radiation, resulting in a cold, dark, and sparsely populated universe. Ultimately, the future of the universe as we understand it today seems to be a long, gradual decline into obscurity, an infinite stretch of time characterized by silence and the absence of significant cosmic events. The evolution of galaxy clusters presents another fascinating chapter in the cosmos's unfolding story. These massive structures, which contain hundreds to thousands of galaxies bound together by gravity, serve as essential laboratories for studying cosmic evolution. The formation of galaxy clusters began when small fluctuations in the density of matter in the early universe triggered the gravitational collapse of regions filled with dark matter and gas. Over billions of years, these collapsing regions coalesced, forming larger clumps that attracted nearby galaxies and matter, reshaping the structure of the universe. As galaxies fall into clusters, they often collide and merge, exchanging stars and gas in the process. These interactions can ignite bursts of star formation as gas is compressed during collisions, leading to periods of heightened activity within the cluster. However, as clusters continue to evolve, they undergo a process known as hierarchical clustering. Smaller groups and clusters merge, forming ever larger structures that reshape the galaxy population. This merging activity can cause significant disruptions in galaxy morphology, transforming once spiral galaxies into elliptical ones, as gravitational forces blend stars together. In parallel, the influence of dark matter within these clusters cannot be overstated. The gravitational forces at play create a well of potential energy that affects the motion of galaxies, shaping the dynamics of the entire cluster. As these processes unfold, the ongoing evolution of galaxy clusters serves as a testament to the vast, interconnected forces shaping the cosmos on an unimaginable scale. The intergalactic medium within galaxy clusters is a vast, dynamic entity dominated by hot, X-ray emitting gas. This gas plays an essential role in the evolution of galaxy clusters, impacting everything from the formation of new stars to the very structure of the galaxies themselves. As galaxies fall into a cluster, their gas can be stripped away by the surrounding hot gas. This process is a crucial part of their evolution. At the same time, the hot gas provides thermal pressure that can inhibit further star formation over time, shaping the future of the galaxies within the cluster. The energy dynamics of these systems are complex, influenced not only by the gas, but also by the feedback from active supermassive black holes located at the centers of some galaxies. These black holes emit powerful energy, affecting star formation processes and, ultimately, the overall growth and diversity of galaxies within the cluster. Over the course of billions of years, galaxy clusters will continue to evolve. They will eventually reach a point where the frequency of mergers begin to decline, leading to a more stable configuration. However, this stability is not permanent. As the universe continues to expand, the interplay of gravity and dark energy will begin to dictate the fate of galaxy clusters. Dark energy will become the dominant force, causing the clusters to gradually loosen their structures. This shift in the forces shaping galaxy clusters will continue to affect their evolution over cosmic timescales, offering essential insights into the history of the universe itself. One of the most important features of the large-scale structure of the universe is the cosmic web. This web is a vast, interconnected structure of galaxies, galaxy clusters, and intergalactic matter, all arranged in an intricate pattern of filaments and voids. The galaxies themselves are found along these filaments, which connect in a web-like fashion, creating a grand network across the universe. Understanding the cosmic web is vital for understanding how matter is distributed across the cosmos and how the universe evolved from its early, nearly homogeneous state to the rich, complex structure it has today. The cosmic web's formation and ongoing evolution have been largely shaped by the gravitational influence of dark matter. In the early universe, small fluctuations in density set off a chain reaction, leading to the collapse of dark matter and the creation of the framework that would later become the cosmic web. Over billions of years, normal matter, which includes stars, gas, and galaxies, accumulated within these dark matter filaments. This process led to the formation of galaxy clusters and continues to drive the growth and merging of galaxies today. As these structures grow, they also influence the distribution of matter throughout the universe. The cosmic web is not uniform. While it is densely populated along the filaments with galaxies, vast regions of emptiness, known as voids, can be found scattered across it. These voids are areas where galaxies are rare and the matter density is significantly lower than in the filaments. This stark contrast between the dense filaments and the empty voids provides important clues to how galaxies form and evolve. The role of the cosmic web in galaxy formation is profound. The gravitational pull of the dark matter filaments affects how gas and other matter are concentrated. These concentrations of gas then give rise to the formation of new stars and galaxies. As a result, the cosmic web plays a direct role in the ongoing evolution of galaxies, influencing not only their creation, but also how they grow and interact over time. Studying the cosmic web is critical for understanding large-scale cosmic phenomena. Observations made by powerful telescopes and through large-scale surveys allow astronomers to trace the evolution of the universe, giving us a glimpse into how it has transformed from a nearly uniform mass of matter into the complex and varied structure that exists today. These observations also provide a window into the fundamental properties of dark matter and dark energy, revealing crucial insights into the forces that shape our universe and influence its continuing expansion. Through the cosmic web, we gain a deeper understanding of the very nature of the cosmos, offering answers to some of the most profound questions about the origins and future of our universe. The cosmic web stands as a vital framework in understanding the organization and evolution of cosmic structures across vast scales, giving us insight into the very fabric of the universe. Measuring the age and size of the observable universe is an intricate process, one that involves a blend of cosmological observations, theoretical principles, and complex calculations. At the heart of this understanding lies the study of cosmic expansion and the behavior of distant galaxies. The key observation here is that galaxies are receding from us, and the further they are, the faster they move away. This relationship is elegantly captured by Hubble's law, which states that the velocity at which a galaxy moves is proportional to its distance from us. This discovery has become a cornerstone in our understanding of cosmic evolution. To estimate the universe's age, scientists delve into the cosmic microwave background radiation, an afterglow of the Big Bang. Tiny fluctuations in this radiation, captured by observatories like the Wilkinson Microwave Anisotropy Probe and the Planck satellite, provide critical information about the early universe and its expansion history. By combining these observations with measurements of the expansion rate, known as the Hubble constant, cosmologists can extrapolate backward, calculating the moment when the universe first began to expand from its initial singularity. Current estimates suggest that the universe is approximately 13.8 billion years old. On the other hand, determining the size of the observable universe focuses on understanding how far light has traveled since the Big Bang. The observable universe is defined as the region from which light has had enough time to reach us since cosmic expansion began. Since light travels at a finite speed, the further an object is, the longer its light takes to reach us. As a result, the observable universe extends about 46.5 billion light-years in every direction from Earth, giving it a diameter of around 93 billion light-years. However, the expansion of the universe adds another layer of complexity. Since the Big Bang, space itself has been stretching, meaning the actual distance between us and far-off objects today is greater than the distance light would have traveled in a static universe. To piece together the full picture of the cosmos, astronomers use a range of observational techniques, such as supernova observations and galaxy surveys. Together, these measurements give us a coherent understanding of the universe's vast size and evolution. These estimates of age and size provide a glimpse into the immense scale of our cosmic home. Yet, perhaps one of the most striking revelations in modern cosmology is the accelerating expansion of the universe, a phenomenon that defies our previous understanding of cosmic dynamics. The discovery of this accelerating expansion emerged in the late 1990s when two independent teams of astronomers were studying Type Ia, a supernova, incredibly bright explosions that serve as standard candles for measuring cosmic distances. As they analyzed the light curves of these distant supernova, they found them to be dimmer than expected, based on earlier models that assumed a uniformly expanding universe. This unexpected dimming suggested that these supernovae were farther away than they should have been if the expansion had been slowing down over time. Instead of decelerating, the universe's expansion was accelerating. This breakthrough led to the hypothesis that an unknown form of energy was driving this accelerated expansion. This mysterious energy, now known as dark energy, is believed to make up around 70% of the universe's total energy density. Its Its true nature remains one of the greatest enigmas in modern cosmology, but its influence is undeniable. Further evidence of this accelerating expansion is found in the cosmic microwave background radiation, which offers a snapshot of how matter was distributed in the early universe. These observations are consistent with models that predict an accelerating expansion. Thus, the story of the universe's age, size, and expansion is not only a tale of the past, but also a glimpse into the ongoing mysteries that continue to unfold. Through these discoveries, we not only learn about the cosmos, but also about the very forces shaping its future. In recent years, galaxy surveys and observations of the large-scale structure of the universe have provided us with deeper insights into a phenomenon that continues to challenge our understanding. Studies of galaxy clusters, along with their distribution over time, reveal patterns that strongly align with the concept of an accelerating universe. This acceleration, propelled by the mysterious force of dark energy, has revolutionized the way we perceive the cosmos. Collectively, these observations have transformed our conception of the universe, showing that not only is it expanding, but it is doing so at an ever-increasing rate. This discovery has forced us to reconsider fundamental ideas about gravity and has spurred an intense wave of research into the true nature of dark energy. At the same time, cosmic voids, enormous, relatively empty regions of space, have been identified as one of the most significant features of the large-scale structure of the universe. These vast voids are sparsely populated with galaxies and serve as a key puzzle piece in understanding how the universe has evolved. The formation of these voids is intricately tied to the gravitational dynamics of dark matter and the early stages of the universe's development. In the aftermath of the Big Bang, the universe was nearly uniform, with only slight fluctuations in density. Over time, gravity began pulling matter together, creating denser regions that would later become galaxies and galaxy clusters. As matter accumulated in these areas, the surrounding regions, which did not experience enough gravitational attraction, remained emptier. This imbalance led to the formation of voids, regions of space that lacked enough matter to become dense enough for galaxies to form. These voids, although seemingly empty, have grown larger over cosmic time as the structures of the universe continue to develop. They stand as a reflection of the uneven distribution of matter throughout the universe's history. As galaxies within clusters merge and grow, the gravitational influence of these clusters continues to pull material from the voids, making them even emptier. This process, known as the chimney effect, funnels matter from the low-density void regions into higher-density areas, thereby amplifying the emptiness of the voids. Over time, the dynamics within these voids have an intriguing impact on the evolution of galaxies. Galaxies residing within voids often exhibit distinct characteristics, such as irregular shapes and lower star formation rates when compared to those in denser environments. Observations suggest that galaxies in voids may be more spread out, with fewer neighboring galaxies, implying a more dispersed cosmic evolution. Void formation and evolution are deeply intertwined with gravitational forces, the growth of cosmic structures, and the distribution of dark matter. While they mark the vast emptiness in the universe, voids also offer vital clues about the processes governing galaxy formation and the behavior of matter in an ever-expanding universe. Meanwhile, magnetic fields, which permeate every corner of the cosmos, play a fundamental role in shaping cosmic structures. These fields influence everything from the formation of galaxies to the dynamics of stars. Present across the interstellar and intergalactic mediums, magnetic fields are present throughout the universe. Though their origins remain an area of active research, it is believed that they first emerged through processes in the early universe and the movement of charged particles. As galaxies evolve, these magnetic fields contribute to their overall structure and stability by affecting the behavior of gas and dust, two essential components for star formation. When gas clouds collapse under gravity to form stars, magnetic fields can regulate this process by providing additional pressure, sometimes enhancing star formation and, at other times, inhibiting it. This interaction helps shape a more complex cosmic architecture. Beyond galaxies, magnetic fields extend into galaxy clusters, where they influence the movement of plasma, a hot, ionized state of matter. Interactions between charged particles in the plasma and the magnetic fields can give rise to various phenomena, including the emission of radio waves, further expanding our understanding of the universe. These magnetic fields also play a crucial role in guiding cosmic rays, high-energy particles traveling near the speed of light. Their influence helps shape the behavior of these particles as they journey across vast stretches of space. Magnetic fields, therefore, are integral to the structure and dynamics of the universe. They govern the formation and stability of galaxies and play a pivotal role in how matter behaves across the largest scales. As telescopes and instruments continue to probe deeper into space, our understanding of these invisible forces and their interaction with visible matter will continue to evolve, revealing more about the complex workings of the universe. Meanwhile, the quest to understand exoplanets, planets orbiting stars outside our solar system, has become one of the most exciting frontiers in astronomy. Astronomers have developed a range of innovative techniques to detect these distant worlds, providing us with new insights into the potential for alien life. With each discovery, we come closer to answering one of humanity's most profound questions. Are we alone in the universe? Astronomers have developed a variety of techniques to uncover the mysteries of exoplanets, each offering unique insights into these distant worlds. One of the most well-known methods is the transit technique, where astronomers carefully observe a star's brightness for any small periodic dips. These dips occur when an exoplanet passes in front of its host star, blocking a fraction of its light from our vantage point on Earth. By monitoring these fluctuations in brightness over time, astronomers can deduce crucial information such as the size of the planet and the length of its orbital period. This method has proven essential in the search for exoplanets, providing a wealth of data from far-flung corners of the galaxy. Another widely used technique is the radial velocity method, also known as the Doppler method. This approach is based on the gravitational pull that an exoplanet exerts on its star. As a planet orbits, it causes its star to experience a slight wobble due to their mutual gravitational attraction. The motion of the star, toward or away from us, shifts its light spectrum. When the star moves closer to Earth, the light becomes blue shifted, and when it moves away, it becomes red shifted. By measuring these shifts, astronomers can not only detect the presence of a planet, but also estimate its mass, providing valuable data on its potential characteristics. While the above methods rely on indirect observations, direct imaging of exoplanets remains an exciting but challenging avenue of research. The brightness of stars often overshadows the planets, making it difficult to capture clear images. To overcome this, astronomers use advanced technologies such as coronagraphy and adaptive optics. These techniques allow them to block out the overwhelming light of the star while isolating the fainter light reflected or emitted by the exoplanet. This method is particularly useful for studying large exoplanets situated far from their stars, providing insights into their atmospheres and even their potential for habitability. In recent years, gravitational microlensing has emerged as another powerful technique. This method exploits the phenomenon of gravitational lensing, where massive objects like stars bend the light from more distant objects due to their immense gravitational pull. When a star passes in front of a more distant one, its gravity can magnify the distant star's light. If the foreground star has an exoplanet, the light curve, essentially the pattern of the star's light, reveals distinct features that indicate the planet's presence. This method is particularly valuable for detecting planets that are too faint or too distant for other techniques to detect, opening up new possibilities in the search for distant exoplanets. As technology continues to advance, these methods will evolve, enhancing our ability to explore and understand the diverse worlds beyond our solar system. The quest to determine the habitability of exoplanets remains one of the most exciting frontiers in astronomy. Identifying planets that could support life hinges on a careful analysis of several environmental factors, starting with the concept of the habitable zone, often called the Goldilocks zone. This is the region around a star where conditions are just right for liquid water to exist on a planet's surface. Water, essential for life as we know it, makes this zone a critical focus for astronomers searching for potentially habitable exoplanets. Beyond location, the composition of an exoplanet's atmosphere plays a vital role in its potential to support life. Atmospheric gases, including carbon dioxide, oxygen, and methane, are key indicators that could suggest a stable climate conducive to liquid water. By analyzing light spectra captured by spacecraft and ground observatories, scientists can detect the presence of these gases, gaining insights into a planet's atmospheric conditions and any potential biosignatures, clues that may hint at the existence of life. Geological factors also contribute to our understanding of habitability. For example, the presence of plate tectonics on a planet may be crucial for the recycling of nutrients and the maintenance of a dynamic climate, both factors that could support life. Evaluating a planet's surface conditions, such as temperature, pressure, and geological activity, helps scientists predict whether such an environment could foster the development of living organisms. By considering all of these factors together, astronomers can piece together a picture of a planet's potential to harbor life, expanding our understanding of the universe and the many worlds within it. Recent breakthroughs in astrobiology have pushed the boundaries of what we once thought was necessary for life. As our search for extraterrestrial life expands, scientists are beginning to explore the possibility of life that doesn't rely on water in the way we understand it. Some theories now consider the idea that life could be based on substances like ammonia or even silicon, rather than the familiar carbon and water we associate with life on Earth. As the quest for exoplanets intensifies with the help of cutting-edge technology, our definitions of habitability are evolving, potentially allowing for a far broader spectrum of environments to be considered as havens for life. In this rapidly advancing field, certain exoplanets have emerged as prime candidates for hosting life, as we know it. One of the most compelling is Proxima Centauri b, which orbits Proxima Centauri, the closest known star to our Sun. Nestled in the star's habitable zone, this exoplanet presents conditions that could theoretically support liquid water on its surface. However, its proximity to a flare-active star raises concerns about the retention of its atmosphere, as intense radiation could strip away the very conditions needed for long-term habitability. While still a tantalizing prospect, Proxima Centauri b's potential for sustaining life remains a subject of intense scrutiny. Then there's Kepler 1a6f, the first Earth-sized exoplanet discovered within the habitable zone of a star that mirrors the Sun. Located in the Kepler 186 system, this planet's size and distance from its star suggest that it may possess the right conditions to harbor liquid water, making it a prime candidate for future exploration. The planet's atmospheric composition and surface conditions could hold the key to understanding whether it could support life, making it an exciting target for the next generation of telescopes. Adding further intrigue is the TRAPPIST-1 system, a collection of 7 Earth-sized exoplanets orbiting a cool dwarf star. 3 of these planets fall within the star's habitable zone, where temperatures may be suitable for liquid water to exist. This diversity presents a fascinating opportunity for scientists to study various environmental conditions, offering critical insights into the factors that support life. The system's unusual arrangement of multiple planets in tight orbits makes it even more intriguing, as it holds the potential to reveal how different planets could coexist in a relatively small space, perhaps under conditions vastly different from those in our own solar system. Another exoplanet drawing significant attention is LHS 1140b. Located in the habitable zone of its parent star, LHS 1140b stands out due to its size. This super-Earth planet's larger mass might mean a thicker atmosphere, which could increase its chances of retaining heat. Its proximity to Earth, combined with its relatively favorable characteristics, makes it an ideal candidate for more detailed observations, particularly with the powerful telescopes on the horizon. These observations could potentially reveal whether this exoplanet might harbor the conditions needed for life. Each of these exoplanets presents unique opportunities to deepen our understanding of the cosmos. Studying them could reshape our conception of life beyond Earth and help refine our criteria for habitability. The variety and complexity of exoplanetary systems observed so far challenge many of our long-held assumptions about planetary formation, revealing a universe that's far more dynamic and diverse than previously imagined. Exoplanetary systems show an incredible variety that sets them apart from our solar system. One of the most astonishing differences is the prevalence of hot Jupiters, massive gas giants that orbit incredibly close to their host stars. This contrasts sharply with our solar system, where gas giants like Jupiter and Saturn orbit much farther from the Sun. Scientists believe that these close-orbiting gas giants may have migrated inward over time due to gravitational interactions, providing new perspectives on how planetary systems can evolve. Furthermore, the way planets are arranged in many exoplanetary systems can differ greatly from the patterns seen in our own solar system. Some systems feature tightly packed planets in close orbits, forming more compact configurations compared to our own spacious arrangement. In a few cases, these planets engage in resonant orbits, where their gravitational pull creates a harmonious, rhythmic pattern of motion. These dynamic interactions are rarely seen in our solar system and hint at the fascinating complexity of other star systems. The diversity of planetary types and their compositions only adds to the wonder. Our solar system includes terrestrial planets like Earth and Mars, along with gas giants. In contrast, many detected exoplanets, particularly super-Earths and mini-Neptunes, have distinct sizes and atmospheric characteristics that don't directly correlate with any of the planets in our solar system. These exoplanets often possess thick hydrogen-helium atmospheres or rocky compositions, opening the door to entirely new hypotheses about planetary formation and the factors that drive planetary development. As we discover more, we are forced to rethink not only what makes a planet habitable, but also how planets form and evolve over time. The vast diversity of planetary systems scattered across different types of stars adds an exciting layer of complexity to the ongoing search for extraterrestrial life. One of the most intriguing revelations comes from the discovery of exoplanetary systems orbiting M-type red dwarfs. These stars, which dominate our galaxy, vastly outnumber stars like our Sun. However, they differ significantly in their temperature and luminosity, casting a unique shadow over the habitable zones that surround them. These variances shape the potential climates of planets within these zones, which, in turn, influences their ability to support life as we know it. By studying these differences, scientists hope to unlock essential clues about how planetary systems form and evolve, and what conditions might foster life beyond Earth. These explorations dive deep into the heart of the Fermi paradox, a conundrum that captures the contradictions between the high probability of extraterrestrial civilizations and our utter lack of evidence for them. Named after physicist Enrico Fermi, the paradox famously asks, "Where is everybody?" Given the vast number of potentially habitable planets in our galaxy alone, billions by some estimates, one might reasonably expect that by now, humanity should have encountered signs of intelligent life. Yet despite decades of searching, we've found no definitive proof. Several theories attempt to resolve this paradox. One possibility suggests that intelligent life is exceptionally rare. While microbial life may be widespread across the cosmos, the leap from simple organisms to more complex forms of life and eventually to advanced spacefaring civilizations could be a rare and even unique event in the history of the universe. This perspective paints a picture of the universe teeming with microbial life, but relatively devoid of technologically advanced beings. Another hypothesis revolves around the idea of the Great Filter. This suggests that advanced civilizations may not last long enough to make contact because they tend to self-destruct before reaching the technological capacity needed for interstellar communication. Catastrophic events like nuclear wars, environmental collapse, or technological disasters could strike civilizations at crucial stages in their development, preventing them from surviving long enough to colonize the galaxy. If this filter exists, it may occur at different stages of a civilization's life cycle, explaining the absence of detectable signals from other intelligent beings. An alternative theory is that advanced civilizations are indeed out there, but they may be deliberately avoiding contact. This could be driven by a variety of motives, such as a desire not to interfere with less developed civilizations, or a belief that revealing their presence would disrupt the natural evolutionary trajectory of emerging species. This line of thinking aligns with concepts from science fiction, such as the Prime Directive, where extraterrestrial civilizations adhere to a cosmic code of ethics that forbids direct contact with primitive civilizations. Finally, another possibility is that we simply haven't recognized the signs of extraterrestrial intelligence. It's possible that advanced civilizations communicate in ways or use technologies that are far beyond our current scientific understanding. Maybe the life forms we're searching for don't even resemble anything we consider life. They might exist in forms or environments so radically different from what we know that they remain completely undetectable by our methods. As our technology advances and our understanding of life broadens, the search for extraterrestrial intelligence may open entirely new perspectives on the Fermi paradox, pushing the boundaries of our cosmic exploration. The mystery of why we haven't yet encountered other civilizations continues to inspire scientists and dreamers alike, urging us to look deeper into the void. The evolution of life on planets orbiting red dwarf stars presents a fascinating set of challenges and possibilities. These stars are the most common type in the universe, making up roughly 75% of all stars. However, their cooler, dimmer nature contrasts sharply with the warmth and brilliance of stars like our Sun. This difference in stellar output leads to habitable zones much closer to the star, creating a radically different environment for any planets that might reside within these zones. One of the key factors to consider is the impact of stellar activity. Red dwarfs are notorious for their intense stellar flares and magnetic storms, which can unleash harmful radiation onto nearby planets. For any planet positioned within the habitable zone of such a star, the radiation could be so overwhelming that it might strip away the planet's atmosphere, making the development of life incredibly difficult. However, life might not be completely out of the question. In this hostile environment, organisms could adapt in surprising ways, developing protective mechanisms to withstand the harsh radiation. Some species might evolve thicker protective outer layers, while others could develop biochemical processes that shield them from the radiation's harmful effects. These adaptations present the possibility of a very different form of life, one that can survive in conditions that would be inhospitable to life on Earth. Life on red dwarf planets could offer us a glimpse into the extraordinary potential for diversity in the universe, challenging our assumptions about what makes a planet habitable and what forms life might take in the vast reaches of space. Tidal locking, a fascinating phenomenon often observed in planets orbiting red dwarf stars, brings about a peculiar kind of relationship between a planet and its star. In this scenario, a planet rotates on its axis in such a way that one hemisphere is constantly facing the star, while the other side remains in eternal darkness. The stark contrast between these two extremes of light and heat could create a world of extraordinary extremes. On the illuminated side, temperatures might soar to unbearable heights, while the dark side could descend into an icy wasteland. However, the possibilities for life on such planets are far from bleak. The severe temperature differences might give rise to unique biological adaptations. Life, if it were to emerge, would likely find refuge in a thin twilight zone at the boundary between light and darkness, where the temperatures are more moderate and conditions are more favorable for life to flourish. In this narrow strip of land, where the interplay of light and shadow creates a rich gradient of heat, life could evolve in ways that we can scarcely imagine, potentially leading to a diverse range of organisms adapted to these extreme conditions. The potential for liquid water to exist on these planets adds a hopeful twist to the story. Despite the vast temperature differences, liquid water could persist along the terminator, the boundary between day and night. Here, water would remain in a liquid state, offering an oasis for life to develop. The existence of water, a vital ingredient for life as we know it, would significantly increase the likelihood of life evolving, even in the face of such extremes. This boundary could be the cradle for organisms that are highly specialized to survive in this unique environment. The conditions could foster a specialized ecosystem, teeming with life forms that have evolved to thrive in narrow ecological niches, making this region a marvel of adaptation. Though planets around red dwarf stars present many challenges, life is far from impossible. The diverse pressures of radiation, extreme temperatures, and resource scarcity could push evolution to create organisms with remarkable resilience and highly specific adaptations. The study of such possibilities forces us to rethink what life could look like in the far reaches of the galaxy and expands our understanding of life's adaptability and resilience. This exploration broadens the horizons of where and how life could exist beyond the confines of our solar system. At the heart of this investigation is the search for biosignatures, distinct markers of past or present biological activity. These indicators offer a glimpse into the possibility of life elsewhere in the universe. Biosignatures come in many forms, including particular molecules, atmospheric patterns, or even surface features that suggest the presence of life. For scientists, identifying these signatures is a crucial part of astrobiology. It helps them pinpoint planets that may harbor life or may have supported life at some point in their history. Spectroscopy is one of the most vital tools in the hunt for biosignatures. By studying the light that passes through a planet's atmosphere, scientists can identify specific wavelengths of light that are absorbed by various molecules. This creates a spectral fingerprint, unique to the planet in question. By analyzing this fingerprint, researchers can detect gases commonly associated with biological processes, such as oxygen, methane, nitrous oxide, and ozone. The simultaneous presence of these gases, particularly when generated by biological sources, can serve as compelling evidence that life exists or has existed on a distant world. Thanks to advances in telescope technology, the search for biosignatures is becoming more refined. Both ground-based and space-based observatories now house highly sensitive spectrometers capable of conducting these detailed analyses. The James Webb Space Telescope, set to revolutionize our understanding of distant worlds, will have the capacity to analyze the atmospheres of exoplanets, especially those situated in their star's habitable zone. These observations will provide crucial data on factors such as temperature, pressure, and chemical composition, allowing researchers to detect potential biosignatures more effectively. Surface features, too, provide valuable clues. Evidence of vegetation or organic materials on a planet's surface could hint at the presence of life. For example, the detection of chlorophyll-like molecules could point to photosynthetic organisms, much like the plants that sustain life on Earth. Such findings would be a monumental step in our quest to answer one of the most profound questions of our time. Is life unique to Earth, or could it be found in the vast expanse of the universe? In the vast expanse of the cosmos, the search for signs of life beyond Earth hinges on intricate and complex processes. Variations in surface colors or textures on exoplanets could point toward biological activity, distinguishing them from purely geological phenomena. However, despite the promising methods for detecting biosignatures, interpreting the data remains a challenging task. The signatures observed may not always be the result of biological processes. They could also be produced by abiotic or non-living forces. This adds layers of complexity to conclusions drawn from spectroscopy or surface analysis, urging researchers to proceed cautiously. Often, confirming the presence of life requires multiple lines of evidence to support a hypothesis. As technology continues to advance and our understanding of biosignatures deepens, the search for life beyond Earth will undoubtedly grow more refined. We can expect new, nuanced approaches to unraveling the mysteries of distant worlds. This will open exciting avenues for exploration, offering us the opportunity to answer one of the most profound questions of human existence. Are we alone in the universe? The formation of exoplanets begins in the heart of a protoplanetary disk, a vast, rotating cloud of gas and dust surrounding a young star. This process begins as particles in the disk coalesce under the influence of gravitational forces. These solid particles collide and stick together, gradually forming larger bodies. Over time, these clusters evolve into planetesimals, some of which can reach sizes of several kilometers. As planetesimals continue to collide and merge, they build up into protoplanets, which are the building blocks of fully formed planets. Once a protoplanet reaches a certain size, its gravitational pull becomes strong enough to attract more material from the surrounding disk. This phase can lead to the formation of gas giants, where the protoplanet captures significant amounts of gas, primarily hydrogen and helium. In contrast, terrestrial planets like Earth are formed primarily from rocky material, with only a thin layer of residual gases remaining in their atmospheres. Migration is a pivotal aspect of exoplanetary evolution. Many exoplanets do not remain in the locations where they were initially formed, instead drifting away from their original positions. This migration is influenced by interactions within the protoplanetary disk. As a planet forms, it creates gravitational disturbances in the disk, altering the distribution of gas and dust around it. These disturbances can result in a transfer of angular momentum, causing the planet to migrate either inward toward the star or outward toward the colder regions of the disk. One well-known migration mechanism is called Type 1 migration. This mechanism primarily affects smaller planets, such as those roughly the size of Earth, as they interact with the gas in the disk. Larger planets, on the other hand, can experience Type 2 migration, where they clear a path through the disk, resulting in more significant movement toward the star. The density of the disk also plays a crucial role in migration. If the disk becomes less dense over time, the gravitational interactions that facilitate migration can change. Some planets may become more stable, while others could shift significantly in position. These migration processes contribute to the diverse configurations seen within exoplanetary systems today. For example, the existence of hot Jupiters, gas giants found in close proximity to their stars, suggests that these planets likely migrated inward after forming in cooler regions of their protoplanetary disks. Understanding how exoplanets form, migrate, and evolve offers researchers valuable insights into their characteristics and orbits. It helps piece together the varied histories that shape the countless planetary systems we observe, enriching our understanding of the universe and the dynamics of planetary formation. Interstellar communication with potential alien civilizations is a captivating topic that stretches the limits of our imagination. It involves a range of innovative methods, each reflecting humanity's current technological capabilities and our deepening understanding of how intelligent life might communicate across the vast expanse of space. These methods are as varied as they are bold, envisioning everything from radio waves to laser pulses, physical probes, and even using the stars themselves to send messages. One of the simplest and most well-known methods is the transmission of radio waves. This approach has been actively pursued through initiatives like the Search for Extraterrestrial Intelligence, SETI, where radio signals are broadcast and monitored across specific frequency bands. These frequencies are chosen because they are typically associated with intelligent communication. By focusing on these bands, scientists hope to detect signals that might indicate extraterrestrial activity. This method is grounded in the idea that alien civilizations, much like us, would use radio waves to communicate, making them a natural candidate for interstellar messaging. Another promising method involves laser communication, which offers several advantages over traditional radio waves. Lasers can be highly focused, sending powerful beams of light with minimal dispersion over vast distances. The precision of laser pulses means they can travel further with less interference from cosmic noise. Scientists have proposed sending these laser signals toward nearby star systems. If an alien civilization detects such a signal, the potential for two-way communication could be vastly improved. Unlike radio waves, the narrow focus of lasers allows for more accurate, direct communication, making it an appealing method for interstellar messaging. But what if we could send physical probes? The idea of dispatching small, unmanned spacecraft to neighboring star systems has also gained traction, though the technology to do so remains in its infancy. These probes, equipped with communication instruments, could transmit data back to Earth and, potentially, even carry messages intended for any intelligent life forms they might encounter. Projects like Breakthrough Starshot are working toward developing advanced propulsion systems that could send these tiny, lightweight probes to nearby stars at a fraction of the speed of light. This could lead to direct exploration of distant star systems and open the door for active communication with extraterrestrial civilizations. In an even more unconventional twist, some have proposed the idea of using natural astronomical phenomena as a medium for communication. Neutron stars, for example, emit highly regular radio pulses as they rotate. These pulses act as natural cosmic clocks, capable of providing incredibly precise timekeeping. If an alien civilization were aware of these pulses, they could theoretically encode messages by altering the timing or modulation of these signals in recognizable patterns. This concept leverages the natural rhythms of the universe itself to create a form of interstellar communication that requires no artificial signals or technology beyond the observation of celestial phenomena. Despite the excitement surrounding these possibilities, one major challenge remains: the vast distances between stars. Even at the speed of light, signals from our closest neighboring star, Proxima Centauri, would take over 4 years to reach Earth. This time delay presents significant hurdles for meaningful, real-time communication. However, as humanity continues to develop new technologies, this barrier may become less insurmountable, allowing us to overcome the immense spatial distances that currently separate us from other civilizations. At the same time, our growing understanding of extreme planetary conditions offers new insights into how alien life might evolve in environments radically different from Earth's. Life on distant planets might adapt to extreme temperatures, high radiation levels, intense atmospheric pressure, or entirely unique chemical compositions. These extreme conditions would challenge life forms to develop novel features and metabolic processes to survive. For example, on a planet with scorching temperatures, life forms might evolve heat-resistant proteins and cellular membranes capable of maintaining integrity under extreme heat. Similarly, species living on frigid planets might develop antifreeze-like compounds to prevent their bodily fluids from freezing, much like the extremophiles found in Earth's polar regions or deep-sea environments. Such evolutionary adaptations could lead to life forms that thrive in environments we would consider inhospitable. Radiation levels, too, could shape the trajectory of life's evolution. On planets close to their stars, where radiation is intense, organisms may evolve protective mechanisms to shield themselves from harmful radiation. These might include physical armor, specialized pigments to absorb damaging radiation, or biochemical pathways designed to repair DNA and cellular damage. Life in such environments might possess highly specialized defenses, allowing them to withstand the harshest conditions. High-pressure environments, such as those found on gas giants or deep ocean worlds, present another challenge. Life in these realms may develop body structures and behaviors uniquely suited to withstand crushing pressures. Organisms could evolve flexible, resilient bodies capable of withstanding the immense weight of their surroundings, or they might adopt entirely new forms that allow them to survive in the crushing depths of these alien worlds. While these concepts of interstellar communication and alien life are fascinating, they remind us of just how much we have yet to learn. The search for extraterrestrial civilizations is more than a quest for communication. It's an exploration into the unknown, asking us to consider how life might exist in ways that defy our current understanding. Each discovery, whether it's a new method for sending messages across the stars or an insight into the conditions that shape life elsewhere, brings us one step closer to unraveling the mysteries of the cosmos. The availability of unique energy sources, such as highly energetic chemical reactions deep within Earth's oceans or near hydrothermal vents, could fuel the emergence of entirely new metabolic pathways, ones not observed in life forms on Earth. Additionally, the chemical environment of a planet plays a crucial role in shaping the life forms that could arise there. On planets with abundant ammonia or methane, scientists hypothesize that life might evolve to harness these substances instead of water, leading to biochemical processes vastly different from what we know. As researchers continue to probe the possibility of life in extreme environments, whether within our solar system or on distant exoplanets, they uncover a staggering array of potential evolutionary outcomes. These unique adaptations challenge our current understanding of life's boundaries, compelling us to rethink the resilience and inventiveness of life across the cosmos. Exploration of such extreme environments brings us closer to understanding life's adaptability. The search for life beyond Earth opens up vast, uncharted territories, ones that invite us to question everything we thought we knew about biology and evolution. Whether life is sustained by methane, ammonia, or an entirely unknown chemical compound, our understanding of life's limits grows ever more complex. Every new discovery adds a layer to our appreciation of life's tenacity, inspiring awe at the boundless creativity of evolution. Turning to the mysteries of our own solar system, one of the most intriguing puzzles is the existence of Planet 9. While direct visual confirmation remains elusive, there is mounting indirect evidence to support its presence. Scientists have noted the unusual orbits of distant objects beyond Neptune, called trans-Neptunian objects, which exhibit strikingly anomalous trajectories. These bodies often follow highly elliptical orbits that are tilted at odd angles relative to the solar plane, suggesting an external gravitational influence. The most likely candidate for this force is a large unseen planet. One compelling piece of evidence lies in the clustering of these distant objects. Research has shown that the orbits of several of them align in a way that cannot be easily explained by the gravitational pull of known planets. This clustering hints at the presence of an undiscovered planet that could be exerting a gravitational force strong enough to cause these objects to congregate in a particular region of space. Simulations have suggested that a planet roughly 5 to 10 times the mass of Earth, located far beyond Pluto, could be responsible for these peculiar orbital patterns. The estimated size and position of this hypothetical Planet 9 also suggests that it may be situated in the outermost reaches of our solar system on a highly elongated orbit that takes it several hundred to thousands of astronomical units from the Sun. This extreme distance would make it nearly impossible to detect using current telescopes, as it would reflect very little sunlight. Despite this challenge, its gravitational influence could explain the erratic behavior of these distant bodies. Currently, no direct visual evidence of Planet 9 has been observed. However, astronomers are not deterred. Using powerful telescopes, they continue to scan the sky for signs of this elusive planet. Sky surveys are actively collecting data that may one day either confirm or rule out its existence. For now, the peculiar orbits of distant solar system objects remain the most compelling evidence, keeping the scientific community intrigued and focused on unraveling this cosmic mystery. This ongoing search reflects our enduring quest to understand the architecture and dynamics of our solar system. The formation of Earth's moon, too, remains one of the greatest enigmas of planetary science. The prevailing theory, known as the giant impact hypothesis, suggests that the moon was born from a cataclysmic collision between the early Earth and a Mars-sized body, often referred to as Theia. This dramatic event, believed to have occurred around 4.5 billion years ago, would have sent vast amounts of debris into space, material from both Earth and Theia. Under the force of gravity, this debris eventually coalesced to form the moon. The impact that led to the moon's creation had profound consequences for Earth. Not only did it result in the formation of our natural satellite, but it also altered the rotation of our planet. In the immediate aftermath of the collision, Earth would have rotated much more rapidly, and the intense heat generated by the impact would have caused the surface to become molten. As Earth cooled, the moon began to stabilize in orbit, gradually moving away from the planet over millions of years. This interaction between Earth and the moon continues to influence our planet in remarkable ways. One of the most notable effects is the creation of tides. The moon's gravitational pull on Earth drives the movement of ocean waters, leading to tidal patterns that shape coastal ecosystems. These tidal forces are not merely a curious phenomenon. They are vital for the mixing of nutrients in the oceans, promoting biological diversity and contributing to evolutionary processes over geological timescales. Through this delicate interplay, the moon has played a key role in shaping life on Earth, underscoring the profound and lasting impact celestial events can have on the evolution of our planet. The moon's presence in Earth's orbit plays a crucial role in shaping the conditions we associate with life on our planet. Not only does it stabilize Earth's axial tilt, moderating climate fluctuations and seasonal changes, but this gravitational influence has also created a more hospitable environment for life to thrive. This delicate balance, made possible by the moon's gravitational pull, has allowed Earth to develop a climate that supports the diverse ecosystems we rely on today. The moon's origin and subsequent effects on Earth's geology go far beyond simple lunar formation. The violent collisions that led to the moon's creation left a lasting imprint on its surface, resulting in the heavily cratered landscape we observe today. These craters are more than just lunar features. They serve as a visual record of the turbulent early days of the solar system. By studying these lunar scars, scientists have been able to piece together a history of both the moon and Earth's geological evolution. The moon's formation, far from being a one-time event, has become integral in shaping the conditions that allowed life on Earth to take root. Its gravitational and tidal interactions continue to influence our planet's evolution, making it a key player in the story of our world. While the moon stabilizes Earth, a similarly enigmatic phenomenon is occurring on Saturn, a giant hexagonal storm at its north pole. This extraordinary atmospheric feature, stretching nearly 20,000 miles across, is a striking display of fluid dynamics at work. Though the precise mechanisms behind the storm's formation are still under investigation, scientists believe that Saturn's rapid rotation plays a pivotal role in shaping this six-sided structure. The planet spins on its axis once every 10.5 hours, creating powerful jet streams that help shape the atmosphere. These winds, raging at speeds of over 180 miles per hour, generate persistent atmospheric flows that interact with one another, creating regions of low and high pressure. It is within this context that the hexagonal shape begins to take form. The jet stream circling Saturn's northern pole encounters cooler air, setting off a wave pattern that eventually stabilizes into the geometric formation we see today. This interaction mirrors similar fluid dynamics observed in laboratory experiments and rotating fluids, though the exact details of this process remain an active area of research. What makes the hexagonal storm even more fascinating is its variability. Unlike a simple static structure, the hexagon changes over time. Its color and temperature shift with Saturn's seasons, which are a consequence of the planet's axial tilt and its orbit around the Sun. These seasonal variations reflect a dynamic atmospheric system that continues to evolve. Studying this storm provides scientists with valuable insights not only into Saturn's unique atmospheric conditions, but also into the processes that govern planetary weather systems across the universe. Beyond the storm on Saturn lies another significant aspect of our solar system, the Kuiper Belt and Oort cloud. These two regions, situated at the outer edges of the solar system, contain a wide variety of icy bodies and remnants from the early days of the solar system. They are key to understanding the early stages of planetary formation. The Kuiper Belt, located beyond Neptune's orbit, stretches roughly from 30 to 50 astronomical units from the Sun. It is thought to be a repository of material left over after the formation of the planets. This leftover debris includes countless small planetesimals that never coalesced into full-fledged planets. The Kuiper Belt is not just a distant frozen collection of icy bodies. It offers us a glimpse into the primordial processes that gave birth to the planets and other celestial bodies. Both the Kuiper Belt and Oort cloud are vital to understanding the solar system's history, as they are the remnants of the original protoplanetary disk that once surrounded the young Sun. These distant regions hold clues that could unlock secrets about the early solar system and the forces that shape the formation of not just our planet, but the entire system in which it resides. Each of these phenomena, the moon's role in Earth's stability, Saturn's hexagonal storm, and the far reaches of the solar system, provides us with a deeper understanding of the processes that have shaped not only our planet, but the broader cosmic environment that continues to influence us. Additionally, the gravitational influence of Neptune played a pivotal role in shaping the Kuiper Belt. As Neptune migrated outward during the early stages of the solar system's formation, its interactions with icy bodies had a profound impact. Some of these objects were scattered into new orbits, while others were cleared away entirely. This dynamic interplay between Neptune and the surrounding bodies led to the creation of a diverse population of objects, now known as Kuiper Belt objects, KBOs. The Oort cloud, on the other hand, is a more distant, spherical shell of icy bodies believed to extend from about 200 to 1,000 astronomical units from the Sun, and possibly even farther. Its formation is thought to be tied to the later stages of planetary development. The gas giants, particularly during their early orbits, exerted strong gravitational forces that scattered smaller icy bodies into the outermost regions of the solar system. These bodies were pushed beyond the Kuiper belt, eventually forming what we now recognize as the Oort cloud. The Oort cloud is regarded as a remnant of the early solar system, containing material that never coalesced into larger planets. Due to its vast distance from the Sun, the bodies in the Oort cloud have remained relatively unchanged, preserving crucial information about the solar system's infancy. It is also believed to be a primary source of long-period comets. When some of these cometary nuclei are perturbed, potentially by passing stars or the gravitational influence of the Milky Way, they can be nudged inward toward the inner solar system, occasionally giving rise to spectacular cometary displays. Together, the Kuiper belt and Oort cloud serve as vital components of our solar system's architecture. They hold essential clues about the early solar system's conditions and offer insight into the processes that influenced planetary formation and development over billions of years. The origin of water on Earth and other terrestrial planets is a captivating subject shaped by both cosmic events and planetary processes. Scientists propose that water first appeared on Earth through a combination of materials brought by comets and asteroids. These icy bodies, remnants of the early solar system, bombarded Earth during a period known as the Late Heavy Bombardment, which occurred around 4 billion years ago. As these celestial objects collided with the planet, their ice melted, contributing to the accumulation of water on Earth's surface. Another significant source of Earth's water likely stems from volcanic activity. Water trapped within minerals in the Earth's mantle could have been released through volcanic eruptions. This process not only supplied water vapor to the atmosphere, but also played a critical role in the formation of the oceans we see today. The balance between contributions from ice-bearing bodies and volcanic outgassing laid the foundation for a water-rich planet capable of supporting life. When we consider our neighboring terrestrial planets, however, the story diverges. Mercury, for instance, lies too close to the Sun for any substantial amount of water to remain on its surface or in its atmosphere. Venus, with its thick and toxic atmosphere, likely had water early in its history, but experienced a runaway greenhouse effect, which led to the loss of its oceans. Mars, on the other hand, shows compelling evidence of once having abundant water. Signs of ancient riverbeds and polar ice caps suggest that liquid water once flowed across its surface billions of years ago. Today, however, Mars is a vastly different world, with only trace amounts of water remaining in its atmosphere and polar regions. Understanding the origins of water within our solar system not only illuminates Earth's history, but also has profound implications for the search for life beyond our planet. The discovery of places like Europa, one of Jupiter's moons, believed to harbor a subsurface ocean, offers tantalizing possibilities for finding extraterrestrial life and deepening our understanding of the role water plays in shaping planetary environments. The peculiar tilted orbit of Uranus is one of the most intriguing features in our solar system. While most planets follow relatively flat, aligned orbits, Uranus stands out with an axial tilt of approximately 98 degrees. This extreme tilt means that the planet essentially rolls around the Sun on its side. The origin of this unusual orientation is believed to stem from a combination of massive impacts and gravitational interactions during Uranus's formative years. Scientists propose that, early in the solar system's history, Uranus may have been struck by one or more massive celestial bodies, objects roughly the size of Earth. These collisions could have imparted significant angular momentum, nudging the planet into its current tilted position. The energy from such a collision would have been enough to alter Uranus's spin axis dramatically, giving rise to the unique rotation and orbit that we observe today. The gravitational effects from neighboring planets, particularly those in the outer reaches of the solar system, have played a crucial role in shaping Uranus's unusual tilt over millions of years. This complex dance of gravitational interactions, especially with massive bodies like Neptune, has likely influenced the stability and orientation of Uranus's orbit. As the planet's tilt defies conventional expectations, it offers a striking example of the interconnectedness and dynamic nature of our solar system. Uranus's tilted orbit challenges our understanding of planetary formation and offers scientists a unique window into the processes that have shaped the solar system as a whole. By studying such anomalies, astronomers are able to gain a deeper understanding of the diverse evolutionary paths that planets can take, making Uranus an especially fascinating object of study. It forces us to reimagine the forces at work on planets, pushing the boundaries of our knowledge about planetary systems, both within our own cosmic neighborhood and beyond. In a similar vein, Jupiter's Great Red Spot remains one of the most enduring mysteries in planetary science. This colossal storm, larger than the Earth itself, has fascinated scientists for centuries. With winds reaching speeds of about 400 miles per hour, it is a gargantuan anticyclone powered by the planet's rapid rotation and internal heat. The storm's longevity and intensity stem from Jupiter's unique atmospheric structure, primarily composed of hydrogen and helium. These gases, interacting with varying temperatures and concentrations, generate powerful jet streams that fuel enormous storm systems like the Great Red Spot. The Great Red Spot is not simply a fleeting phenomenon, but a storm system that has persisted for at least 350 years. There are even indications that it may be much older, with early reports dating back to the late 17th century. Giovanni Cassini, one of the first astronomers to document the storm, helped establish that it has been a permanent fixture of Jupiter's atmosphere for centuries. However, despite its resilience, recent observations suggest that the storm has been shrinking, leading scientists to explore questions about the stability and future of such atmospheric phenomena. With the arrival of advanced space telescopes and missions such as NASA's Juno spacecraft, our understanding of Jupiter's atmosphere and the Great Red Spot continues to evolve. These studies not only deepen our knowledge of Jupiter itself, but also open up broader avenues of atmospheric science across different planetary systems. The storm serves as a reminder of the complexity and interconnectedness of planetary atmospheres, and by studying it, we gain insights that may one day be applied to exoplanetary science, broadening our understanding of atmospheric dynamics across the universe. The asteroid belt, situated between Mars and Jupiter, stands as a fascinating relic of the early solar system. Formed around 4.6 billion years ago during the coalescing of the planets, the belt is a fragment of what could have been a fully formed planet. However, the gravitational influence of nearby Jupiter disrupted the process. As Jupiter's massive gravitational pull grew, it prevented the material in the region from coming together to form a planet. Instead, it flung many of the objects away, while others became trapped in a state of perpetual motion within the belt. This disruption of accretion processes led to frequent collisions among the remaining objects, breaking them into smaller bodies and forming the asteroid belt we see today. The belt is far from a uniform collection of debris. Rather, it contains a diverse range of objects, from tiny rocks to much larger bodies, like Ceres, which is classified as a dwarf planet. Despite the belt's seemingly dense collection of asteroids, the vast emptiness of space means that these objects are separated by large distances, making the asteroid belt relatively sparse. As a result, the asteroid belt serves as a kind of time capsule, preserving remnants from the early solar system. By analyzing the composition and characteristics of the asteroids, scientists can gain insights into the building blocks of planet formation, providing a snapshot of the conditions that existed in the primordial solar system. This exploration not only enriches our understanding of our own cosmic history, but also fuels the search for resources that could play a crucial role in future space exploration. In the ongoing quest for extraterrestrial life, the possibility of subsurface oceans on icy moons like Europa and Enceladus has captivated scientists. Both moons exhibit compelling evidence of liquid water beneath their icy surfaces, and missions from various space agencies have provided further insights into their potential for harboring life. Europa, in particular, has been the subject of extensive study by spacecraft like Galileo, which revealed key details about its surface and magnetic field. The surface of Europa is marked by cracks and ridges, suggesting that water from beneath the icy crust erupts through the surface, creating new features. These observations strengthen the hypothesis that liquid water exists in the depths of Europa's icy shell, offering an intriguing environment for the possibility of life. As our exploration of these moons continues, the question of whether life could exist in such extreme environments becomes ever more pressing. The search for subsurface oceans not only has profound implications for the search for extraterrestrial life, but also for the future of space exploration, as these moons might one day become key targets in humanity's journey beyond our home planet. Europa's magnetic field measurements have revealed an astonishing layer beneath its icy surface, one that is conductive, possibly saltwater. This suggests a subsurface ocean, one that could be in contact with the rocky mantle below. Such an environment would be ideal for chemical reactions, potentially supporting life. The discovery mirrors that of Enceladus, Saturn's enigmatic moon, where spacecraft observations have uncovered geysers shooting water vapor and ice particles from the moon's south pole. These eruptions provide compelling evidence of a hidden liquid water reservoir beneath Enceladus's icy crust. The composition of the plumes, which contains organic molecules and simple hydrocarbons, hints at a rich and complex subsurface ecosystem. This revelation has led scientists to speculate on the potential for life in the moon's hidden oceans. Both Europa and Enceladus exhibit heat signatures consistent with gravitational models suggesting internal warmth, likely fueled by tidal heating. This heating arises as the moons interact with their parent planets, maintaining liquid water beneath their frozen exteriors. Together, these findings make a strong case for subsurface oceans on both moons. The prospect that these environments could support life is a tantalizing one. With future missions planned to explore these icy worlds, scientists are eager to delve deeper into their secrets, unlocking the mysteries of their hidden oceans and the broader question of life beyond Earth. On the other side of the solar system, Mercury experiences some of the most extreme temperature variations known. Its proximity to the Sun, coupled with a slow rotation and the absence of a significant atmosphere, leads to temperature swings that are staggering. Daytime temperatures can soar to nearly 800 degrees Fahrenheit, while nighttime temperatures plummet to an almost unimaginable -300 degrees Fahrenheit. The primary culprit is Mercury's thin atmosphere, which is too weak to retain heat. Unlike Earth, where the atmosphere helps regulate temperature by trapping heat, Mercury's tenuous atmosphere allows heat to dissipate rapidly once the sun sets. Mercury's unusual day-night cycle exacerbates these extremes. A full rotation on its axis takes about 58 Earth days, while its orbit around the Sun takes approximately 88 Earth days. This means one side of Mercury is exposed to the Sun for an extended period, causing its surface to heat up dramatically before the long night sets in. When the Sun's light finally fades, the temperature can drop precipitously. These temperature extremes pose a significant challenge for any mission to Mercury, requiring equipment capable of enduring both blistering heat and freezing cold. But the extreme conditions also offer scientists a unique opportunity. Understanding how Mercury's surface processes respond to such harsh environments could yield insights into the planet's geological history and surface evolution. Meanwhile, in the realm of space-time and relativity, the Sun's gravity bends light in a remarkable phenomenon known as gravitational lensing. According to Einstein's theory of general relativity, massive objects like stars and galaxies warp the fabric of space-time around them. When light from a distant object passes near one of these massive bodies, its path is altered, curving around the object instead of traveling in a straight line. This bending of light can lead to spectacular visual effects. In some cases, it produces multiple images of the same object, or even a complete ring-like structure known as an Einstein ring. Far from being mere curiosities, these effects serve as powerful tools for astronomers to probe the universe. By studying how light bends around massive objects, scientists can infer crucial information about the galaxies in the foreground and the distribution of dark matter, an elusive substance that accounts for much of the universe's mass. Gravitational lensing also provides a way to observe distant galaxies that would otherwise be too faint or too small to detect. A massive galaxy or galaxy cluster can act as a cosmic lens, amplifying and distorting the light from galaxies far behind it, making them visible to telescopes. This phenomenon has opened new frontiers in the study of the early universe, offering clues about the formation of galaxies and the evolution of cosmic structures. The implications of gravitational lensing stretch far beyond simply observing distant objects. It gives us a glimpse into the nature of dark matter, the expansion of the universe, and the intricate distribution of matter across the cosmos. In this way, gravitational lensing serves as a profound reminder of how the universe's vast structures influence each other, shaping the very path that light travels across the immense expanse of space. Through this lens, we gain deeper insight into the interconnectedness of the cosmos and our place within it. Time dilation is one of the most captivating phenomena explored in Einstein's theory of relativity. It reveals how time itself is not a fixed, universal constant, but a variable that bends and stretches depending on two key factors: relative speed and gravitational influence. According to this groundbreaking theory, time slows down for objects in motion compared to those at rest. Moreover, it also ticks slower when under the influence of strong gravitational fields. This concept takes on a whole new significance in the context of space travel. Astronauts traveling at high velocities or near powerful gravitational sources could experience time in a completely different way than people on Earth. Imagine a spacecraft hurtling through space at a speed close to the speed of light. For the astronauts aboard, only a few years might pass, while back on Earth, many more years could unfold. The result? The astronauts would return home significantly younger than their counterparts who stayed behind. This idea has been vividly illustrated through thought experiments such as the twins paradox, where one twin ventures into space and upon returning finds themselves decades younger than the twin who remained on Earth. Gravitational time dilation adds another layer of complexity. Consider astronauts conducting missions near celestial giants, black holes, for example. These enormous objects warp the fabric of space-time so intensely that time aboard a spacecraft in their proximity would slow down relative to clocks on Earth. For missions orbiting planets or traveling in low Earth orbit, these effects are imperceptible. But for long-distance space travel or deep space missions near massive bodies, the impact of time dilation becomes significant, affecting everything from mission planning to astronaut well-being. As humanity begins to chart courses for missions to Mars and perhaps even farther, these relativistic effects must be carefully considered, not only in terms of the logistical challenges of such long-duration voyages, but also for the mental and psychological toll on those who experience time passing differently. Time dilation serves as a powerful reminder of the interconnectedness of time and space, providing a lens through which we gain profound insights into the universe. Gravitational waves, another of Einstein's predictions, offer yet another window into the strange, dynamic nature of the cosmos. These ripples in space-time are caused by some of the most violent and energetic events in the universe. When massive objects, such as black holes or neutron stars, collide or orbit each other, they send out gravitational waves that travel outward at the speed of light. These waves distort space-time, stretching and compressing the space they pass through. It's similar to the effect seen when a stone is thrown into a pond, creating ripples that spread across the water's surface. As gravitational waves move through space, they create distortions that stretch distances in one direction while compressing them in another. The challenge lies in detecting these minuscule changes. Gravitational waves are so subtle that for years their existence was only theoretical. It wasn't until the advent of highly sensitive instruments like LIGO and Virgo that we were able to capture their signals. The detection of gravitational waves marked a monumental achievement in physics, transforming our understanding of the universe. These waves provide an entirely new way of observing cosmic events, shedding light on phenomena such as black hole mergers, the collision of neutron stars, and even the dynamics behind supernova explosions. Unlike traditional telescopes, which capture light across the electromagnetic spectrum, gravitational wave detectors allow us to hear the universe, revealing insights that are otherwise invisible to our conventional senses. The implications of gravitational wave astronomy are profound. By studying the wave's origins, we can learn about the masses, spins, and orbital movements of the objects that produce them. This level of insight enhances our understanding of galactic formation, the evolution of stellar bodies, and the nature of the forces that govern the cosmos. Ultimately, the discovery of gravitational waves provides us with a deeper understanding of the fabric of space itself, unveiling a layer of reality that was once hidden from view. As we continue to explore this new frontier, our perception of the universe will be forever transformed, opening up possibilities that once seemed the stuff of science fiction. Frame dragging, governed by the dynamics of space-time itself, is one of the most captivating aspects of Einstein's theory of general relativity. This phenomenon occurs when a massive, rotating object, like a planet or a star, exerts an influence on the space-time fabric around it. It's not just the object's mass that curves space-time. The very rotation of the object pulls space-time along with it. Imagine space-time as a vast, stretchy fabric. As the object spins, it twists and tugs on the fabric, dragging it in the direction of the spin. To visualize frame dragging, think of a figure skater spinning. As they rotate, the air around them is also pulled into motion, spiraling along with their movement. Similarly, when a massive object such as Earth rotates, it drags the surrounding space-time, altering the motion of nearby objects, including light itself. This subtle but powerful effect is most evident in satellites orbiting Earth. One of the earliest demonstrations of frame dragging was observed in the orbits of the Laos satellites. These satellites showed minute shifts in their trajectories, caused by the warping of space-time due to Earth's rotation, exactly as predicted by Einstein's general relativity. Further evidence came from the Gravity Probe B mission, which measured tiny shifts in the direction of a gyroscope mounted in orbit around Earth. The results provided direct confirmation of frame dragging, offering a glimpse into the way gravity functions at the deepest levels. Understanding this phenomenon has profound implications for astrophysics, especially in environments close to rotating black holes. In these extreme regions, frame dragging effects are so intense that they give rise to the ergosphere, a region surrounding a black hole where space-time is twisted so severely that even light is unable to escape. The concept of frame dragging extends beyond the exotic environments near black holes. It fundamentally alters our understanding of motion, gravity, and the very structure of the universe. As scientists continue to explore these effects, they uncover more about how the universe operates at its core. The expansion of the universe adds another layer to our understanding of space-time. According to the Big Bang theory, the universe has been expanding since its inception, approximately 13.8 billion years ago. This expansion is not merely the movement of galaxies through space, it is the stretching of space itself, carrying galaxies away from each other. Over time, this stretching increases the distances between galaxies, creating the observable phenomenon known as redshift. As galaxies recede from us, the light they emit shifts to the red end of the spectrum, revealing how much they've moved away. This stretching of space-time has a direct impact on our perception of distances and the relationships between celestial objects. Space is no longer a static backdrop, it's a dynamic, ever-changing fabric. As galaxies move further apart, the time it takes for their light to reach us increases, creating an observable horizon beyond which we cannot see. This also has profound implications for the future of the universe. If the expansion continues to accelerate, as current observations suggest, due to dark energy, the universe could eventually reach a state known as the Big Freeze, where galaxies become increasingly isolated over billions of years. On the other hand, if the expansion slows down or reverses, the universe might face a big crunch, where it collapses back on itself. In either case, the expansion of the universe underscores the fluid, dynamic nature of space-time. It challenges our conventional notions of distance and motion, revealing that the very fabric of the cosmos is not fixed, but ever evolving. By understanding these cosmic principles, we begin to unravel the fundamental laws that govern the universe, providing deeper insights into how reality itself is structured. Wormholes, another mind-bending concept from general relativity, present a theoretical method of traversing vast distances in space-time. These hypothetical passages, often referred to as shortcuts, could connect distant regions of the universe, offering a much quicker route than traveling through conventional space. The idea of wormholes emerges from Einstein's equations, which suggest the possibility of tunnel-like structures linking two separate points in space and time. To illustrate, imagine a flat sheet of paper. Normally, traveling between 2 points would require you to move across its surface. However, if you could fold the paper in such a way that the 2 points meet, you would shorten the journey considerably. A wormhole works similarly, allowing a spacecraft to effectively take a shortcut through space-time, bypassing the intervening space entirely. The allure of wormholes lies in their potential to enable faster-than-light travel. If a spacecraft could navigate through a wormhole, it wouldn't be breaking the fundamental speed limit set by the speed of light. Instead, it would be moving through a shortcut in the fabric of space-time, bypassing the vast distances between distant stars and galaxies. While we are far from being able to build or travel through wormholes, the theoretical possibilities they present open up an exciting frontier in the realm of interstellar exploration, potentially revolutionizing the way we think about travel across the cosmos. However, the theoretical existence of wormholes presents significant challenges. For one, the stability of a wormhole is a major concern. Most solutions to the equation suggest that these cosmic shortcuts would be unstable, collapsing long before anything could traverse them. To keep a wormhole open, a form of exotic matter with negative energy density would be required. This hypothetical matter has yet to be discovered or understood by contemporary physics. Without it, wormholes remain firmly within the realm of speculation. Yet, despite their purely theoretical nature, wormholes pose compelling questions about the very structure of space-time and the limits of our understanding of the universe. They offer tantalizing glimpses into possible shortcuts for interstellar travel, but for now, their practical application remains confined to science fiction. Continued research into the properties of space-time may one day provide new insights into whether wormholes could indeed become pathways to the stars. But as of now, the quest for understanding these exotic phenomena continues to push the boundaries of what we know about the cosmos. Time behaves in curious ways within the intense embrace of strong gravitational fields, a phenomenon known as gravitational time dilation. This concept is rooted in Einstein's theory of general relativity, which revolutionized our understanding of gravity. According to this theory, gravity is not merely a force acting at a distance, but rather a distortion of space-time itself, caused by massive objects like stars, planets, and black holes. The stronger the gravitational field, the more pronounced the curvature of space-time. This warping of the fabric of the universe means that time, as experienced by an observer, passes more slowly near a massive object compared to an observer who is far away from its gravitational influence. If two clocks are synchronized and one is placed in a strong gravitational field, such as near a planet's surface or close to a black hole, while the other remains in a region with weaker gravity, the clock in the stronger field will tick at a slower rate. In practical terms, this means that if a person were to spend time near a black hole and then return to a location farther from its gravitational pull, they would discover that more time had passed for those who remained on Earth. A fascinating real-world example of gravitational time dilation can be observed with Earth's satellites. The Global Positioning System, GPS, which relies on precise timekeeping to calculate locations, must account for the slight but crucial differences in time experienced by satellites orbiting Earth. These satellites, which are farther from the planet's gravitational influence, experience less time dilation than clocks on the surface. Engineers must factor in this difference in time to ensure the GPS system remains accurate. This practical application not only deepens our understanding of how gravity affects time, but also holds profound implications for astrophysics and cosmology, particularly in our study of phenomena like black holes and neutron stars. Gravitational time dilation serves as a powerful reminder of the intricate relationship between gravity, space-time, and the nature of time itself. It is a concept that continues to shape our understanding of the universe and challenges us to conceive time in ways we never thought possible. The twin paradox is another thought experiment that challenges our intuitive understanding of time. Set within the framework of special relativity, this paradox illustrates the effects of time dilation at relativistic speeds. The scenario involves two identical twins. One embarks on a journey into space, traveling at a significant fraction of the speed of light, while the other remains on Earth. When the traveling twin returns, it is discovered that they are younger than their Earth-bound sibling. This seemingly paradoxical situation is rooted in the principle of time dilation, a cornerstone of Einstein's theory of special relativity. According to the theory, time appears to pass more slowly for objects moving at high velocities compared to those at rest. For the twin traveling through space, their onboard clock ticks more slowly relative to the clock of the twin who stayed on Earth. As a result, while the journey might only take a few years for the traveling twin, many more years would pass for the twin who remained behind. What adds to the intrigue of the twin paradox is that both twins could consider themselves to be at rest in their own frame of reference, while the other is moving. This symmetry in the situation only deepens the paradox, making it one of the most fascinating and mind-bending aspects of modern physics. The twin paradox not only challenges our understanding of time, but also reveals the mind-boggling nature of the universe, where the passage of time is anything but absolute. However, the critical difference emerges from the fact that the traveling twin experiences acceleration and deceleration throughout their journey, especially when turning around to return to Earth. This shift in velocity disrupts the symmetry of the situation, causing the traveling twin to experience less time overall. The twin paradox serves as an elegant illustration of one of the most profound consequences of Einstein's special theory of relativity. That time is not a universal constant. Instead, it is relative, dependent on the frame of reference of the observer. This thought experiment, though seemingly counterintuitive, has been experimentally validated in numerous studies. One of the most striking demonstrations involves atomic clocks flown on high-speed jets. These real-world experiments confirm that the phenomenon of time dilation holds true, proving the paradox's predictions. As a result, the twin paradox does not just exist as an abstract theoretical concept. It has tangible, measurable implications in the physical world. This stark deviation from our everyday experience of time underscores the fundamentally different way in which time operates under relativistic conditions. In this light, the twin paradox becomes more than just a quirky thought experiment. It's a profound gateway into understanding how time, space, and motion are intricately linked in the universe. It challenges the very fabric of how we perceive the passage of time, revealing that under extreme conditions, time behaves in ways that are far from ordinary. The curvature of space-time, another cornerstone of Einstein's theories, further enhances our understanding of gravity and motion in the cosmos. In general relativity, gravity is not seen as a force pulling objects together, but rather as the result of massive bodies bending the very fabric of space-time. Picture a stretched rubber sheet. When you place a heavy ball in the center, the sheet bends and smaller objects roll toward the ball. Similarly, when massive objects like stars or planets exist within space-time, they cause a distortion, creating a dent that influences the motion of other objects in the vicinity. Take the Earth's orbit around the Sun as an example. The Sun, with its immense mass, curves the space-time around it. The Earth, moving through this curved space-time, doesn't simply fall directly toward the Sun, as we might expect due to gravity. Instead, it follows a curved path, which we observe as an elliptical orbit. In fact, Earth is perpetually falling toward the Sun, but because it is also moving forward with sufficient velocity, it continues to miss the Sun, effectively maintaining its orbit. This delicate balance between the forward motion of the Earth and the Sun's gravitational pull results in a stable orbital path. In essence, the Earth's orbit is not merely a random motion through space, but a precise trajectory shaped by the curvature of space-time around the Sun. This principle applies not only to planets orbiting stars, but also to moons orbiting planets, and even to binary star systems, where two stars orbit a common center of mass. Each of these celestial objects is following its own curved path through space-time, influenced by the mass of the bodies involved and the curvature they create in the surrounding space-time fabric. Furthermore, this understanding of curved space-time has far-reaching applications, especially in the field of space exploration. Take gravitational assists, for example. By carefully calculating the curvature of space-time around a planetary body, spacecraft can maneuver through this distortion to gain speed and adjust their trajectory. This technique, known as a gravity assist, allows spacecraft to conserve energy and alter their paths, enabling them to reach distant destinations within the solar system. The elegance of this process illustrates the profound link between mass, spacetime, and motion, which was first described in general relativity. But the relationship between mass, energy, and spacetime curvature is not just a theoretical abstraction. It is beautifully encapsulated in Einstein's most famous equation, E equals mc squared. This equation expresses the equivalence of mass and energy, two sides of the same coin. They are not separate entities, but interchangeable forms of the same underlying quantity. This realization is central to understanding how both mass and energy influence the geometry of spacetime. According to general relativity, mass and energy are not mere passive features of the universe. Rather, they are active participants in shaping the curvature of spacetime itself. The presence of mass and energy causes spacetime to bend, creating regions where the curvature is more pronounced. Objects within these regions will then follow paths determined by this curvature, which we perceive as gravitational attraction or orbital motion. For instance, consider Earth again. Its mass creates a distortion in spacetime, and other objects near it, whether they be satellites, meteoroids, or even the Moon, move along paths dictated by this curvature. This is what we experience as gravity. The Earth's mass has warped the fabric of spacetime around it, and as a result, everything within this curved space moves along curved trajectories, creating the gravitational effects we observe. In sum, these concepts, time dilation, spacetime curvature, and the interchangeability of mass and energy, revolutionize our understanding of the universe. They force us to rethink not only how we perceive time and space, but also how we engage with the cosmos, from exploring the fundamental laws of physics to planning missions that send spacecraft to the farthest reaches of space. Furthermore, mass is not the only factor that creates curvature in space. Energy plays an equally pivotal role. All forms of energy, whether potential, kinetic, or thermal, contribute to the overall mass-energy content of a system. This means that both mass and energy influence the curvature of spacetime in a similar manner, resulting in gravitational effects. Take, for instance, the energy released during nuclear reactions or the movement of particles. These processes can induce local changes in the curvature of spacetime, which in turn affects nearby objects. The curvature of spacetime itself is not a static feature, but a dynamic one, fluctuating over time as mass and energy undergo various transformations. A striking example of this can be seen when a massive star undergoes a supernova explosion. The energy released in such an event, coupled with the redistribution of mass, alters the local curvature of spacetime, impacting not only nearby celestial objects, but also the behavior of radiation. This is just one instance of how mass, energy, and the curvature of spacetime are intricately connected in a constantly shifting framework that shapes the behavior of the universe. By understanding that both mass and energy contribute to the bending of spacetime, we gain deeper insights into gravity's fundamental workings. This knowledge helps us comprehend everything from the orbits of planets to the bending of light near massive objects. It's a key to understanding the universe's grand mechanics. In cutting-edge space exploration, one particularly ingenious technique that takes advantage of the interplay between mass, energy, and gravitational forces is the gravitational assist, also known as a gravity assist or slingshot maneuver. This method allows spacecraft to increase their velocity and change trajectory without expending additional fuel. It leverages the gravitational pull of planets or other celestial bodies. As a spacecraft approaches a planet, it falls into the planet's gravitational well, and as it swings past, the gravitational pull accelerates the spacecraft. This interaction transfers some of the planet's orbital momentum to the spacecraft, propelling it faster and altering its path. The beauty of this maneuver lies in its fuel conservation, making it an invaluable tool for interplanetary missions. By carefully plotting a spacecraft's approach and timing it precisely, mission planners can achieve remarkable velocities and cover vast distances, all without relying heavily on onboard fuel. One of the most famous examples of this technique is the Voyager missions. Launched in the 1970s and 1980s, the spacecraft used multiple gravitational assists from Jupiter and Saturn to gain enough velocity to continue their journey to the outer reaches of the solar system. Gravitational assists are also a key enabler for missions to more distant destinations, like the outer planets or even interstellar space. These assists allow spacecraft to explore multiple celestial bodies within a single mission. For instance, the Galileo spacecraft used gravity assists to reach Jupiter, while the New Horizons mission relied on a gravity assist from Jupiter to reach Pluto in record time. These examples highlight how gravitational assists are a critical element in the exploration of our solar system, and by extension, the universe itself. By harnessing the natural movements and gravitational forces of planets, spacecraft can conserve fuel, increase their efficiency, and make significant strides in exploring distant regions of space. The dynamic relationship between celestial mechanics and space travel has opened new doors for interstellar exploration, advancing both our technological capabilities and our understanding of the cosmos. Looking forward, nuclear propulsion stands as a promising advancement in space travel. Unlike traditional chemical rockets that rely on the combustion of propellant to generate thrust, nuclear propulsion systems leverage nuclear reactions to produce energy. This breakthrough could revolutionize long-duration space missions, especially those aimed at distant planets or even interstellar travel. Nuclear propulsion offers immense potential to drastically improve the efficiency of space travel, extending our reach further into the universe while also reducing the limitations posed by current propulsion methods. Nuclear propulsion, one of the most exciting innovations in space travel, is steadily paving the way for interplanetary exploration. At its core, nuclear thermal propulsion harnesses the power of a nuclear reactor to heat a propellant, typically hydrogen, which is then expelled at high velocities to generate thrust. This system offers a significant advantage over conventional chemical rockets. It provides a much higher specific impulse, which is a key measure of propulsion efficiency. The result? Missions that would traditionally take years, like a journey to Mars or the outer planets, could be completed in a fraction of the time. This dramatic reduction in travel duration lessens the risks astronauts face during long space missions, including the harmful effects of prolonged exposure to radiation and the psychological strain of extended isolation. But the potential of nuclear propulsion doesn't stop there. Another groundbreaking concept is nuclear electric propulsion. In this system, nuclear reactors generate electricity, which powers ion thrusters. Though ion thrusters produce low levels of thrust, their efficiency is unparalleled. They can operate continuously for long periods, allowing for gradual acceleration over time. This makes them ideal for deep space missions, where conventional propulsion systems would be inefficient or even impractical. With nuclear electric propulsion, a spacecraft could gradually build up speed, enabling it to venture to the distant asteroid belt or even beyond, to the far reaches of our solar system. The implications of nuclear propulsion extend far beyond just deep space exploration. It could be the key to reaching destinations previously considered unreachable, such as the moons of Jupiter and Saturn. Today, these locations remain off-limits for human exploration due to the immense distances and the limitations of chemical propulsion. However, with faster, more efficient propulsion methods, we could reach these distant worlds, opening up possibilities for scientific research and resource utilization. The concept of mining asteroids, for instance, becomes far more feasible, as does the prospect of studying the icy moons in the outer solar system, which may harbor secrets to life beyond Earth. What truly sets nuclear propulsion apart is its reliability. Once a nuclear reactor is activated, it can produce energy continuously for long periods without the need for refueling. This makes it ideal for missions that require sustained operations, such as maintaining research outposts on distant planetary bodies. As nuclear technology continues to improve, both in terms of power generation and safety protocols, the potential applications for space travel are virtually limitless. This could revolutionize how humanity explores space, making missions to the farthest corners of our solar system not just possible, but efficient and safe. In parallel, space elevators represent another innovative concept that could radically alter how we access space. Imagine a massive structure extending from the surface of Earth all the way to a point beyond geostationary orbit, where centrifugal force balances gravitational pull. This structure would be anchored to the Earth, with a counterweight positioned in space to maintain the tension needed to keep the tether taut. The advantages of space elevators are profound. Currently, sending payloads into space is an energy-intensive and expensive endeavor, reliant on rockets that operate using chemical propulsion. Space elevators, however, could drastically reduce the cost of launching materials into orbit. Instead of using rockets, climbers, vehicles powered by electricity, could ascend the tether, carrying cargo and potentially people up into space. This would not only lower operational costs, but also increase the frequency of launches, making it far more economical to transport larger quantities of cargo. Space elevators could also unlock a host of new opportunities in space activities. With a more accessible and affordable means of transport, industries such as space tourism, satellite launching, and planetary exploration could thrive. More regular access to orbit could enable the development of orbital infrastructures, research stations, manufacturing facilities, and even human habitats, laying the foundation for an expanded human presence in space. Both nuclear propulsion and space elevators represent the next frontier in our quest to explore the cosmos. By dramatically improving the efficiency, safety, and cost-effectiveness of space travel, these technologies are set to transform humanity's ability to reach new worlds, unlocking the potential for exploration, resource utilization, and even the colonization of distant celestial bodies. As we continue to push the boundaries of what's possible, the dream of living and working in space is becoming more of a reality than ever before. A space elevator would revolutionize our connection between Earth and orbit, providing a continuous, fast, and efficient pathway that bypasses the long delays common in traditional space launches. This uninterrupted flow of supplies and personnel would be vital for sustaining long-term missions such as those to the Moon or Mars. Space elevators could also facilitate the construction of advanced space infrastructure, like solar power satellites, which would collect energy in space and beam it back to Earth, an energy solution that could power our planet for generations to come. However, while the idea of space elevators is undeniably enticing, several significant challenges remain before this concept can become a reality. For one, the materials required for the elevator's tether must have extraordinary properties. Extreme strength paired with lightweight characteristics. Current contenders, such as carbon nanotubes, are being actively researched for their potential in this regard. Alongside this, the stability of the structure must be guaranteed, withstanding external forces like weather patterns and space debris. Safety protocols also need to be meticulously crafted to ensure secure and reliable operations. Despite these hurdles, the potential of space elevators is enormous. If successfully developed, they could completely transform space access, making exploration and resource utilization in space not just a reality, but a sustainable endeavor. This shift could open up new pathways for the generations to come, making space far more accessible than it ever has been. Asteroid mining, another captivating prospect, brings with it a host of both extraordinary possibilities and formidable challenges. As humanity turns its gaze towards the cosmos for resources, extracting minerals and materials from asteroids emerges as an innovative way to supplement Earth's terrestrial resources. Not only could asteroid mining provide raw materials for space exploration, but it could also unlock critical resources for infrastructure development in space. One of the most compelling advantages of asteroid mining is the abundance of valuable materials that are scattered throughout our solar system. Many asteroids are rich in metals like platinum, gold, and rare earth elements, which are essential for the production of cutting-edge technologies, including those used in electronics and renewable energy systems. Tapping into this treasure trove of materials could ease the pressure on Earth's dwindling resources, reduce the environmental damage caused by traditional mining, and pave the way for new economic opportunities. Furthermore, these materials could provide the necessary components for future space missions, building materials, fuels, and even water for life support systems in deep space. Yet the path to asteroid mining is riddled with challenges. The foremost of these is the technology required to locate, reach, and mine asteroids, many of which may be small or located in the farthest corners of our solar system. Efficient propulsion systems, robotic mining technologies, and autonomous systems will be indispensable for identifying, accessing, and extracting materials from these celestial bodies. Additionally, the logistics of transporting mined materials back to Earth or utilizing them directly in space present complex engineering obstacles. Equally significant are the legal and regulatory frameworks that need to be established. International space treaties, such as the 1967 Outer Space Treaty, are silent on the ownership of resources extracted from asteroids. Without clear, universally agreed upon guidelines, conflicts could arise over who owns the materials mined from these distant bodies. Clear legal frameworks will be essential to ensure the success of asteroid mining, allowing commercial ventures to operate without risk of disputes, and ensuring the fair use of space resources. In both space elevators and asteroid mining, the future of space exploration hinges on overcoming considerable technological, logistical, and legal challenges. But if these obstacles are addressed, humanity stands on the cusp of a new era, one where the resources of space are harnessed and the boundaries of human exploration are expanded beyond our wildest dreams. The economic implications of asteroid mining are profound and complex. The initial investments required for these ventures are expected to be substantial, and the journey toward profitability hinges on overcoming significant technological barriers. These challenges are not just about securing the necessary tools to mine asteroids, but also about ensuring that the materials extracted can be transported and utilized in a cost-effective manner. The market for asteroid-sourced materials must be carefully defined, taking into account the possible effects on existing Earth-based commodities. Despite these hurdles, the idea of asteroid mining holds a magnetic appeal. As we continue to advance technologically and deepen our understanding of space, this field promises to usher in a new era of resource utilization beyond Earth. Asteroid mining could potentially provide critical materials needed for life on Earth, while also supporting humanity's long-term presence in space. Such endeavors could ignite innovations, reduce terrestrial resource demands, and unlock vast, untapped potential within our solar system for generations to come. One of the major challenges for long-duration space missions, like those planned for Mars or beyond, is the protection of spacecraft and astronauts from cosmic radiation. Cosmic radiation, which is made up of high-energy particles from the Sun and distant supernovae, presents a serious health threat to those venturing into deep space. These high-energy particles can penetrate biological tissues, causing DNA damage, increasing the risk of cancer, and potentially leading to other long-term health problems. Thus, ensuring astronaut safety during extended periods in space necessitates effective radiation protection. One solution being explored involves the spacecraft's own structure. Engineers are investigating materials with high atomic numbers, such as lead and polyethylene, which are capable of absorbing or deflecting radiation. This could translate into spacecraft designs featuring multi-layered walls constructed from different materials, each serving to mitigate the penetration of harmful particles. Additionally, critical sections of the spacecraft, like living quarters, could be strategically placed behind thicker shielding or even inside specially designed science bunkers that offer added protection during high radiation events like solar particle storms. Beyond structural solutions, another strategy involves utilizing the massive supplies and equipment within the spacecraft as passive shielding. Water supplies, cargo, and other materials not only serve their intended purpose, but can also act as effective barriers against radiation. This dual-purpose approach optimizes space usage within the spacecraft while providing essential protection. For missions to Mars, thoughtful planning could ensure that the resources required for the journey, fuel, supplies, and equipment, can also contribute to the spacecraft's radiation shielding. This strategic use of available materials not only enhances the mission's sustainability, but also maximizes the spacecraft's overall efficiency. In addition to these passive solutions, there is ongoing research into active shielding techniques. One promising concept involves creating electromagnetic fields that could deflect charged particles away from the spacecraft. While still in the experimental stage, the idea of using magnetic or electrostatic fields to create a protective bubble around the spacecraft is an exciting prospect. However, turning this concept into a practical, deployable technology will require significant breakthroughs in both engineering and science. As space exploration continues to evolve, addressing these radiation risks and unlocking the potential of asteroid mining will be critical milestones in humanity's quest to explore and utilize space. Monitoring and timely communication about radiation levels are essential for the safety of astronauts during space missions. Spacecraft can be equipped with radiation detectors that provide real-time data on cosmic radiation exposure. By establishing protocols for astronauts to take refuge in more shielded areas during high radiation events, such as solar flares, we can further minimize their exposure. As our ambitions for deep space exploration continue to grow, addressing cosmic radiation will remain a top priority. Through the combination of innovative shielding techniques, effective mission planning, and real-time monitoring, we can ensure that astronauts are better protected as they venture further into the cosmos. This will unlock new opportunities for discovery and exploration, allowing humanity to reach new frontiers while safeguarding the health of those who brave the unknown. In parallel, advancements in exoplanet imaging technologies are rapidly transforming our ability to detect and study planets outside our solar system. As astronomers push the boundaries of exploration, new techniques are emerging that significantly enhance our ability to capture clearer images of exoplanets and analyze their atmospheres. One of the most exciting developments has been the integration of adaptive optics with powerful ground-based telescopes. Adaptive optics help correct the distortions caused by Earth's atmosphere, enabling telescopes to produce sharper, more accurate images. This breakthrough is especially valuable for observing exoplanets, which are often hidden by the intense glare of their parent stars. By reducing atmospheric interference, astronomers can more effectively identify and characterize the light coming from distant exoplanets. Notable observatories, such as the Keck Observatory in Hawaii and the Very Large Telescope in Chile, have successfully employed adaptive optics to directly image exoplanets. Another promising innovation lies in the use of coronagraphs and starshades. These instruments are designed to block the overwhelming light from a star, allowing astronomers to directly observe nearby exoplanets. By selectively filtering out starlight, coronagraphs and starshades reveal planets that would otherwise remain obscured. NASA's upcoming missions, including the James Webb Space Telescope and the Nancy Grace Roman Space Telescope, will utilize advanced coronagraph technology, pushing the boundaries of exoplanet imaging even further. The James Webb Space Telescope, with its advanced infrared capabilities, aims to offer unparalleled insights into the atmospheres of exoplanets. It could potentially detect molecules that indicate habitability or even signs of life. In addition, recent advancements in spectroscopic techniques are allowing astronomers to study the chemical compositions and atmospheric conditions of exoplanets in greater detail. By analyzing the light spectrum that passes through or reflects off an exoplanet's atmosphere, researchers can identify the presence of specific molecules like water vapor, carbon dioxide, and methane. These innovations are crucial for the search for potentially habitable worlds. Atmosphere analysis provides vital clues about whether a planet can support life as we know it. As the precision and sensitivity of spectrometers continue to improve, our understanding of exoplanet environments is becoming clearer, bringing us one step closer to answering one of humanity's most profound questions. Are we alone in the universe? Machine learning and artificial intelligence are rapidly becoming essential tools in the realm of advanced imaging technologies. As the volume of data produced by these technologies soars, these innovative methods are providing new ways to analyze and interpret complex data sets with unparalleled speed and accuracy. These capabilities are transforming the way we explore and understand exoplanets. By identifying subtle patterns and anomalies, AI-driven algorithms can detect new exoplanets with an efficiency that was once unimaginable. The result is an accelerated pace of discovery and a more detailed understanding of known exoplanets, including the possibility of discovering Earth-like worlds. As these technologies evolve, their potential to revolutionize our understanding of planetary systems across the galaxy grows. The impact of these advances extends beyond merely identifying new worlds. They hold the promise of enhancing our knowledge about the conditions required for life to thrive on distant planets. With each breakthrough, we inch closer to answering one of humanity's most profound questions. Are we alone in the universe? One of the most transformative roles of AI in space exploration lies in the realm of data processing and analysis. Space telescopes and satellites continually generate vast amounts of data, particularly in fields like astronomy and planetary science. Traditional methods of analyzing this data can be slow and labor-intensive, but AI systems, especially those powered by machine learning, can process this information much more efficiently. AI excels in identifying subtle patterns that might go unnoticed by human analysts. For example, AI algorithms are being used to detect the faint signals of exoplanets by analyzing light curves, which show the periodic dimming of a star's light as a planet transits in front of it. This capability dramatically speeds up the discovery process and expands the scope of astronomical research. AI also plays a crucial role in the analysis of images collected from space missions. Techniques such as convolutional neural networks, CNNs, are especially valuable in processing high-resolution images from space telescopes and planetary exploration missions. These AI models can identify and categorize geological features on planets, monitor atmospheric changes, and track environmental shifts on planetary bodies. A prime example is the use of AI to analyze images of Mars, where AI systems have assisted scientists in identifying surface features, pinpointing areas of interest for future missions, and even categorizing mineral deposits. Moreover, the integration of AI into autonomous spacecraft systems is a game changer for deep space exploration. Space missions often involve significant communication delays between spacecraft and Earth. AI-driven systems can overcome this challenge by enabling spacecraft to make real-time decisions based on environmental data. This autonomy allows spacecraft to adjust their trajectory, optimize resource management, and perform other operational tasks without needing immediate human intervention. Such capabilities increase the efficiency, safety, and success of missions, particularly those exploring distant corners of our solar system and beyond. In addition to improving operational efficiency, AI is also enhancing the ability to model and simulate complex space environments. By using advanced algorithms, scientists can create highly detailed simulations that mimic various space conditions. These simulations are vital for mission planning, helping researchers anticipate potential challenges and devise contingency strategies for unforeseen issues. The ability to predict outcomes and assess risks is essential for ensuring the success of long-duration space missions, such as those aimed at reaching Mars or exploring distant moons. AI's potential is not limited to data analysis and mission operations. It can also foster greater collaboration across different scientific fields. By integrating data from multiple disciplines, such as geology, biology, and atmospheric science, AI enables researchers to develop more comprehensive models of celestial phenomena. This interdisciplinary approach paves the way for the development of next-generation exploration strategies, making space research more interconnected and holistic. The future of space exploration is poised to benefit greatly from the integration of artificial intelligence. As we continue to refine these technologies, their impact will only grow. AI is not just improving our ability to process data more quickly. It is enhancing our ability to think strategically, solve complex problems, and conduct more informed research. From autonomous operations to sophisticated simulations, AI is shaping the future of space missions and broadening our horizons. In parallel, another transformative technology that holds immense potential for space exploration is 3D printing. In the context of space colonization, 3D printing offers a groundbreaking solution to the challenges of establishing human habitats beyond Earth. Instead of relying on transporting materials from Earth, 3D printing allows for the production of tools, components, and even entire structures directly in space. This localized manufacturing process significantly reduces the logistical and financial challenges associated with space missions, making space exploration more sustainable and cost-effective. By enabling the creation of on-site infrastructure, 3D printing could facilitate the construction of habitats on the Moon, Mars, and beyond, where every component must be produced from local resources. This innovation could revolutionize not only how we build in space, but also how we think about humanity's long-term presence in the cosmos. The combination of AI and 3D printing technologies promises to usher in a new era of space exploration, one where missions are more self-sufficient, adaptable, and far-reaching than ever before. Machine learning and artificial intelligence are rapidly becoming essential tools in the realm of advanced imaging technologies. As the volume of data produced by these technologies soars, these innovative methods are providing new ways to analyze and interpret complex data sets with unparalleled speed and accuracy. These capabilities are transforming the way we explore and understand exoplanets. By identifying subtle patterns and anomalies, AI-driven algorithms can detect new exoplanets with an efficiency that was once unimaginable. The result is an accelerated pace of discovery and a more detailed understanding of known exoplanets, including the possibility of discovering Earth-like worlds. As these technologies evolve, their potential to revolutionize our understanding of planetary systems across the galaxy grows. The impact of these advances extends beyond merely identifying new worlds. They hold the promise of enhancing our knowledge about the conditions required for life to thrive on distant planets. With each breakthrough, we inch closer to answering one of humanity's most profound questions. Are we alone in the universe? One of the most transformative roles of AI in space exploration lies in the realm of data processing and analysis. Space telescopes and satellites continually generate vast amounts of data, particularly in fields like astronomy and planetary science. Traditional methods of analyzing this data can be slow and labor-intensive, but AI systems, especially those powered by machine learning, can process this information much more efficiently. AI excels in identifying subtle patterns that might go unnoticed by human analysts. For example, AI algorithms are being used to detect the faint signals of exoplanets by analyzing light curves, which show the periodic dimming of a star's light as a planet transits in front of it. This capability dramatically speeds up the discovery process and expands the scope of astronomical research. AI also plays a crucial role in the analysis of images collected from space missions. Techniques such as convolutional neural networks, CNNs, are especially valuable in processing high-resolution images from space telescopes and planetary exploration missions. These AI models can identify and categorize geological features on planets, monitor atmospheric changes, and track environmental shifts on planetary bodies. A prime example is the use of AI to analyze images of Mars, where AI systems have assisted scientists in identifying surface features, pinpointing areas of interest for future missions, and even categorizing mineral deposits. Moreover, the integration of AI into autonomous spacecraft systems is a game changer for deep space exploration. Space missions often involve significant communication delays between spacecraft and Earth. AI-driven systems can overcome this challenge by enabling spacecraft to make real-time decisions based on environmental data. This autonomy allows spacecraft to adjust their trajectory, optimize resource management, and perform other operational tasks without needing immediate human intervention. Such capabilities increase the efficiency, safety, and success of missions, particularly those exploring distant corners of our solar system and beyond. In addition to improving operational efficiency, AI is also enhancing the ability to model and simulate complex space environments. By using advanced algorithms, scientists can create highly detailed simulations that mimic various space conditions. These simulations are vital for mission planning, helping researchers anticipate potential challenges and devise contingency strategies for unforeseen issues. The ability to predict outcomes and assess risks is essential for ensuring the success of long-duration space missions, such as those aimed at reaching Mars or exploring distant moons. AI's potential is not limited to data analysis and mission operations. It can also foster greater collaboration across different scientific fields. By integrating data from multiple disciplines, such as geology, biology, and atmospheric science, AI enables researchers to develop more comprehensive models of celestial phenomena. This interdisciplinary approach paves the way for the development of next-generation exploration strategies and making space research more interconnected and holistic. The future of space exploration is poised to benefit greatly from the integration of artificial intelligence. As we continue to refine these technologies, their impact will only grow. AI is not just improving our ability to process data more quickly, it is enhancing our ability to think strategically, solve complex problems, and conduct more informed research. From autonomous operations to sophisticated simulations, AI is shaping the future of space missions and broadening our horizons. In parallel, another transformative technology that holds immense potential for space exploration is 3D printing. In the context of space colonization, 3D printing offers a groundbreaking solution to the challenges of establishing human habitats beyond Earth. Instead of relying on transporting materials from Earth, 3D printing allows for the production of tools, components, and even entire structures directly in space. This localized manufacturing process significantly reduces the logistical and financial challenges associated with space missions, making space exploration more sustainable and cost-effective. By enabling the creation of on-site infrastructure, 3D printing could facilitate the construction of habitats on the Moon, Mars, and beyond, where every component must be produced from local resources. This innovation could revolutionize not only how we build in space, but also how we think about humanity's long-term presence in the cosmos. The combination of AI and 3D printing technologies promises to usher in a new era of space exploration, one where missions are more self-sufficient, adaptable, and far-reaching than ever before. Space-based solar power presents a groundbreaking solution to the energy challenges of the future. The potential of harnessing solar energy in space, where the sun's rays are uninterrupted by atmospheric interference, could revolutionize the way we think about power generation. This technology, which can beam energy directly to Earth, holds promise not only for providing sustainable energy, but also for ensuring that remote or disaster-stricken areas lacking robust infrastructure are no longer left in the dark. By tapping into space-based solar power, these systems could support humanitarian efforts, military operations, and emergency response initiatives by offering a flexible, reliable solution for power distribution. Furthermore, the implications for climate change are profound. With space-based solar power, the reliance on fossil fuels could dramatically decrease as solar energy is harvested directly from space, where it is abundant and consistent, rendering a significant reduction in greenhouse gas emissions. This shift could contribute to the global efforts to combat climate change, creating a cleaner, greener future for all. However, the path to making space-based solar power a reality is fraught with challenges. From the technological complexities of designing and launching large satellites to ensuring the efficient conversion and transmission of energy, these hurdles are formidable. The cost and complexity of developing such systems are immense, and the safety concerns regarding the health impacts of high-intensity microwave beams or lasers demand thorough investigation and stringent regulations. Despite these hurdles, the vision of space-based solar power offers a tantalizing glimpse of what the future of energy generation could look like. Continued research and innovation in this field may unlock solutions to capture and distribute solar energy from space, transforming the way we power our planet and bringing us closer to a sustainable future. As we venture further into space, particularly with ambitions for long-term human habitation on the Moon, Mars, and beyond, a new set of challenges emerges. Extended missions to these distant destinations require solutions to ensure the safety, health, and well-being of astronauts living in the harsh conditions of space. Among the foremost challenges are the effects of microgravity, radiation exposure, psychological well-being, resource management, and the sustainability of life support systems. One of the most significant challenges is the physiological impact of microgravity. In the absence of gravity, astronauts experience muscle atrophy and bone density loss, which can lead to serious health issues over time. Countermeasures, such as regular exercise regimens using specialized equipment designed for microgravity, are essential to maintaining astronaut health. Researchers are also exploring nutritional interventions and pharmaceutical therapies that can help mitigate these effects, ensuring astronauts remain fit and healthy during long-duration missions. Radiation exposure presents another critical concern. In deep space, astronauts are exposed to higher levels of cosmic radiation and solar particle events than those on Earth, which significantly increases the risk of cancer and other health problems. To combat this, spacecraft could be designed with advanced shielding materials, and habitats could utilize natural resources like lunar regolith or Martian soil to provide additional protection from harmful radiation. These innovations could enhance the safety of astronauts on missions to the farthest reaches of space. Psychological well-being also plays a crucial role in the success of long-term missions. Astronauts on extended missions may face isolation, confinement, and stress, all of which can affect their mental health and team dynamics. To counteract these effects, creating supportive environments that foster social interaction, open communication, and recreational activities is essential. Research into team dynamics and conflict resolution will also play a key role in preparing crews for the unique challenges of living and working together in confined spaces for long periods. Another fundamental challenge for long-term space missions is resource management. In the harsh environment of space where resupply missions are limited, astronauts will need reliable systems to recycle water, purify air, and produce food. Closed-loop life support systems, which recycle air and water, can minimize waste and reduce the need for constant resupply. Advances in hydroponics and aeroponics, the growth of plants in water and air, are already making strides, allowing for fresh food production in space. Research into growing crops in microgravity, coupled with the development of efficient food production systems, will be crucial to supporting astronauts on missions to the Moon or Mars. These space-based greenhouses could not only provide vital nutrition, but also offer psychological benefits, as tending to plants has been shown to improve mental well-being. As humanity looks to the stars, these challenges are just the beginning. The future of human space exploration hinges on the development of technologies that enable long-term survival and sustainability in space. As we continue to push the boundaries of what is possible, the lessons learned and innovations developed will not only benefit astronauts, but may also offer new solutions to some of Earth's most pressing issues, from energy production to resource management and beyond. As space missions push further from Earth, the need for autonomous systems capable of repairing and maintaining habitats becomes ever more pressing. With each new mission, the challenges of providing timely support grow more complex. Robotics, artificial intelligence, and automation are poised to become the critical tools for overcoming these obstacles. These technologies can perform essential tasks such as repairs, monitor life support systems, and ensure that habitats remain safe and operational, thus providing astronauts with more autonomy and reliability in the unforgiving environment of space. Addressing the long-term challenges of human space habitation requires a broad and innovative approach. By investing in cutting-edge research and advancing new technologies, we can build safe, sustainable environments for astronauts on extended missions. This will not only support humanity's exploration of the solar system, but also pave the way for the establishment of a permanent human presence beyond Earth. When we look up at the cosmos, we marvel at the vastness and beauty of the universe. But lurking in the stars are some of the most violent and catastrophic events imaginable. Gamma ray bursts. These bursts are among the most powerful explosions ever observed, releasing mind-boggling amounts of energy in the form of gamma radiation over a span of mere seconds or minutes. They are thought to occur during the collapse of massive stars into black holes, or when neutron stars collide, creating the perfect storm of energy. If such an event were to occur close to Earth, directed at our planet, the consequences would be nothing short of catastrophic. One of the first areas of concern would be the ozone layer, which acts as Earth's shield against harmful ultraviolet radiation. The sheer intensity of gamma radiation from a nearby burst could strip away this protective layer, exposing life on Earth to deadly levels of UV rays. The effects would be devastating. Marine life, especially phytoplankton, which form the foundation of the oceanic food chain, would be at risk alongside terrestrial plants and even human health. The heightened levels of ultraviolet radiation could lead to widespread ecological collapse, affecting everything from crops to ecosystems. Yet the immediate radiation from such an event wouldn't be limited to the surface. Life forms at higher altitudes, such as those aboard spacecraft, would be exposed to lethal doses of radiation, potentially incapacitating astronauts or inducing radiation sickness. The dangers could also extend to technology. Satellites in low Earth orbit could be fried by the radiation, leaving humanity vulnerable to communication blackouts and power failures. With the electromagnetic pulse created by the burst, even more critical systems could be disrupted, leading to cascading failures across entire networks. Fortunately, the likelihood of a gamma-ray burst occurring close enough to harm Earth is incredibly low. Most known bursts originate from distant galaxies, often millions or even billions of light years away. While the threat remains remote, scientists continue to study these explosive phenomena. By monitoring the cosmos for gamma-ray bursts, we not only satisfy our curiosity about the universe, but also deepen our understanding of cosmic processes, reinforcing the need to protect our planet's delicate ecosystems from potential disasters. Planetary impacts, collisions with asteroids or comets, have had a profound impact on Earth's history and may hold the key to understanding the potential for life on other planets. These cosmic events can reshape planetary environments, sometimes with catastrophic consequences, but in other instances, they can drive transformative changes. One of the most significant impacts in Earth's history occurred around 66 million years ago, when a colossal asteroid collided with what is now the Yucatan Peninsula. This impact is believed to have triggered the mass extinction event known as the Cretaceous-Paleogene, KPG extinction, which wiped out roughly 75% of all species, including the non-avian dinosaurs. The aftermath of this event was catastrophic: wildfires, tsunamis, and a nuclear winter effect, dust and debris filling the atmosphere, blocking sunlight and disrupting photosynthesis. This dramatic shift in environmental conditions created an opportunity for other species to thrive. With the dinosaurs gone, mammals began to diversify, setting the stage for the eventual rise of primates and, much later, humans. However, planetary impacts are not merely destructive. They can also be a source of new materials and chemicals that can help foster new forms of life. For example, certain impacts may bring water and organic compounds to a planet, potentially jump-starting the development of life. This idea ties into the panspermia hypothesis, which suggests that life, or at least the building blocks of life, might spread across the universe through asteroids and comets. If true, these spacefaring bodies could play a critical role in creating the right conditions for life to take root on rocky planets, increasing the odds of life emerging elsewhere in the cosmos. The impact of celestial events on the geological and climatic dynamics of a planet is profound, often driving change that shapes the very nature of a planet's environment. The heat generated by an impact can trigger volcanic activity, giving rise to new landforms and altering the composition of the atmosphere. These changes can, in turn, foster the creation of diverse ecosystems and habitats, promoting the emergence of new life forms. Take, for instance, volcanic eruptions that follow a large impact. These eruptions can enrich soils with nutrients, setting the stage for the adaptation of life to an evolving environment. Such impacts can also influence the potential for life to emerge on other planets. Consider Mars, a planet that has undergone numerous impacts throughout its history. These collisions could have once provided the conditions necessary for life to flourish. The delivery of water and organic materials through these impacts might have played a crucial role in the early formation of Mars's environment. Similarly, moons like Europa or Enceladus, with their subsurface oceans, may have been subjected to impacts that introduced the compounds required for life to thrive. Planetary impacts are not simple events. They are complex phenomena capable of drastically altering the course of a planet's evolutionary path. They can lead to mass extinctions, give rise to entirely new forms of life, and dramatically influence environmental conditions. These events underscore the delicate and intricate relationships between celestial happenings and the evolution of life itself. Understanding such processes enhances our comprehension of Earth's history and guides our ongoing search for life beyond our planet. However, the influence of celestial events does not end with impacts alone. A nearby supernova explosion, for example, could have profound consequences for Earth and its biosphere, depending on the proximity of the event. Supernovae are massive stellar explosions that occur at the end of a star's life cycle. When a star exhausts its nuclear fuel, it can no longer sustain its mass, leading to an explosion that releases an immense amount of energy and ejects heavy elements into space. If a supernova were to occur relatively close to Earth, within about 50 to 100 light years, its effects could be catastrophic. One of the immediate consequences of such an event would be an increase in radiation exposure. A supernova emits vast amounts of high-energy radiation, including gamma rays and X-rays, which could have harmful effects on our atmosphere. The radiation might deplete the ozone layer, which serves as Earth's protective shield against harmful ultraviolet UV radiation. With a weakened ozone layer, Earth's surface would be exposed to higher levels of UV radiation, potentially leading to an increase in skin cancer, cataracts, and damage to ecosystems. Additionally, the shockwave generated by the explosion could also affect the Earth. While the shockwave's intensity would diminish with distance, it could still disrupt the atmospheres of nearby planets and even interact with the solar wind. This interaction might impact Earth's magnetosphere, leading to geomagnetic storms that could damage power grids and communication systems, much like the storms caused by strong solar flares. Another potential consequence of a nearby supernova is the introduction of heavy elements into our solar system. Supernovae are responsible for producing many of the universe's heavier elements, such as gold, uranium, and others. The explosion would scatter these elements across space, and depending on the trajectory of the debris, some of it could be drawn into the solar system. This process contributes to the cosmic abundance of materials essential for planet formation, and could have played a significant role in shaping Earth's early environment. The historical significance of these heavy elements cannot be overstated, as they are fundamental to the chemistry that supports life on Earth today. However, it's crucial to understand that, despite the potential consequences, the likelihood of a supernova occurring in our cosmic neighborhood anytime soon remains minimal. The closest candidate, Betelgeuse in the Orion constellation, is still situated far enough away that its eventual explosion would not pose a direct catastrophic threat to Earth. Even when this stellar giant does eventually explode, the effects on our planet would be determined by the distance between Earth and the explosion, as well as the energy released during the event. While a supernova happening nearby could lead to noticeable disruptions, such as an increase in radiation, atmospheric disturbances, and the introduction of heavy elements into the atmosphere, the risks we face today are largely speculative. Ongoing research into stellar evolution and cosmology continues to deepen our understanding of these awe-inspiring cosmic events and their potential implications for Earth. Scientists are constantly monitoring distant stars, refining their predictions, and uncovering new layers of knowledge about these stellar phenomena. While the idea of a supernova wreaking havoc on Earth captures the imagination, the vast distances between us and these celestial objects mean that for the time being, the threat remains hypothetical. In a completely different realm of cosmic phenomena, the concept of geomagnetic reversal presents a fascinating subject of study. Geomagnetic reversal refers to a process in which the Earth's magnetic poles, north and south, switch places. This dramatic event has occurred numerous times throughout Earth's history, with the last significant reversal, known as the Brunhes-Matuyama reversal, taking place approximately 800,000 years ago. While these magnetic flips are natural and occur over geological timescales, their potential effects on both life and our technologically driven society raise intriguing questions. One immediate consequence of a geomagnetic reversal would be a temporary weakening of Earth's magnetic field. This field serves as an essential shield, protecting our planet from harmful cosmic radiation and solar wind by deflecting charged particles. Should the magnetic field weaken, it could allow greater amounts of radiation to penetrate the atmosphere, increasing exposure to living organisms. The more vulnerable species, such as animals with no protective outer layers or those living at lower altitudes, could be particularly affected by this change in radiation levels. Despite the potential risks, it is important to recognize that past geomagnetic reversals did not correlate with mass extinctions. This suggests that life on Earth has historically shown resilience, adapting over time to the fluctuating radiation levels. Many organisms, particularly those dwelling underground or in the depths of the oceans, have evolved natural mechanisms to shield themselves from radiation, thus mitigating the potential adverse effects of such events. Aside from biological consequences, a magnetic field reversal could have far-reaching implications for modern technology and infrastructure. In today's world, much of our technological systems, from satellite communications to GPS navigation, rely heavily on the stability of Earth's magnetic field. Any significant fluctuations or anomalies in the field could lead to disruptions in these systems, potentially impacting global positioning services and communication networks. Astronauts aboard the International Space Station, positioned above much of the protective shield of Earth's magnetic field, could also experience increased exposure to radiation. This would require adjustments to space mission protocols and potentially additional measures to ensure the safety of those venturing beyond Earth's atmosphere. Although geomagnetic reversals have occurred throughout the planet's history, the intertwining of our modern reliance on technology with these natural processes presents new challenges and considerations for both our understanding of Earth's past and our preparation for the future. As Earth's magnetic field gradually shifts, the societal and psychological ramifications could become significant. The process, though a natural and predictable part of our planet's geological cycle, might stir public concern or provoke widespread misunderstanding. This is why clear communication from scientists and authorities is essential. It's vital to share knowledge about geomagnetic reversals, their history, what we know about them, and their contemporary implications. Such transparency can help calm fears, encourage informed discussion, and prevent panic. Though the reversal of Earth's magnetic field may hold potential consequences for life and technology, history has shown that both Earth and its inhabitants can endure and adapt to such changes. Ongoing research into the dynamics of Earth's magnetic field will continue to deepen our understanding of the phenomenon. As we learn more about the impacts on both biological systems and technological infrastructure, we will be better prepared to face any challenges that arise from this natural occurrence. Looking far ahead, in about 5 billion years, the Sun will enter its red giant phase, an event that will have profound consequences on our solar system. This dramatic transformation is driven by the Sun's shift from hydrogen fusion to helium fusion in its core. As a result, the Sun's outer layers will expand enormously, potentially engulfing the inner planets. The Sun's surface temperature will cool slightly, giving it a reddish hue, but its luminosity will soar, making the Sun many times brighter than it is today. During this red giant phase, the immediate effects on Earth will be catastrophic. As the Sun's size increases, Earth will experience extreme heating. The temperatures will rise so significantly that oceans will evaporate and the atmosphere will be lost to space. Any form of life that remains on Earth will struggle to survive, and the planet will become uninhabitable long before it is physically consumed by the Sun. For the outer planets and their moons, the situation will be different. While they are unlikely to be destroyed by the Sun's expansion, they will still undergo significant environmental changes. The increased solar output could alter the atmospheres and climates of planets like Jupiter and Saturn, potentially affecting their moons that might harbor conditions conducive to life. The heightened radiation and solar wind may also alter their magnetospheres. As the Sun completes its transformation, it will shed its outer layers, creating a stunning planetary nebula. This process will leave behind a dense, cooling core, known as a white dwarf, which will continue to cool for billions of years. While this might sound apocalyptic, it is simply part of the Sun's natural life cycle. The expelled material from the Sun will enrich the interstellar medium with heavy elements, facilitating the formation of new stars and potentially new planetary systems. Although this cataclysmic event seems far off, it is important to remember that it occurs on timescales that are almost unfathomable, giving humanity ample opportunity to prepare. Whether through the colonization of other celestial bodies or the development of technologies to escape the solar system, there is time to explore options for long-term survival. This transition into a red giant will undeniably reshape the solar system, causing the destruction of the inner planets, including Earth. but it will also provide the building blocks for the formation of new stars, a process that is fundamental to the ongoing evolution of the galaxy. This cosmic event serves as a powerful reminder of the ever-changing nature of the universe, a universe in which we live, not as spectators, but as active participants, however fleeting our time may be. Meanwhile, coronal mass ejections, CMEs, massive bursts of solar wind and magnetic fields rising above the sun's corona, are also a significant phenomenon to consider. These eruptions send billions of tons of charged particles, primarily electrons and protons, streaming into space at speeds that can exceed several million miles per hour. When these charged particles are directed toward Earth, they can pose serious threats to modern technology, particularly systems that rely on electronic communication and power distribution. One of the most immediate dangers of CMEs is their ability to disrupt Earth's magnetosphere. When these charged particles interact with our planet's magnetic field, they can induce geomagnetic storms. These storms can interfere with satellite operations, including communication satellites and GPS systems. In extreme cases, CMEs can cause satellite malfunctions, leading to data loss, service disruptions, and costly repairs or replacements. But satellites are not the only systems at risk. CMEs also pose a significant threat to power grids on Earth. The geomagnetic storms they trigger can induce powerful electric currents in power lines and transformers, leading to dangerous voltage spikes. Such surges can damage critical transformer infrastructure, resulting in widespread power outages. Historical events like the 1989 blackout in Quebec serve as stark reminders of the potential impact of CMEs on electricity supply. In addition to their effects on satellites and power grids, CMEs can disrupt communication systems on Earth, particularly high-frequency radio signals, which are crucial for aviation and maritime operations. During geomagnetic storms, these communication systems can be subject to interference, which can be especially problematic in polar regions, where high-frequency radio communication is essential for safe navigation. As solar activity continues to influence our planet in these profound ways, understanding the risks and preparing for the effects of CMEs becomes an essential task. The unpredictable nature of these solar events serves as another reminder of the dynamic and interconnected forces that shape both our technology and our planet's environment. The ongoing study of the sun and its behavior will help ensure that humanity is better equipped to deal with the challenges of the future. The solar system's interaction with space weather, particularly during periods of heightened solar activity, presents a growing challenge to our technological infrastructure. As the sun enters its more active phases, phenomena like coronal mass ejections, CMEs, release immense bursts of energy and charged particles. These events pose a significant risk to astronauts in space, with the radiation levels reaching dangerous thresholds. To safeguard human space exploration, strict safety protocols must be in place, especially during these intense solar events. Scientists actively monitor solar activity with the help of advanced satellites, which are equipped with specialized instruments designed to detect CMEs and other solar phenomena. Early warning systems play a crucial role, providing alerts when a CME is detected. These systems can forecast its trajectory toward Earth, enabling power grid operators, satellite managers, and other key stakeholders to take precautionary measures. With proper preparation, we can reduce the potential disruptions that CMEs could cause to our power grids, communication systems, and satellite operations. This proactive approach strengthens the resilience of modern technological systems, ensuring they can weather the storm of solar disruptions. The potential impact of a rogue planet entering our solar system adds another layer of complexity to the unpredictable nature of space. Rogue planets, celestial bodies that do not orbit a star and travel through interstellar space, could present significant risks if they were to enter the gravitational reach of our solar system. The consequences of such an event would depend on several factors: the size and mass of the rogue planet, its trajectory, and its proximity to other celestial bodies. One immediate concern would be the gravitational interactions between the rogue planet and the Sun or other planets. If a rogue planet passed too close to the Sun or another planet, its gravitational forces could disrupt the orbits of nearby celestial bodies. Such disturbances could destabilize the orbits of outer planets, sending asteroids or comets into the inner solar system and heightening the risk of impacts on Earth or other planets. Additionally, the gravitational pull of a rogue planet could perturb the Kuiper Belt or Oort cloud, regions that house icy bodies, and send them into new orbits, further escalating the risks of collisions. The threat of a rogue planet coming into direct contact with Earth is another alarming possibility. If the rogue planet's trajectory brought it too close to our planet, the results could be catastrophic. Depending on its size and proximity, it could pose a serious threat of collision, similar to past events that have triggered mass extinction events. Even if a rogue planet did not directly collide with Earth, but passed at a dangerously close range, its gravitational influence could still disrupt the planet's rotation, axial tilt, and overall stability. Such shifts could result in severe climate changes, altering Earth's environment in unpredictable ways. A rogue planet might also bring with it a variety of materials, such as gases, dust, or icy bodies, which could further change the dynamics of our solar system. These materials could introduce new environmental conditions that might affect the habitability of neighboring worlds, particularly if they interacted with the atmospheres or surface conditions of planets and moons. Beyond the immediate physical effects, the discovery of a rogue planet entering our solar system would have significant psychological and societal consequences. The news could spark widespread public concern, prompting intensified scientific investigation and leading to discussions about planetary defense strategies. This would likely fuel a renewed focus on celestial monitoring and the development of technologies designed to mitigate the risks associated with rogue planets and other potentially hazardous objects in space. While the likelihood of a rogue planet entering our solar system is statistically low, the potential ramifications of such an event are profound. The gravitational dynamics of the solar system could be severely altered, and the chance of catastrophic impacts would require careful observation and preparedness. As we advance our observational technologies and deepen our understanding of celestial mechanics, we will improve our ability to detect and respond to such cosmic phenomena, ensuring that humanity is better equipped to face the unpredictable threats posed by space. Looking further ahead, in about 4 to 5 billion years, our galaxy, the Milky Way, will collide with the Andromeda Galaxy. This monumental event will reshape the very structure of our universe, although the term collision is somewhat misleading. While a galactic merger may sound like a catastrophic crash, the reality is far more intricate. Such large-scale interactions between galaxies typically occur over vast stretches of time and result in profound yet gradual changes. One of the most immediate implications of this galactic merger is the rearrangement of stellar orbits. As the Milky Way and Andromeda galaxies begin to interact gravitationally, many stars, including those in our solar system, will experience shifts in their trajectories. While the vast distances between individual stars make direct collisions between them exceedingly rare, the gravitational forces at play could still pull our solar system into different regions within the newly formed galaxy. This change in position relative to other stars may have long-term consequences for the environment of our solar system, though the full impact remains uncertain. As we stand on the cusp of an era where our understanding of cosmic forces is rapidly expanding, the future of our solar system and our place within the broader universe remains a topic of great scientific inquiry. However, the gravitational interactions between celestial bodies could lead to significant disturbances in the orbits of nearby stars, shaking the very fabric of the solar system. This upheaval may extend its reach to the Oort cloud, a distant region populated by comets and icy bodies that is on the outermost edge of our solar system. The gravitational forces at play have the potential to send some of these objects spiraling inward, bringing them closer to the inner regions of the solar system. As these bodies move, the likelihood of cometary activity impacting the planets, Earth included, would increase. These forces would not only affect objects within our solar system, but also ripple outward, altering the trajectories and behaviors of countless cosmic bodies. The merger of the Milky Way and Andromeda galaxies will likely have profound consequences on their structure and dynamics. As these two massive galaxies collide, they are expected to form a new combined galaxy, often referred to as Mila. This cosmic transformation will pull stars from both galaxies towards the center, where both galaxies' cores will merge, potentially forming a singular, enormous elliptical galaxy. The process will be messy, violent, and unpredictable, with bursts of star formation occurring in the central regions. These bursts are driven by the compression of gas and dust clouds as the galaxies collide and feed into the new core. Additionally, the interaction between the Milky Way and Andromeda may trigger the expansion of the newly formed galaxy. The gravitational forces from the merger could lead to the formation of new star clusters and regions of active star creation. In turn, this could offer the right conditions for new solar systems to form, creating entirely new worlds over time. As this cosmic dance unfolds, the Milky Way's role within the universe will evolve, with the merger shaping the future trajectory of our galaxy. Despite these monumental changes, however, the solar system, including Earth, is expected to endure, largely intact, albeit in a vastly different galactic environment. But this collision, like many cosmic events, operates on timescales so vast they are almost incomprehensible. The entire merger could take billions of years to unfold fully, meaning that while humanity may be long gone, the ripples of this event will still be felt in distant futures. As a result, the effects of this galactic merger could play a crucial role in influencing conditions within the galaxy that may support life, potentially paving the way for new possibilities or challenges for life beyond our own solar system. Beyond the dramatic cosmic events on a galactic scale, another hidden danger awaits travelers who venture beyond Earth's protective atmosphere: cosmic radiation. This invisible threat is ever present, and understanding its potential long-term impacts is critical for planning missions to the farthest reaches of our solar system, such as Mars and beyond. Cosmic radiation, composed primarily of high-energy charged particles from sources like supernovae and the Sun, is capable of penetrating spacecraft and even human tissue. Once inside the body, these particles can wreak havoc on biological systems, leading to various health issues for astronauts on long-term missions. One of the most dangerous long-term effects of cosmic radiation is its ability to increase the risk of cancer. The high-energy particles can cause damage to DNA, resulting in mutations that could lead to cancerous growths. For astronauts, the risk is particularly acute on missions outside the protective shield of Earth's atmosphere. As they venture farther into space, they accumulate a cumulative dose of radiation that could elevate their chances of developing cancer. Therefore, careful monitoring and protective strategies are essential to safeguard astronaut health. While the threat of cancer looms large, another risk of cosmic radiation is acute radiation syndrome. Though this is more likely to occur during solar particle events, where large bursts of radiation suddenly bombard space travelers, astronauts may also experience its effects during extended missions due to the cumulative exposure to lower doses over time. Symptoms of acute radiation exposure could include nausea, fatigue, and various other short-term health problems that could complicate the mission and its objectives. The brain, however, is not immune to the damage caused by prolonged radiation exposure. Research suggests that high levels of cosmic radiation can lead to cognitive decline, impaired memory, and even psychological changes in astronauts over time. These effects can have far-reaching consequences for mission success, as mental health and cognitive function are critical in maintaining crew performance, morale, and overall mission effectiveness. As space exploration ventures further into deep space, maintaining the cognitive well-being of astronauts will be just as crucial as their physical health. Further complicating the dangers of deep space travel, cosmic radiation also poses a potential threat to reproductive health. Studies indicate that increased radiation exposure may interfere with fertility, disrupt embryonic development, and lead to genetic mutations that could affect future generations. This concern becomes especially important on long-duration missions, where the exposure times are far greater, and the risks to crew members' long-term health may only become evident after years of space travel. To mitigate these risks, spacecraft designed for interplanetary travel must be equipped with robust shielding to protect astronauts from the harmful effects of cosmic radiation. Effective shielding materials such as polyethylene or water can absorb or deflect high-energy particles, significantly reducing the amount of radiation that reaches the crew. Ensuring that this shielding is incorporated into spacecraft design is essential for the health and safety of astronauts traveling to distant planets and beyond. In the end, the cosmic forces shaping our universe and the dangers of radiation will both play pivotal roles in determining the future of space exploration. Whether venturing through the galaxy's new structure or tackling the biological risks of deep space travel, the path ahead will demand resilience, innovation, and a profound understanding of the forces at play on both a galactic and personal scale. Mission planning for space exploration must evolve to address the persistent dangers posed by cosmic radiation, ensuring the health and safety of astronauts venturing beyond Earth's protective atmosphere. It's not merely about navigating the unknown, it's about protecting human life. Thus, comprehensive mission frameworks should incorporate sophisticated radiation monitoring systems, constantly tracking exposure levels and adjusting crew schedules during solar events. The unpredictable nature of solar storms demands that crews be able to adapt quickly, maintaining safety in environments that are inhospitable by earthly standards. However, the effects of cosmic radiation extend far beyond a simple precautionary measure. This issue requires long-term strategies, research, and technological advancement. Radiation protection research, alongside breakthroughs in spacecraft design and mission logistics, is crucial for overcoming the challenges of deep space exploration. The future of interplanetary travel depends on our ability to shield astronauts from radiation that can harm their health, jeopardizing their missions and even their lives. Only with sustained effort can we ensure that humans can live and work safely in the vacuum of space, far from the cradle of Earth's atmosphere. In tandem with cosmic radiation, another potential threat to our planet and our spacefaring future is the risk posed by near-Earth objects, NEOs. These include asteroids, comets, and other celestial bodies that could have catastrophic consequences if they collide with Earth. As awareness of these risks grows, so does international collaboration to understand and mitigate these threats. The process begins with detection. Global observatories, together with space missions, are dedicated to scanning the skies for NEOs. Programs like NASA's Near-Earth Object Observing Program and the European Space Agency's Space Situational Awareness Program employ both ground-based and space-based telescopes to spot new objects, track their orbits, and provide early warnings of potential dangers. Automated systems further streamline this process, analyzing vast amounts of data to prioritize the most critical objects. These systems help track newly discovered bodies, assessing their risk potential by examining their trajectories and calculating their likelihood of impact with Earth. Once a NEO is identified, tracking its path becomes the next essential step. Precise measurements allow astronomers to chart its course, predicting whether it poses a collision risk within a given time frame. Understanding the object's size, shape, and velocity allows scientists to predict whether its orbit could change over time, either due to gravitational interactions with other objects or because of sunlight. Tools like the Palermo Technical and Torino scales are commonly used to communicate the risk level of NEOs, with both scales offering a framework to assess the threat they pose. Yet, detection and tracking are just the beginning. To fully understand a NEO's potential threat, we must characterize it. What is it made of? Is it solid rock, a loose rubble pile, or does it contain volatile substances? Knowing the composition and structure of a NEO can help determine the most effective mitigation strategies. Space missions like NEOWISE and the upcoming Double Asteroid Redirection Test, DART, aim to gather invaluable data on specific NEOs, providing a clearer picture of what we are up against and how we can deal with them. When it comes to mitigation, there are several strategies on the table, each with varying degrees of feasibility and risk. Kinetic impactor technology, for instance, involves sending a spacecraft to collide with a NEO, altering its trajectory just enough to avoid an impact with Earth. The DART mission is designed to demonstrate this technique by targeting a binary asteroid system, proving the concept that a direct collision can change the object's orbit. Another method being explored is the gravitational tractor technique. In this scenario, a spacecraft would position itself near a NEO, using its own gravitational pull to gradually alter the object's course. This method would be slower, but it could provide a more controlled and long-term solution, especially for objects that are further out in space. For larger NEOs, or those on a more immediate collision course, more extreme measures have been suggested, such as nuclear disruption. The idea here is to detonate a nuclear device near a NEO, causing it to change its path. While this may sound like science fiction, it is considered a potential last resort. However, such a strategy comes with its own set of challenges, including the potential for unintended consequences. Therefore, international cooperation and careful planning are vital before pursuing this option. Ultimately, dealing with the threat of NEOs requires a concerted effort from national space agencies, international organizations, and private sector collaborators. Through ongoing research, heightened awareness, and preparedness initiatives, humanity can develop the necessary tools to detect, track, and mitigate the risks posed by these objects. As our understanding of NEOs deepens, so too does our capacity to protect Earth from potentially devastating impacts. By taking these steps, we ensure that our planet and its inhabitants remain safe, even as we push the boundaries of space exploration.